is preparing for the most perfect death in human history. You might think space is calm and predictable, yet the universe around us is experiencing events far beyond our imagination. Tonight, we will set out on an exploration toward microquasars that fire particle beams at impossible speeds, passing through plasma highways carved by ancient explosions, and moving past rogue black holes hunting through our galaxy. We will witness a hidden companion star that delays cosmic destruction, explore tunnels that connect distant worlds, and learn why our night sky is standing on the edge of a transformation. If you're subscribed, we can begin. When scientists finally detected the ghost following Betelgeuse, they couldn't believe what they were seeing on their screens. For decades, astronomers watched this red supergiant dim and brighten in mysterious cycles. They believed the star was dying, with carbon in its core burning like a cosmic time bomb. But the truth shocked everyone who thought they understood stellar death. We introduce you to Betelgeuse's companion, a blue-white companion star no one expected. This stellar partner orbits Betelgeuse once every 2,100 days and behaves like a cosmic snowplow moving through clouds of dust. Think of a speedboat cutting a wake across water. As this companion passes through the material constantly ejected into space by Betelgeuse, it creates the brightness changes we observe from Earth. The discovery was made using the Gemini North telescope with a specialized speckle imaging technique. Scientists found this hidden companion behind Betelgeuse's blinding glare. The blue-white star shines far more faintly than its giant red partner, like trying to spot a candle next to a stadium floodlight. Here comes the shocking part. Betelgeuse was predicted to explode within decades. Astronomers had forecast a near-term supernova based on the brightness cycles they observed. The companion star changes everything. These cycles come not from internal stellar collapse, but from orbital mechanics. Betelgeuse's companion extends the star's lifespan from decades to hundreds of thousands of years. When Betelgeuse finally explodes, the spectacle will be unlike anything in recorded human history. The supernova will shine at a magnitude between -10 and -12. Imagine a star as bright as a half moon, visible in daylight for months. At midnight, you could read a book by the light of the supernova. The explosion will cast shadows on Earth from 400 trillion miles away. Betelgeuse extends to 700 times the radius of our Sun. If you placed this monster where the Sun is, its surface would stretch beyond Jupiter's orbit. Material released by recent surface eruptions equals the combined output of 400 billion solar flares. During the Great Dimming event of 2019-2020, 40% of the star's light was blocked by clouds of ejected dust. Current measurements place Betelgeuse at exactly 642 light-years from Earth. At this distance, the supernova poses no danger. However, neutrino detectors will warn us 10 to 15 seconds before the light reaches our eyes. We will literally watch the future arrive. The discovery of the companion star is rewriting supernova prediction models. Binary systems behave differently from single stars. Mass exchange between stellar partners affects nuclear burning rates. Orbital mechanics influence stellar winds and dust production. What looked like the pains of death were actually movements in a gravitational dance. Betelgeuse's companion teaches us that even the most famous stars still keep secrets. From our perspective, the night sky appears static. Stars seem fixed in constellation patterns passed down for thousands of years. Yet stellar systems reveal themselves in complex ways we barely understand. Multiple star systems dominate the galaxy, while single stars, like our Sun, are the exception. This discovery confronts us with new questions about stellar evolution and supernova timing. How many other giant stars have hidden companions? What other assumptions about stellar death need to be re-examined? Betelgeuse may surprise us again before its final performance. But what is approaching from the depths of space makes Betelgeuse seem like a gentle friend? Within 1.3 million years, an orange giant will dominate Earth's night sky like no star in human memory. When you look toward the constellation Ophiuchus today, you see nothing special. The star hiding there appears so faint that you need a telescope to detect it. And yet, this cosmic sleepwalker will become brighter than all the stars we see today combined. Gliese 710 is creeping toward us at 43,000 miles per hour. This orange dwarf star is currently 63.8 light-years away in the constellation Serpens. With a magnitude of 9.7, it is invisible to the naked eye. Amateur astronomers struggle to find this ordinary K7V class star among thousands of similar faint points. The approaching encounter will completely rewrite Earth's night sky. Gliese 710 will pass within 0.166 light-years of our solar system. That distance is roughly 10 trillion miles, closer than any star has come in millions of years. The orange giant will shine at magnitude -2.7, rivaling Jupiter's brightness and outshining Sirius by a factor of 4. Imagine this cosmic visitor growing brighter each night. Unlike every star you see today, Gliese 710 will appear as a true disk rather than a point of light. The approaching star will become 140,000 times brighter than it is now. You will be able to watch it visibly move across the sky by about 1 arc-minute per year, like the moon sliding past background stars. Gliese 710 will reign as Earth's brightest star for roughly 20,000 years. The encounter transforms far more than brightness records. This stellar visitor will plow through the Oort cloud like a wrecking ball. Gravitational forces will scatter trillions of icy bodies in every direction. The Oort cloud surrounds our solar system like a spherical shell of frozen comets. These ancient remnants from the formation of the solar system orbit at distances of up to 100,000 astronomical units. When Gliese 710 passes through this field of cosmic debris, gravity will hurl countless objects toward the inner planets. Computer models predict that for millions of years following the encounter, about 10 comets per year will stream toward Earth and Mars. The late heavy bombardment that scarred planetary surfaces 4 billion years ago will essentially restart. Impact craters will cover every solid surface from Mercury to the asteroid belt. The orange star is slightly smaller than our Sun, with about 60% of the Sun's mass. A surface temperature of 4,000 Kelvin gives Gliese 710 its characteristic orange color, painting our night sky. Spectroscopic analysis reveals that this star burns hydrogen steadily, without dramatic variability or stellar flares. Advanced civilizations around distant stars likely noticed our Sun approaching their systems millions of years ago. Just as we will observe Gliese 710, they may have watched our yellow star brighten in their skies. Perhaps they prepared for the gravitational disturbance of their own comet clouds. In our galactic neighborhood, the rate of stellar encounters averages 1 close pass every few million years. Previous visitors have repeatedly reshaped the Oort cloud throughout Earth's history. Mass extinction events may be linked to these stellar encounters through increased comet bombardment. Gliese 710 poses no radiation threat due to its stable hydrogen burning. The star does not produce harmful X-rays or gamma radiation, capable of damaging Earth's atmosphere. Instead, solar system dynamics face their primary danger from the gravitational disturbance of long-period comets. Even so, this approaching stellar giant pales beside the architectural wonders carved across our region by ancient explosions. The space between stars hides a secret highway system linking our solar system to distant worlds. You imagine interstellar space as an empty darkness dotted with isolated points of light. That picture is completely wrong. Ancient stellar explosions carved vast tunnels across the galaxy, creating channels of superheated gas stretching for thousands of light years. Scientists using the E-Rosetta X-ray telescope discovered these cosmic highways by accident while mapping background radiation. The space surrounding our solar system glows with million-degree plasma that should have cooled long ago. Instead of random clouds of hot gas, observations revealed organized structures pointing in specific directions. These interstellar tunnels formed from multiple supernova explosions occurring over millions of years. When massive stars explode, they hurl shells of material outward at thousands of miles per second. Imagine throwing a stone into a pond and watching ripples spread across the surface. Stellar explosions work in a similar way, except the ripples are shock waves of superheated plasma expanding through space. Multiple supernovae in the same region create overlapping blast zones. The expanding shells collide and merge, carving channels through the interstellar medium like rivers cutting through a landscape. These cosmic waterways follow paths of least resistance, linking regions where ancient star formation once occurred. The local hot bubble surrounding our solar system spans roughly 300 light-years in diameter. This cavity contains gas heated to temperatures of up to 1.2 million Kelvin, about 100 times hotter than the surface of the Sun. The bubble formed when nearby stars exploded between 10 and 20 million years ago. However, the local hot bubble is not isolated. Tunnel-like extensions connect our cosmic neighborhood to distant stellar regions. The most prominent tunnel stretches toward the constellation Centaurus, potentially providing a direct pathway to the Alpha Centauri system, located just 4 light-years away. These plasma highways offer fascinating implications for interstellar travel. Spacecraft could move through low-density channels instead of pushing through normal interstellar space. The tunnels contain roughly 1/10 the particle density of surrounding regions, reducing drag on hypothetical starships. The tunnel network resembles the cosmic web structure that organizes matter on galactic scales. Just as dark matter filaments connect galaxy clusters, these plasma channels link stellar neighborhoods together. The architecture reveals that supernova explosions follow patterns tied to spiral arm dynamics and the history of star formation. Scientists have discovered similar tunnel systems around other nearby stars. The network may extend along the local galactic arm, potentially forming a transportation grid for advanced civilizations. X-ray observations reveal temperature gradients along the tunnel walls, where hot plasma meets cooler surrounding material. These boundary layers create complex fluid dynamics with regions of turbulence and mixing. Despite ongoing evolution, the tunnels remain stable for millions of years. The discovery shifts our understanding of the interstellar medium from a static void to a dynamic architecture. The space between stars is stirred by ongoing processes driven by stellar evolution. The galaxy operates less like a collection of isolated objects and more like a living organism. Future space missions could use these plasma channels as natural highways between star systems. Reduced particle density would allow higher speeds with less radiation shielding. Interstellar travel becomes far more practical when a cosmic infrastructure is already in place. Yet, the most extraordinary tunnel of all points toward our nearest stellar neighbors, offering possibilities that science fiction has barely dared to imagine. A direct tunnel of superheated gas connects our solar system to Alpha Centauri, creating the first interstellar highway ever discovered. You've always assumed that a 4-light-year journey to our nearest stellar neighbors would require crossing empty space filled with cosmic dust and radiation. The reality is far more astonishing than anyone expected. The Centaurus tunnel extends in an almost straight line from the local hot bubble toward the Alpha Centauri system. This plasma channel maintains remarkably consistent properties across light-year distances, like a cosmic fiber optic cable made of million-degree gas. The tunnel walls display remarkable stability, despite the violent forces that created them. X-ray telescopes reveal the highway structure in exquisite detail. The central channel measures roughly 50 light-years in diameter, wide enough to contain entire solar systems. Temperature readings show the tunnel interior averages about 1.4 million Kelvin, hot enough to instantly strip electrons from atoms. The plasma highway formed from multiple supernova explosions occurring in sequence between our region and Alpha Centauri. Imagine a line of falling dominoes. Each stellar explosion triggered shock waves that carved the tunnel structure deeper. The process required precise timing over millions of years. Alpha Centauri sits at the far end of the tunnel, like a lighthouse marking a cosmic harbor. The triple star system consists of Alpha Centauri A, a sun-like yellow star, Alpha Centauri B, an orange dwarf companion, and the red dwarf Proxima Centauri, which may host potentially habitable planets. The highway reduces travel time for hypothetical spacecraft in unexpected ways. While the tunnel does not shorten the physical distance, its low particle density allows for much higher speeds. Interstellar ramjet concepts could collect plasma directly from the tunnel to use as propulsion fuel. Scientists calculate that spacecraft could reach 10% of the speed of light while traveling through the Centaurus tunnel. With current theoretical technology, travel time drops from 40,000 years using conventional rockets to just 40 years for plasma-propelled ships. Advanced civilizations could cross the highway in decades instead of millennia. The tunnel also provides natural protection from cosmic radiation. Dense plasma walls deflect the high-energy particles that normally bombard spacecraft during interstellar flight. Magnetic fields embedded in the tunnel structure create protective barriers similar to planetary magnetospheres. Temperature measurements reveal fascinating dynamics inside the plasma highway. Hot gas flows toward Alpha Centauri at hundreds of miles per hour, creating a cosmic tailwind that could assist outbound missions. Return journeys would have to fight against this plasma flow, but would still benefit from the reduced particle density. The discovery suggests that similar tunnels connect other nearby star systems. The local galactic arm may contain an entire network of plasma highways left behind by ancient chains of supernovae. Future studies with advanced X-ray telescopes could map this interstellar infrastructure. Proxima Centauri b, the potentially habitable planet orbiting our nearest red dwarf neighbor, becomes far more accessible thanks to the tunnel route. This rocky world receives stellar radiation levels similar to Earth and may host liquid water oceans. The plasma highway transforms Proxima from an impossible destination into a challenging but reachable target. The existence of the tunnel implies that advanced extraterrestrial civilizations may already be aware of these cosmic highways. Any species that develops interstellar travel capabilities would discover plasma channels through X-ray astronomy. They may already be using the tunnel network. Communication along the Centaurus tunnel could also benefit from plasma wave propagation. Radio signals can travel faster through ionized environments than through normal space. The tunnel could serve as a natural waveguide for interstellar messaging. Yet, the plasma highway represents only a single thread within a vast cosmic infrastructure network that dwarfs anything humans have ever imagined. Rivers of plasma, hotter than stellar cores, flow between star systems and create a galactic transportation network spanning thousands of light years. You imagine space as cold and empty, a vacuum that spacecraft must struggle through. The truth reveals that space is a turbulent ocean of superheated gas organized into vast currents that dwarf any terrestrial river system. These cosmic highways carry temperatures reaching 2 million Kelvin, 20 times hotter than the surface of the sun. Plasma flows move at hundreds of miles per hour and generate stellar winds capable of powering entire civilizations. Magnetic fields embedded within the gas streams generate forces equivalent to billions of nuclear power plants. The highway system emerged from some of the most violent events in galactic history. Supernova explosions pump enormous amounts of energy into the interstellar medium and create shock waves that propagate for millions of years. These shock waves heat surrounding gas to extreme temperatures and set it in motion along predictable paths. Think of cosmic highways as celestial arteries carrying the lifeblood of star formation across the galaxy. Hot plasma streams transport heavy elements forged in stellar cores to regions where new stars will form. Carbon, oxygen, iron, and other materials required for rocky planets surf between stellar nurseries within these cosmic currents. Scientists are mapping the highway network using X-ray observatories that detect thermal emissions from superheated gas. The plasma glows like neon lights, marking interstellar highways visible from thousands of light years away. Advanced alien civilizations could navigate using these cosmic landmarks, just as ancient sailors once used the stars. The local hot bubble sits at a major highway junction. That explains the complex structure. Multiple plasma flows converge near the solar system before branching off toward different galactic destinations. We live inside a cosmic traffic hub connecting dozens of stellar neighborhoods. Plasma speeds inside the highway reach 300 kilometers per second, fast enough to cross the entire solar system in just 1 week. Spacecraft could ride these currents like sailing ships using trade winds, reaching interstellar speeds that are impossible with conventional propulsion. The key lies in understanding plasma physics and magnetic field interactions. Highway walls show remarkable organization despite the chaotic forces that created them. Gradients create distinct layers where the hot central plasma meets cooler surrounding material. These boundary regions can generate turbulence and mixing that enrich the interstellar medium with woven stellar materials. Magnetic fields thread through plasma flows like invisible train tracks that guide charged particles along specific paths. These field lines stretch across light years without breaking, creating cosmic infrastructure that could guide spacecraft navigation systems or interstellar communication. The highways also influence galactic weather patterns by transporting energy between active star-forming regions. Hot plasma from stellar nurseries flows toward cooler regions, equalizing temperatures across vast volumes of space. This cosmic climate control affects where and when new stars can form. Recent discoveries revealed that the highway network connects to similar structures in neighboring galaxies. The local galaxy group shows evidence of intergalactic plasma bridges spanning millions of light years. The cosmic highway system may extend across the observable universe. Future space missions could map these plasma highways in detail and reveal optimal routes for interstellar exploration. Just as ancient traders followed river systems to reach distant lands, spacefaring civilizations could use cosmic currents to traverse the galaxy efficiently. The highway system operates continuously, renewed by ongoing stellar explosions and powered by galactic rotation. Unlike human-made infrastructure that requires maintenance, these cosmic highways are self-sustaining and grow stronger over time as more supernovae add energy to the network. Yet, all of these vast plasma rivers flow within an even larger structure that surrounds our entire solar system in ways we are only beginning to understand. We live inside a giant soap bubble made of million-degree gas stretching farther than most people could ever imagine. You might think our solar system is freely floating through empty space between distant stars. The reality is that we exist inside a vast cavity carved by ancient explosions, surrounded by walls of superheated plasma extending 300 light-years in every direction. The local hot bubble formed 10 to 20 million years ago when massive stars in our cosmic neighborhood exploded one after another. These supernova explosions carved out a spherical void in the interstellar medium, much like underground blasts create cave systems. Shock waves pushed dense gas away from our region, leaving behind a hollow space filled with extremely hot, thin plasma. Inside the bubble, the gas density drops to about 1/10 of typical interstellar values. This low-density environment reduces radiation exposure for any spacecraft traveling between nearby stars. The bubble also blocks cosmic rays from distant galactic sources, creating a partially shielded region around our solar system. Temperature measurements reveal that the interior of the bubble averages 1.2 million Kelvin. This sounds incredibly hot, but the gas is so thin that the human body would instantly freeze despite the high temperature. Think of the difference between a campfire and a blast furnace. Both produce heat, but a campfire contains more total thermal energy because it has more fuel. Within the boundaries of the local hot bubble, there are roughly 500 stars, including many of the bright stars visible in Earth's night sky. Sirius, Procyon, Altair, and other familiar stellar names shine from within our cosmic neighborhood. These stars appear prominent because we observe them through the bubble's clear interior rather than through dust-obscured outer regions. Scientists, using the Arosita X-ray telescope, discovered the bubble's asymmetric shape. Instead of forming a perfect sphere, the cavity shows elongated extensions and irregular boundaries. These deformations arise from interactions with other nearby supernova remnants and with the structure of the galaxy's magnetic field. The walls of the bubble are made of compressed gas heated to temperatures exceeding 2 million Kelvin. These boundary regions glow brightly at X-ray wavelengths, creating a cosmic shell visible to space-based telescopes. The wall thickness varies between 10 and 50 light-years, depending on local conditions. Stellar winds from hot stars inside the bubble protect the cavity against gravitational collapse. These winds carry enough energy to prevent surrounding dense gas from flowing back into the cleared region. The bubble remains stable for tens of millions of years before external forces begin to compress it. The solar system sits slightly off-center within the local hot bubble, closer to the boundary in the direction of the constellation Centaurus. This asymmetric position explains why we see more dust and gas clouds in some directions of the sky compared to others. The edge of the bubble appears across our night sky as the visible band of the Milky Way. Recent studies suggest that the bubble continues to expand slowly as additional stellar explosions inject energy into the structure. Young, massive stars within the cavity will eventually explode as supernovae, potentially enlarging the bubble further or creating side cavities connected to the main volume. The discovery of the local hot bubble revolutionized our understanding of the solar system's galactic environment. Rather than traveling through uniform interstellar space, we live in a special region shaped by cosmic violence. This protected zone may have influenced Earth's climate and biological evolution by reducing exposure to harmful radiation. Across the galaxy, advanced extraterrestrial civilizations likely live within similar bubble structures created by local supernova activity. These cosmic refuges provide ideal conditions for long-term planetary evolution and technological development. Life may concentrate inside hot bubbles rather than in the denser, more radiation-rich regions of the galaxy. The ultimate fate of the bubble depends on future stellar explosions and interactions with neighboring supernova remnants. Our cosmic home will evolve and likely merge with adjacent cavities, creating even larger cleared regions within the interstellar medium. But as we drift safely inside this protective cocoon, somewhere else in the galaxy, a stellar bomb is preparing to explode with the power of billions of nuclear weapons. 3,000 light-years away, a white dwarf star is accumulating stolen hydrogen like a cosmic suicide bomber preparing to detonate. When you scan the constellation Corona Borealis tonight, you see nothing unusual among its faint stars. Yet hidden within this celestial crown, an unseen stellar remnant is racing toward a thermonuclear explosion that will suddenly create Earth's newest naked-eye star. T Corona Borealis consists of two stars locked in a deadly orbital dance. The primary white dwarf has a mass comparable to our Sun, but is only Earth-sized, generating surface gravity 300,000 times stronger than that of our planet. Its companion, a bloated red giant star, slowly bleeds material toward the compact monster through gravitational pull. The mass transfer process is like a cosmic vampire feeding on its victim. Hydrogen-rich gas flows from the outer atmosphere of the red giant toward the white dwarf in a spiraling stream called an accretion disk. This disk glows at temperatures of 50,000 Kelvin, where gravitational energy is converted into heat through friction. Material accumulates on the surface of the white dwarf like snow piling up during a snowstorm. But this stellar snow consists of compressed hydrogen gas heated to millions of degrees. The crushing gravity of the white dwarf compresses the accumulated layer until conditions for nuclear fusion develop at the surface. When the hydrogen layer reaches a critical thickness, explosive nuclear burning ignites simultaneously across the entire surface of the white dwarf. This runaway fusion process releases more energy in seconds than our Sun produces in thousands of years. The explosion hurls the accumulated material into space at speeds exceeding 6,000 miles per second. T Coronae Borealis last erupted in 1946, creating a second-magnitude star visible to the naked eye for several days. Astronomers recorded detailed observations as the new star rapidly brightened and then faded over the course of several weeks. The cycle repeats roughly every 80 years as the white dwarf rebuilds its supply of hydrogen fuel. Current observations show that all indicators point to an imminent eruption. The system has been dimming since March 2023, following the same pattern observed before the 1946 outburst. Spectroscopic monitoring reveals increasing mass transfer rates and an expanding accretion disk radius. The upcoming explosion will increase the brightness of T Coronae Borealis by a factor of 1,000, transforming it from an invisible telescopic object into a star of visible magnitude comparable to Polaris. The eruption will be visible worldwide to naked-eye observers, creating a visible star where none existed before. Professional observatories around the world are preparing for intensive monitoring when the eruption occurs. The James Webb Space Telescope, the Hubble Space Telescope, and ground-based facilities are planning coordinated observations across all wavelengths. This event represents the first recurrent nova eruption observable with modern space-based instruments. The nova explosion will eject roughly 1/10,000th of the white dwarf's mass into surrounding space. This material, enriched with carbon, oxygen, and other heavy elements created during the fusion blast, will contribute to the interstellar medium and to future star formation processes. Timing predictions focus on late 2025, with some models suggesting November 10 as the most likely eruption date. However, stellar explosions follow complex physics that make precise prediction impossible. The eruption could occur on any night within the next few years. The recurrent nova phenomenon demonstrates how white dwarf stars can explode repeatedly without destroying themselves. Unlike Type A supernovae, in which the white dwarf is completely destroyed, recurrent novae blow off only the surface layers while leaving the compact core intact for future cycles. T Coronae Borealis belongs to a rare class of only 10 known recurrent novae in the entire galaxy. These systems require delicately balanced conditions in which mass transfer rates match nuclear burning timescales. Too little material produces no eruption, while too much triggers complete destruction. The upcoming eruption offers unprecedented opportunities to study stellar nuclear physics in real time. Modern instruments can observe the eruption's evolution from initial ignition through material ejection and subsequent cooling. These observations will refine models of nuclear burning on stellar surfaces. Even so, this controlled stellar explosion seems gentle when compared to the rogue celestial objects drifting alone through the cosmic wilderness between stars. One night, this year or next, you will witness something no human has seen for nearly 80 years. A completely new star in the constellation Corona Borealis will suddenly come to life, shining brightly enough to be seen without a telescope or binoculars. This stellar birth does not come from the formation of a new sun out of gas and dust, but from an explosive event violent enough to outshine entire galaxies. The new star will appear between the bright stars Arcturus and Vega, creating the distinctive arc pattern ancient astronomers called the Northern Crown. You can find Corona Borealis by looking northeast on summer evenings, where 7 stars form a semicircular crown. The new arrival will join this cosmic jewel as the constellation's second brightest member. When T Coronae Borealis erupts, the light show begins within hours. The invisible 10th magnitude star will brighten rapidly, gaining luminosity faster than any supernova. Within days, it will reach 2nd magnitude, matching the brightness of Polaris. The creation of a visible star will be observable worldwide to the naked eye for about 1 week. Professional astronomers call this phenomenon a recurrent nova, but the name understates the drama involved. The eruption releases 10 billion times more energy than the most powerful nuclear weapons ever built. If you could bottle the energy from just 1 second of the explosion, it would power human civilization for millions of years. As the ejected material expands into space, the eruption creates spectacular visual effects. High-speed cameras will capture the evolution of the blast, revealing glowing shells of gas expanding at speeds of 6,000 miles per second. These ejecta form complex patterns as they collide with material expelled during previous eruptions. Spectroscopic observations will reveal the chemical signature of the explosion as different elements produce characteristic colors. Hydrogen burns with deep red light. Oxygen glows green and blue, while carbon appears at ultraviolet wavelengths. The nova becomes a cosmic laboratory for studying nuclear physics under extreme conditions. The brightness of the new star will fluctuate dramatically during the first few weeks after the eruption. Initial observations show rapid brightening following irregular variations as the blast wave spreads through surrounding material. Multiple peaks and valleys create a complex light curve. Unlike the behavior of constant stars, amateur astronomers worldwide will contribute valuable observations using simple equipment. Digital cameras and basic telescopes can track the nova's changes in brightness and color evolution. Citizen science projects will coordinate thousands of measurements from observers in different time zones. The eruption will be visible from every continent outside Antarctica during local nighttime hours. Observers in the southern hemisphere will see Corona Borealis low on the northern horizon, while northern observers enjoy the constellation high above their heads. Light pollution in large cities will dim the view, but cannot hide an event this bright. Space-based telescopes will observe wavelengths invisible from Earth's surface. The Hubble Space Telescope will capture ultraviolet light from the hottest regions of the eruption. The James Webb Space Telescope will peer through dust clouds using infrared detectors. X-ray observatories will track the most energetic emissions from the blast. The appearance of the nova will trigger intense media coverage as news organizations report the sudden creation of a star. Social media will explode with amateur photographs and time-lapse videos showing the emergence of the new star. This will be the first major astronomical event of the smartphone era visible without specialized equipment. Educational systems worldwide will use the nova as a teaching opportunity to explain stellar evolution and nuclear physics. Students will be able to observe ongoing astrophysical processes rather than studying static textbook illustrations. The eruption demonstrates cosmic violence on scales that dwarf everyday human experience. The new star will gradually fade over several months as the ejected material expands and cools. Next year, T Coronae Borealis will return to invisibility, leaving only faint nebular remnants detectable with powerful telescopes. The next eruption will occur roughly 80 years later when today's children have grown old. Yet this controlled stellar eruption represents only one type among many forms of destruction that white dwarf stars can unleash. The most common stellar remnants in our galaxy act as cosmic time bombs waiting for the right conditions to explode. White dwarf stars appear as peaceful points of light, slowly cooling over billions of years. The reality is far more explosive. These stellar corpses can trigger nuclear blasts rivaling the most violent events in the universe. White dwarf stars form when sun-like stars exhaust their nuclear fuel and shed their outer layers. The remaining core collapses under its own gravity until electron pressure halts further compression. The result is a stellar remnant compressed into a sphere the size of Earth with the mass of the Sun. The surface gravity on a white dwarf reaches 300,000 times that of Earth. A sugar cube on such a world would weigh as much as a car. This crushing gravitational field creates the conditions necessary for explosive nuclear burning whenever fresh fuel becomes available. Most white dwarfs are found in binary systems with companion stars orbiting them. When the companion expands during its own stellar evolution, material begins flowing toward the white dwarf under gravitational pull. This process turns peaceful stellar remnants into potential superweapons. The transferred material accumulates on the white dwarf's surface in a thin layer that becomes denser over thousands of years. Temperature and pressure gradually increase until nuclear fusion conditions develop. Unlike controlled burning in stellar cores, fusion on white dwarf surfaces proceeds explosively once ignited. Nova eruptions occur when accumulated hydrogen ignites in uncontrolled nuclear reactions. The explosion consumes the entire surface layer within hours, hurling material at thousands of miles per second. The energy release exceeds that of 10 billion nuclear weapons simultaneously detonating on the white dwarf's surface. Some white dwarfs trigger even more catastrophic explosions, called Type 1a supernovae. When accumulated material pushes the white dwarf's mass beyond 1.4 solar masses, the entire star detonates in a thermonuclear explosion visible across billions of light years. Nothing remains except expanding clouds of debris enriched with heavy elements. The galaxy contains roughly 10 billion white dwarf stars, making them the most numerous stellar remnants. About half reside in binary systems capable of mass transfer events. This means there are roughly 5 billion potential nova or supernova progenitors across the Milky Way, waiting for the right triggering conditions. Nova eruptions occur roughly once a year in our galaxy. Most happen too far from Earth or behind clouds of dust to be seen. However, historical records document novae appearing as new stars in familiar constellations, visible to the naked eye for a few weeks before fading. The most famous white dwarf bomb resides in the constellation Cygnus, where the white dwarf WD 1933 plus 229 slowly accumulates helium from its companion star. Astronomers predict that this system will explode as a Type 1a supernova within 100 million years, creating a blast visible in daylight. White dwarf eruptions contribute fundamental heavy elements to galactic chemical evolution. Iron, nickel, chromium, and other metals forged in thermonuclear blasts seed the interstellar medium for future star and planet formation. Every atom heavier than oxygen in your body was likely created in white dwarf explosions. The discovery of white dwarf variability revolutionized our understanding of the final stages of stellar evolution. Rather than simply cooling and fading, these stellar remnants remain active participants in galactic processes through explosive interactions with companion stars. Advanced civilizations orbiting white dwarf systems would face periodic extinction events from nova eruptions. The blast radiation would sterilize planets within a few astronomical units and disrupt atmospheric chemistry across entire solar systems. Survival would require either deep underground shelters or interplanetary evacuation. Future space missions could observe white dwarf systems before, during, and after explosive events. Real-time monitoring would reveal the detailed physics of thermonuclear burning under extreme conditions impossible to reproduce in terrestrial laboratories. While white dwarf eruptions represent the most common stellar violence, the systems that create them display even more dramatic examples of cosmic destruction through gravitational warfare. Two stars locked in orbital combat produce some of the most spectacular explosions known to astronomy. You might imagine binary star systems as peaceful cosmic couples dancing together in space. The reality reveals gravitational warfare that tears stars apart, triggers nuclear blasts, and creates some of the brightest events in the observable universe. Close binary systems experience tidal forces that stretch both stellar partners into egg-shaped objects. Gravitational pull elongates each star toward its companion, creating protrusions pointing at the orbital center. These deformations heat stellar surfaces through internal friction, making binary stars brighter and more active than single stars. When one star evolves faster than its companion, the binary system becomes a cosmic vampire. The more massive star first expands into a red giant, filling a gravitational influence region called the Roche lobe. Material from the bloated giant flows toward the compact companion via the gravitational balance point between the two stars. This mass transfer creates magnificent accretion disks around the receiving star. Imagine a cosmic whirlpool where stolen stellar material spirals inward at incredible speeds. Friction heats the disk until it shines, brighter than many galaxies, producing some of the brightest objects in the universe. The most extreme binary systems contain a black hole or neutron star paired with a normal stellar companion. These high-mass compact objects strip material from their partners with devastating efficiency. Gas falling toward the compact object accelerates to a significant fraction of the speed of light, producing X-ray emission visible across galactic distances.
Cataclysmic variables represent binary systems where a white dwarf siphons hydrogen from its main sequence companion. Accumulated material builds up on the white dwarf's surface until explosive nuclear burning ignites. These nova eruptions can repeat every few decades or centuries, creating recurrent stellar bombs. Some binary systems experience contact phases where the surfaces of both stars actually touch. The two stars share a common atmospheric envelope while their cores remain separate. These contact binaries often merge completely, triggering bright red nova eruptions, temporarily outshining their host galaxies. X-ray binaries produce jets of material moving at nearly the speed of light. These relativistic flows extend light years from the central binary, creating cosmic blowtorches, heating surrounding gas above 1 billion degrees. Although the jets originate from stellar mass objects, they rival quasar emissions. Wolf-Rayet binary systems display the most violent stellar winds known to astronomy. These hot, massive stars lose material at rates millions of times higher than the sun's solar wind. Paired with compact companions, their interactions generate complex shock structures and particle acceleration regions. Symbiotic stars illustrate long-term binary evolution, where a white dwarf slowly accretes material from a red giant companion over millions of years. These systems undergo periodic eruptions as accumulated material reaches critical densities for explosive nuclear burning. The cycle can repeat hundreds of times over the lifetime of the binary. Type 1a supernovae, the thermonuclear explosions that destroy white dwarf stars, occur exclusively in binary systems. The white dwarf must accumulate enough material from its companion to exceed the critical mass limit. These explosions serve as standard candles for measuring cosmic distances and probing dark energy. Gravitational wave observatories detect kilonovae, explosive events from merging neutron star binaries that create heavy elements like gold and platinum. These cosmic collisions occur when two ultra-dense stellar remnants spiral inward and merge, producing catastrophic explosions visible across billions of light years. The galaxy contains millions of interacting binary systems at various evolutionary stages. Each represents a potential future eruption as gravitational forces drive stellar components toward ever more violent interactions. Advanced alien civilizations within binary star systems would experience regular cosmic disasters from the violent interactions of their host stars. Planetary survival would require either advanced technology to deflect stellar emissions or migration to more stable single-star systems.
Yet even all these magnificent binary eruptions appear tame compared to solitary wanderers drifting through interstellar space without any stellar companion. And so, in this vast arena of the universe, we find ourselves in the midst of a cosmic dance spanning billions of years. The approaching supernova of Betelgeuse, the slow approach of Gliese 710, energies flowing along plasma highways, all remind us how dynamic, how alive, how dangerous, yet how magnificent the universe truly is. Every night, when we lift our heads and look at the stars, we do not see merely calm points of light. We witness the cosmic wars, explosions, mergers, and rebirths that have unfolded over millions of years. The night sky may appear static, but the truth is, we are only capturing a single snapshot of the ongoing cosmic drama around us. Stars are being born, dying, and being reborn. Galaxies collide, black holes dance, and we, in the midst of this magnificent cosmic symphony, on a spiral arm of the Milky Way, on our small blue planet, are the only species striving to comprehend this entire universe. Perhaps the greatest miracle is that, amidst all this cosmic violence and chaos, life can exist, evolve, and begin to unravel the secrets of the cosmos. That truly is astonishing. It is 4 million times heavier than our Sun, and it controls the motion of 400 billion stars. Some stars are accelerated to speeds of 27 million kilometers per hour. Get ready for a journey where time stands still, space bends like a liquid, and a single star spins at insane speeds just to survive. When you look up at the night sky, you might think the stars are scattered randomly, but the truth is far more interesting. Our entire galaxy moves with clock-like precision. 400 billion stars, countless planets, and massive clouds of gas orbit around an invisible point. Our solar system is currently traveling at a speed of 830,000 kilometers per hour, around something we cannot see. This cosmic dance is completed once every 240 million years. The last time we were exactly at this point, dinosaurs were roaming the Earth. So what holds this massive spiral structure together? For centuries, astronomers thought this was caused by stars pulling on each other. Like dancers holding hands in a cosmic circle, the gravity of stars would naturally create order out of chaos. The mathematics seemed to support this. But when scientists measured how fast the stars were actually moving, they realized they were wrong. The stars at the edge of the galaxy were moving far too fast. They should have already been flung into the cold darkness of space. Something massive was hidden at the center. A gravitational force strong enough to grasp stars from 26,000 light-years away. This hidden anchor had to be millions of times heavier than the Sun. Yet telescopes saw nothing there, except an empty darkness. Our galactic center lies in the direction of the Sagittarius constellation, hidden behind thick clouds of dust that block visible light. For decades, this cosmic fog concealed the truth. We could see its effects, but we could not see the cause. Radio waves, however, were piercing through the dust clouds like X-rays cutting through flesh. In the 1970s, astronomers turned radio telescopes toward the center of the galaxy and discovered something extraordinary. A compact source was glowing with radio energy, brighter than anything else in our galaxy. They named it Sagittarius A star, marking its position with an asterisk like a warning sign. But radio waves alone could not reveal the true nature of this monster. How could it produce such intense radiation while remaining completely invisible to visible light? In 1974, astronomers Bruce Ballack and Robert Brown turned their radio telescopes toward the Sagittarius constellation. They were expecting normal cosmic interference. Instead, they found something inexplicable,
A bright radio source was emanating from the exact center of our galaxy. This was not the faint shimmer of distant stars, nor the scattered emissions of gas clouds. It was a focused beam of energy, concentrated into a region smaller than our solar system, yet outshining entire star clusters. To mark it as something unidentifiable and mysterious, they named it Sagittarius A star, using a star symbol. But the truly strange part was just beginning. When astronomers searched for the same object with visible light telescopes, they found absolutely nothing. No star, no glowing cloud, no bright disk of matter. The most powerful radio source in our galaxy had rendered itself invisible to the human eye. Radio telescopes managed to reveal complex details about this hidden object. It was approximately 20 million kilometers wide. Its radio emissions displayed structural patterns suggesting rotation and magnetic fields of unimaginable strength. Yet optical telescopes saw only the black emptiness of space.
The intensity of the radio waves suggested an enormous release of energy. Whatever was powering Sagittarius A star was producing more energy in a single second than our Sun produces in an entire year. This was not a gentle stellar fire. This was a cosmic furnace of unimaginable power. Astronomers realized they were observing something fundamentally different from any known astronomical object. Not a star, because stars emit visible light. Not a gas cloud, because the emissions were far too concentrated. Not a star cluster, because the source remained point-like even in the most powerful telescopes. As more radio observations accumulated, a disturbing picture emerged. The energy output required a central engine millions of times heavier than our Sun, compressed into a region smaller than Mercury's orbit. Only one known object in the universe could meet these impossible requirements. But proving its existence required tracking the invisible monster's gravitational grip on its nearby victims. Stars are supposed to move slowly through space, drifting like distant ships across a cosmic ocean. Their positions barely change over human lifetimes. Yet some stars near the center of our galaxy were moving like race cars on a cosmic track. In the 1990s, two teams of astronomers began monitoring infrared light coming from the galactic center. Infrared wavelengths can pierce through the dust clouds that block visible observations, finally allowing us to look into the heart of our galaxy. What they discovered shattered every assumption about stellar motion. A cluster of bright stars was orbiting empty space at tremendous speeds. These were not the gentle drifting patterns of normal stellar neighborhoods. These were violent, elongated orbits, carrying stars millions of kilometers in just months. The fastest of these stellar races became known as S2, a blue giant star following an extremely elliptical path. S2 completes a full orbit every 16 years around something our instruments cannot see. At its closest approach, this star reaches speeds of 27 million kilometers per hour. Imagine standing there during S2's closest approach. The invisible gravitational anchor would fill half your sky. Tidal forces would stretch space itself. The surface of the star would glow white-hot from the intense radiation environment. Time itself would slow down compared to the rest of the universe. Yet our telescopes saw only empty darkness at the center of S2's wild dance. Orbital mechanics told an incredible story. Something more than 4.3 million times heavier than our Sun had to exist at the exact center of these stellar orbits. The mathematics of gravity was unavoidable, locked in by centuries of Newtonian and Einsteinian physics. Yet this central mass did not occupy a region larger than our solar system. If you tried to compress 4 million suns into the volume between Earth and Pluto, normal matter would explode outward with the force of 1 billion hydrogen bombs.
No known stellar configuration could remain stable under such extreme conditions. The dancing stars revealed another crucial detail. Their orbital planes remained fixed in space, proving that the central object was not a cluster of individual stars or a dense stellar core. Perfect orbital stability pointed to a single, incredibly compact object. At its closest approach, S2 came to within just 120 astronomical units of the invisible anchor. At that distance, the star experienced gravitational forces powerful enough to bend space and time. According to Einstein's predictions, light coming from S2 was redshifted as it climbed out of the deep gravitational well. These relativistic effects provided the final proof. In the known universe, only one type of object could create such extreme gravitational conditions while remaining completely invisible to telescopes. The dancing stars had revealed the location of our galaxy's ultimate predator. How do you weigh something you cannot see, cannot touch, or directly observe? How do you measure an invisible giant hiding in the darkness 26,000 light-years away? The answer lies in the cosmic equivalent of watching a dog chase its tail. When astronomers tracked S2's complete orbit around the galactic center, they gained access to the most precise scale in the universe. Gravity never lies. The mathematics of orbital motion, perfected by Newton and expanded by Einstein, reveals the exact mass of any central object based on how smaller objects move around it. S2's orbit told an incredible story written in the language of physics. The star's elliptical path stretches from 970 astronomical units at its farthest point to just 120 astronomical units at closest approach. This extreme elongation creates a cosmic laboratory where gravitational effects are amplified to levels found nowhere else in the universe. Using these orbital measurements, astronomers calculated the central mass with extraordinary precision, 4,297,000 times the mass of our Sun, accurate to within just 12,000 solar masses. If you could somehow gather 4 million suns and compress them into a region smaller than Mercury's orbit, you would create the gravitational anchor at the heart of our galaxy. But mass alone was not enough to solve the puzzle. The size constraint provided the final piece of evidence. S2's closest approach placed strict limits on how large the central object could be. If the invisible mass had a significant radius, S2 would have collided with its surface during its orbit. S2's survival through its closest approaches meant that the central object had to be smaller than 120 astronomical units. The results led to an unavoidable conclusion. The gravitational anchor at the center of our galaxy had to be a region of space where matter is compressed so tightly that it bends space-time beyond the point of no return. The dancing stars had weighed our galaxy's central black hole with unprecedented accuracy. But seeing this invisible monster would push technology to its absolute limits. After its discovery, nearly 50 years later, Sagittarius A star remained a ghost. Astronomers could measure its radio emissions, track the stars orbiting around it, and calculate its immense mass, but they could never see the monster itself. Then, in 2022, humanity finally succeeded in capturing the first image of the black hole at the center of our galaxy. The challenge seemed impossible from the start. Black holes trap light so completely that no photon can escape their gravitational prison. You cannot photograph something that absorbs every wavelength of electromagnetic radiation. But black holes do not exist in perfect isolation. Matter falling toward the event horizon heats up to billions of degrees, burning brighter than any star before vanishing forever. This superheated material forms an accretion disk, spiraling around the black hole like water circling a cosmic drain.
The Event Horizon Telescope project combined 8 radio observatories across 4 continents, creating a virtual telescope the size of planet Earth. This global array could theoretically resolve objects as small as an orange sitting on the surface of the Moon. Despite this incredible resolution, imaging Sagittarius A star presented unique challenges. The black hole's relatively small size made it a difficult target. While the supermassive black hole in the Messier 87 galaxy weighs 6 billion times the mass of our Sun, Sagittarius A star contains only 4 million solar masses. The imaging process also had to account for our position inside the galaxy. We are looking toward the galactic center through 26,000 light-years of interstellar dust, gas clouds, and stellar radiation. The breakthrough came from combining observations taken over multiple nights. In April 2017, supercomputers spent 5 years processing the data. The final result revealed Sagittarius A star as a perfect black circular shadow surrounded by a bright orange ring of light. The shadow represents the event horizon itself, the boundary where space-time is bent so violently that nothing can escape. The image matched Einstein's predictions with striking accuracy. General relativity, developed more than a century ago, had perfectly described the appearance of an object that would not be photographed until 2022. The glowing ring showed matter heated to 10 billion degrees as it spiraled toward annihilation. Magnetic fields twisted through the plasma, creating bright hotspots racing around the black hole at nearly the speed of light. This photograph represented more than a technical achievement. For the first time in human history, we had visual confirmation that these theoretical objects truly exist in nature. The shadow cast by Sagittarius A star proved that the gravitational anchor at the center of our galaxy is indeed a region where space and time are completely broken. Most stars drift through space at comfortable speeds, covering only a few kilometers per second as they follow lazy orbits around the galactic center. But near Sagittarius A star, the normal rules of stellar motion collapse into something far more extreme. During its closest approach in May 2018, S2 held the record for the fastest confirmed orbit around any black hole. This racing star reached a speed of 7,650 kilometers per second, equivalent to 27 million kilometers per hour. At that velocity, S2 could travel from New York to Los Angeles in less than a tenth of a second. But raw speed tells only part of the incredible story. S2's orbital mechanics push the limits of what physics considers possible for normal matter. Despite experiencing gravitational forces that should tear most objects apart, the star completes its 16-year journey while maintaining its structural integrity. At its closest approach, S2 passes only 120 astronomical units from the black hole's event horizon. This distance is equivalent to roughly 18 billion kilometers, enormous until you consider the monster that S2 is orbiting. The gravitational acceleration experienced by S2 at closest approach exceeds levels found anywhere else in the known universe. Tidal forces stretch the star's structure, with the side facing the black hole pulled significantly harder than the far side. The star's velocity creates relativistic effects that become measurable with current instruments. As S2 races around Sagittarius A, its light is redshifted by the combined gravitational and Doppler effects by an amount equivalent to about 200 kilometers per second. This redshift represents light literally struggling to escape the black hole's gravitational well. Time dilation also affects S2 during its high-speed passage. Clocks on the star would run measurably slower than identical clocks in normal space. If you could somehow visit S2 during closest approach, your watch would lose several seconds compared to Earth time. Time flows like a river. steady and unchanging from our human perspective. We assume that seconds pass at the same rate everywhere in the universe, but near Sagittarius A star, time itself bends just as much as the warped space around it. Einstein's general relativity makes a startling prediction about gravity's effect on time. Strong gravitational fields literally slow the passage of time compared to weaker fields. This is not science fiction or theoretical speculation. This is measurable physics, the same effect that influences GPS satellites orbiting Earth. Near a black hole, these time dilation effects become extreme. When S2 made its closest approach to Sagittarius A star in 2018, astronomers detected the exact gravitational redshift predicted by Einstein's equations. At S2's closest approach, this time dilation produces a measurable effect. For every 1 million seconds that pass on Earth, S2 experiences about 999,999 seconds. The difference is only about 10 seconds per million, but modern instruments can detect this tiny change. Gravitational redshift becomes even more extreme closer to the event horizon. If you could somehow hover just outside the black hole's point of no return, time dilation would approach infinite values. Your seconds would stretch into hours when viewed from normal space. In the simple world of Newtonian physics, planets follow the same elliptical path over and over again. Earth's orbit around the Sun creates a perfectly closed loop repeated identically year after year for billions of years. But near Sagittarius A star, even the concept of a stable orbit turns into something far stranger. S2 never follows the same path twice. Instead, its orbit undergoes precession, meaning the entire elliptical path slowly rotates through space. Each 16-year journey around the black hole traces a slightly different route, creating a flower-like pattern known as a rosette. This orbital precession represents one of the most precise tests of Einstein's general relativity ever performed. The effect arises because space-time near Sagittarius A star is bent so severely that the usual rules of geometry no longer apply. S2's precession amounts to 12 arc-minutes per orbit, about 1/5 of a degree. This small rotation accumulates over multiple orbits, causing the star's path to draw a cosmic flower pattern over centuries of observation. The measured precession matches Einstein's predictions perfectly. When observations confirmed this prediction within the margin of measurement error, they provided strong evidence that our understanding of gravity remains correct even under extreme conditions. Most of the time, Sagittarius A star quietly sleeps at the center of our galaxy, consuming matter at a gentle rate, barely noticeable on cosmic scales. The black hole appears almost dormant. But 200 years ago, our galaxy's monsters suddenly awoke and began to feast. NASA's Imaging X-ray Polarimetry Explorer uncovered evidence of this ancient outburst by studying X-ray light reflected from gas clouds near the galactic center. These molecular clouds should have been cold and dark. Instead, they were glowing with X-ray emissions far brighter than astronomers could initially explain. The breakthrough came when scientists realized they were observing an echo from the past. The X-ray light was coming from a period of intense activity from Sagittarius A star about 200 years ago. During this outburst, the black hole increased its brightness by factors of millions. Think of this cosmic awakening like a campfire suddenly flaring when someone throws gasoline onto glowing embers. As Mozart was composing his final symphonies, the black hole erupted with energy that outshone entire star clusters. This discovery revealed that Sagittarius A's current quiet state does not represent its normal behavior over long timescales. The black hole experiences periodic feeding frenzies when large amounts of material fall under its gravitational influence.
Common sense suggests that a monster 4 million times heavier than our Sun would be a greedy cosmic predator, constantly devouring everything within reach of its gravitational claws. But Sagittarius A turns out to be surprisingly selective about its meals. Despite sitting at the center of our galaxy and having access to enormous amounts of interstellar material, the black hole consumes matter at an almost leisurely pace. Current observations suggest that Sagittarius A star accumulates roughly 1 Earth mass of material per year. This may sound like a massive appetite until you consider the scale. 1 Earth mass is equal to about 6 quadrillion kilograms, which represents less than 1% of 1/1,000,000th of the black hole's total mass. The reason for this surprisingly gentle behavior lies in the physics of accretion near black holes. As matter approaches the event horizon, it does not simply fall straight in like water down a drain. Instead, the material must lose both energy and angular momentum before completing its final plunge. Research using NASA's Chandra X-ray Observatory revealed that less than 1% of the material initially captured by Sagittarius A star's gravity actually crosses the event horizon. The remaining 99% is heated to extreme temperatures and flung back into space through powerful outflows. Think of this like a cosmic filtration system. The black hole captures enormous amounts of material from stellar winds and interstellar gas clouds, but its own feeding process becomes so violent that most of the matter is blown away before it ever reaches the point of no return. From our perspective on Earth, the Milky Way appears as a faint band of light stretching across the night sky. This gentle arc seems permanent and unchanging, yet the delicate spiral structure of our galaxy exists only because of the massive gravitational anchor at its center. Sagittarius A star does not merely passively occupy the galactic center. The black hole actively shapes the distribution of stars, gas clouds, and dark matter across hundreds of thousands of light years. Like a cosmic sculptor working with material on unimaginable scales, it carves the elegant spiral arms of our galaxy through pure gravitational influence. The process begins with density waves propagating outward from the galactic center. These gravitational ripples move at different speeds than the orbital motion of stars, creating regions where stellar material is compressed into the bright spiral patterns we observe. The mass of the black hole determines many fundamental properties of our galaxy. Astronomers have discovered a tight correlation between the masses of supermassive black holes and the stellar bulges of their host galaxies. If Sagittarius A star were significantly more or less massive, our entire galaxy would have evolved differently. A lighter black hole could have allowed the Milky Way to become a dwarf galaxy with an irregular structure. A heavier central mass could have created a more compact elliptical galaxy with very little ongoing star formation. The region around Sagittarius A star may appear like a cosmic wasteland, but the galactic center is actually teeming with exotic companions that make it one of the most crowded neighborhoods in our galaxy. Within just 3 light-years of the central black hole, astronomers have detected thousands of individual stellar objects. These are not ordinary stars following safe orbits in the galactic suburbs. They are cosmic extremophiles that have managed to survive in the most violent environment our galaxy has to offer. The most striking discovery came in November 2004, when astronomers detected GCR S13e, an intermediate-mass black hole containing 1,300 times the mass of our Sun. This smaller monster orbits Sagittarius A star at a distance of 3 light-years, accompanied by a cluster of 7 massive stars. Most astronomical objects change slowly on human timescales. Stars burn steadily for millions or billions of years. Planets follow predictable orbits. But Sagittarius A star occasionally produces bursts of energy that transform it from a sleeping giant into a blazing beacon in just a few hours. On May 13, 2019, astronomers using the Keck Observatory witnessed something extraordinary. The black hole suddenly became 75 times brighter than normal at infrared wavelengths, producing the most dramatic flare ever recorded from our galactic center. The increase in brightness happened so rapidly that astronomers initially suspected an equipment malfunction. Infrared detectors recorded Sagittarius A star's brightness rising from its usual suppressed glow to intense brilliance in less than 2 hours. Astronomers suspect that the flare was caused by a close encounter between Sagittarius A star and another astronomical object. The leading candidate is a massive gas cloud known as G2, which passed near the black hole during the brightening event. Photographing a black hole seems like the ultimate contradiction. These cosmic monsters trap light so completely that no photon can ever escape their gravitational prison. Yet darkness itself can cast a shadow. When the Event Horizon Telescope captured its historic image in 2022, it revealed Sagittarius A star as a bright orange ring of light surrounding a perfectly circular shadow. The shadow represents the event horizon itself, the boundary where space-time is bent so severely that light cannot escape. This shadow measures roughly 20 million kilometers in diameter. Yet, from our distance of 26,000 light-years, this enormous structure appears smaller than an orange sitting on the surface of the moon. The glowing ring around the shadow reveals matter heated to temperatures exceeding 10 billion degrees. This superheated plasma spirals around the black hole at nearly the speed of light. Imagine standing at the edge of a cliff. You can step back, but one step forward commits you to an irreversible fall. Yet, the event horizon around Sagittarius A star creates something far more absolute than any physical cliff. The event horizon represents the boundary in space where the escape velocity equals the speed of light. Inside this spherical surface, nothing can move fast enough to overcome the black hole's gravitational pull. For Sagittarius A star, this point of no return spans a diameter of 20 million kilometers. If you could replace our Sun with this event horizon, the boundary would extend beyond the orbit of Venus and nearly reach Earth. Crossing the event horizon creates the ultimate one-way journey. Inside, every possible future path leads inevitably toward the central singularity. You could fire your rocket engines at maximum power, but instead of escaping, you would only reach the center a little faster. Falling toward any massive object creates tidal forces. The moon's gravity pulls Earth's oceans slightly more strongly than the solid ground beneath them. But near Sagittarius A star, these same tidal forces turn into instruments of cosmic destruction. The process begins subtly as you approach the black hole feet first. Gravity pulls on your feet slightly more strongly than on your head. This combination of vertical stretching and horizontal compression transforms objects into long, thin shapes resembling strands of spaghetti. Physicists call this terrifying process spaghettification. The mathematics of tidal forces depends critically on the mass of the black hole. For stellar mass black holes, only a few times heavier than our Sun, spaghettification becomes lethal long before reaching the event horizon. Sagittarius A star presents a strikingly different scenario because the event horizons of supermassive black holes lie far from their centers. At the point of no return, the tidal gradient remains relatively gentle. You could cross the event horizon of Sagittarius A star without experiencing immediately fatal tidal forces. Reality near a black hole is entirely dependent on perspective. The same physical process can appear completely different to observers in different reference frames. Imagine watching someone fall into a black hole from a safe distance. As they approach the event horizon, time dilation causes you to see them slow down dramatically. From your external perspective, the falling person never actually reaches the event horizon. Instead, they appear frozen at the boundary. However, from the perspective of the falling person, nothing unusual happens during the crossing. Their clock continues to tick at a normal rate. They cross the event horizon in finite time and continue falling toward the singularity. Every particle carries information, yet black holes appear to completely destroy information, creating one of the deepest puzzles in modern physics. When matter falls into Sagittarius A, it carries detailed information about its structure, composition, and quantum state. Classical physics assumed that this information was simply crushed at the central singularity and lost forever. However, quantum mechanics tells a different story. In the 1970s, Stephen Hawking discovered that black holes actually evaporate through quantum effects near the event horizon. Virtual particle pairs constantly appear near the boundary, with one particle falling inward while the other escapes as Hawking radiation. This Hawking radiation causes black holes to slowly evaporate like cosmic ice cubes. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes glow hotter than larger ones. With 4 million solar masses, Sagittarius A has a Hawking temperature of roughly 1/15 trillionth of a degree. This makes it colder than the cosmic microwave background radiation left over from the Big Bang. The timescales exceed human comprehension. For Sagittarius A to completely evaporate through Hawking radiation would require approximately 10 to the power of 97 years. This duration exceeds the current age of the universe by quadrillions of times. For most of this evaporation process, the black hole will remain almost unchanged. The real fireworks begin during the final moments, when the remaining mass drops to just a few solar masses. The final second of Sagittarius A's existence will release energy equivalent to millions of hydrogen bombs detonating at once. All the mass that has fallen into the black hole over cosmic history will be converted into pure energy and released in this ultimate cosmic firework. The distant future belongs to black holes. When star formation ends and existing stars burn out, these cosmic monsters will become the dominant objects in a cold, dark universe. But this growth phase cannot continue forever. Eventually, even the largest supermassive black holes will begin to shrink through Hawking radiation, slowly returning their accumulated mass energy back to the universe. Trillions of years into the future, when the last stars have faded and galaxies have dimmed into darkness, Sagittarius A will still be growing. But eventually, the universe's final destiny will arrive. The monster that anchors our galaxy and shaped the cosmic neighborhood where Earth was formed will give back the mass it borrowed to the universe. The story of Sagittarius A represents both the ultimate triumph of gravity and its final defeat by the quantum nature of space-time. Imagine light coming from stars that died before Earth even existed, racing towards you at a speed exceeding 1 billion kilometers per hour. You think you can estimate its size, but everything you know about scale will most likely be wrong. Beyond neutron stars spinning faster than mixer blades, through cosmic filaments stretching 1 billion light-years, and toward regions where space itself was created faster than light, we are about to embark on a journey. If you're ready for your mind to be confused by the true scale of existence, hit the like button, because what's coming next will change how you see everything. You think the Earth is massive because it takes hours to travel from one end to the other. You think the ground beneath your feet is solid and permanent. But here is the truth that will shatter all your beliefs about scale. The Earth looks enormous to us because we experience it step by step. Walking from your home to the grocery store feels like a journey. Crossing your state from end to end takes hours. Flying to another continent takes an entire day. We build our entire understanding of size based on these human-scale references. But compared to what truly exists out there, the Earth is smaller than a speck of dust floating inside a cathedral. If you could shrink everything that exists, the Earth would become invisible to the naked eye before you even left your own neighborhood in space. The Moon, which looks small enough to cover with your thumb, is actually 384,000 kilometers away. That's like lining up 10 Earths end to end, and yet you still can't reach our closest neighbor. Your brain may not be able to grasp what this really means. Evolution did not equip us to understand distances measured in millions or billions. When someone says a billion, your brain automatically treats it the same way as a million. But the difference is astonishing. 1 million seconds equals 11.5 days. 1 billion seconds equals 32 years. If the Earth were a marble, our entire solar system would still be smaller than a single city block. And our solar system itself is just one point in a galaxy containing 400 billion stars. You will travel beyond everything your mind can comfortably contain. You will discover objects so dense that a teaspoon of their material would weigh as much as Mount Everest. You will witness collisions that produce more energy in 1 second than our sun will generate in 1 million years. You will encounter structures so vast that light takes longer to cross them than the entire duration of human existence. The big things in your everyday life will become completely meaningless compared to what truly exists out there. The Earth's atmosphere is trying to crush you with the weight of an elephant. Every square centimeter of your body is currently experiencing about 1 kilogram of air pressure. But this gas blanket that keeps you alive extends only a few tens of kilometers above your head. Space officially begins 100 kilometers above sea level. If you could stack average-sized humans on top of one another, you would need 59,520 people to build a tower reaching the edge of space. Most commercial airplanes cruise at only 10 to 11 kilometers in altitude. Even at that height, without pressurization, you would die within 15 seconds. And yet, you would still be only 1/10 of the way to space. Mount Everest rises just 8.8 kilometers. To reach space, you would need to stack 11 Everests on top of each other. If the Earth were shrunk to the size of a basketball, its atmosphere would be thinner than a sheet of paper wrapped around it. Every breath you have ever taken, every cloud you have seen, every bird that has ever flown, exists within this incredibly thin shell surrounding our planet. The International Space Station orbits 400 kilometers above Earth. The astronauts up there aren't floating because there is no gravity. They are falling around the Earth at 28,000 kilometers per hour. The space station, which seems impossibly far away, actually orbits closer to Earth's surface than the distance between New York and Washington, D.C. If you could drive straight up at highway speed, you would reach it in less than 3 hours. And yet, this tiny step represents humanity's greatest achievement in space travel. In all of human history, only about 600 people have traveled that far. Light from the sun hits your face 8 minutes and 20 seconds after leaving the surface of our star. In those 8 minutes, light travels 150 million kilometers through empty space. But here's the part that will melt your brain. In that same amount of time, light could circle Earth's equator 7 times. Our star is so massive that even light, the fastest thing in the universe, needs more than 4.5 seconds to cross from one side to the other. The sun could swallow more than 1 million Earths and still have room left. The sun contains 99.86% of all the mass in our solar system. Everything else combined makes up just 0.14%. If the solar system were a giant pizza, the sun would be almost everything, with only a few tiny crumbs scattered around the edges.
The Sun's surface temperature reaches 5,500 degrees. That's hot enough to vaporize any material known to exist on Earth. The Sun's core burns at 15 million degrees. Every second, the Sun converts 4 million tons of matter directly into pure energy. This process has been happening for 4.6 billion years, and it will continue for another 5 billion years. Yet despite this incredible power output, the Sun is actually quite average. Astronomers classify it as a yellow dwarf star. Even within our own galaxy, there are stars that make our Sun look like a birthday candle. Some stars burn so intensely that instead of a 10 billion year lifespan, they consume themselves in just a few million years. The Sun is so far away that it appears as only a small disk in our sky. And yet, if you look at it directly, it is bright enough to permanently blind you. This average-sized star, sitting 150 million kilometers away, completely dominates our planet's energy budget. Without the Sun's light, Earth would become a frozen rock with surface temperatures hundreds of degrees below zero. Pluto sits in endless darkness at the frozen edge of everything you call home. This distant world marks what most people imagine to be the edge of the solar system. But Pluto isn't even close to the real edge. Pluto orbits the Sun at an average distance of 5.9 billion kilometers. Light from the Sun takes more than 5 hours to reach it. Temperatures there never rise above -225 degrees. Pluto represents only the inner boundary of our solar system's true edge. Beyond it lies the Kuiper Belt, and even farther out, the Oort cloud. The Oort cloud extends 50,000 times farther from the Sun than Earth does. If you could shrink our entire solar system to the size of a grain of sand, the nearest star would still be 1.5 kilometers away. Our fastest spacecraft, Voyager 1, was launched in 1977 and is still moving away from the Sun at 61,000 kilometers per hour. After 47 years of uninterrupted flight, it has only barely left our solar system. It will not come close to another star for 40,000 years. Even at the speed of light, reaching our nearest stellar neighbor would take 4 years and 4 months. Interstellar space contains almost nothing. In the emptiest regions between star systems, you might find 1 hydrogen atom per cubic meter. Earth's atmosphere contains trillions upon trillions of atoms in the same volume. This emptiness stretches in every direction across distances that would take lifetimes to cross, even at the speed of light. Our galaxy is currently eating other galaxies. The Milky Way slowly devours smaller galaxy groups, stretching them into streams of stars wrapped around us like cosmic spaghetti. This process has been happening for billions of years. The Milky Way contains between 200 and 400 billion stars. Each one is a sun, potentially hosting its own family of planets. If you could count 1 star per second, it would take more than 12,000 years to count them all. But the truly mind-blowing part is the distance between them. Our galaxy measures 100,000 light-years from edge to edge. Light takes 100,000 years to cross from one side to the other. Voyager 1 would need more than 1.7 billion years to make the same journey. By then, the Sun would have burned out, Earth would be gone, and the galaxy itself would have completely reshaped. Our entire solar system orbits the galactic center at a speed of 828,000 kilometers per hour. Even at this incredible speed, completing a single orbit still takes 230 million years. Dinosaurs lived and died during just the last quarter of our orbit. At the center of our galaxy lies a supermassive black hole called Sagittarius A star. This monster contains 4 million solar masses compressed into a region smaller than Mercury's orbit. Stars near the galactic center orbit this black hole so fast that they complete a full orbit in just 16 years. These stars experience such extreme gravity that time itself flows more slowly for them compared to us. A star called UY Scuti is so large that if you placed it where our Sun is, it would swallow Mercury, Venus, Earth, and Mars, and extend beyond the orbit of Jupiter. It would take 9 hours for light to travel around the circumference of this monster. If you could drive around its equator at highway speed, the journey would take 9 million years. UY Scuti belongs to the class of red supergiants. It represents the final stage in the lives of the most massive stars. When a star contains more than 25 times the mass of our Sun, it consumes its nuclear fuel at an incredible rate. While our Sun will burn steadily for 10 billion years, UY Scuti will exist for only about 10 million years in total. Despite being 1.7 billion times larger in volume than our Sun, it contains only about 30 times more mass. That means the star is incredibly sparse. Its outer atmosphere is so thin that it is essentially a vacuum. But UY Scuti isn't even close to the most massive stars we know. Stars in the R136 cluster contain up to 300 times the mass of our Sun compressed into much smaller volumes. They burn so hot and bright that they hurl their outer layers into space, with stellar winds moving thousands of kilometers per second. When UY Scuti eventually dies, it will likely explode as a supernova, visible from Earth in broad daylight. Despite being thousands of light years away, the explosion will outshine our entire galaxy for several weeks. A neutron star called PSR J17482446e spins 716 times per second. In the time it takes you to blink once, this stellar corpse completes more than 200 full rotations. Its equator moves at nearly 160 million kilometers per hour. Any faster, and centrifugal forces would tear the star apart. Neutron stars represent what happens when the core of a massive star collapses under its own gravity. In less than 1 second, a region the size of Earth is crushed into a sphere just 19 kilometers wide. The collapse is so violent that protons and electrons are forced together, forming neutrons.
A neutron star contains more mass than our Sun, compressed into a volume smaller than Manhattan. The gravity at its surface is 200 billion times stronger than Earth's gravity. A single teaspoon of neutron star material would weigh 6 billion tons on Earth, more than all the cars, trucks, and buses on this planet combined. The magnetic field around a neutron star is 1 trillion times stronger than Earth's magnetic field. Some neutron stars are even more extreme. Magnetars have magnetic fields 1,000 times stronger than normal neutron stars. These fields are so intense that they would wipe every credit card on Earth from a distance of 160,000 kilometers. When two neutron stars spiral toward each other, they create kilonova explosions that forge gold, platinum, and uranium. Every gold ring, every platinum catalyst, every uranium atom on Earth was created inside these cosmic collisions billions of years ago. On August 17, 2017, gravitational wave detectors felt space itself vibrate. Two neutron stars collided 130 million light-years away. The merger, known as GW170817, lasted just 100 seconds, but released more energy than our Sun will produce in its entire 10 billion-year lifetime. Even though the collision occurred in another galaxy, it created an explosion called a kilonova that was visible to amateur astronomers. When two neutron stars merge, they create conditions found nowhere else in the universe. Temperatures reach 100 billion degrees. The collision hurled pure heavy elements equal to about 50 Earth masses into space at thousands of kilometers per second.
Dark matter outweighs all the stars, planets, gas, and dust in the universe by a ratio of 5 to 1. Every atom in your body, every grain of sand on Earth, every star in the night sky represents only 16% of all existing matter. The remaining 84% is completely invisible and interacts with normal matter only through gravity. We know dark matter exists because we can see its gravitational effects on everything. Galaxies spin too fast to hold themselves together using visible matter alone. Right now, billions of dark matter particles are flowing through your body without interacting with a single atom. Despite decades of searching with increasingly sensitive instruments, scientists have still not directly detected a single dark matter particle. The leading theory suggests that dark matter is made of particles created in the first moments after the Big Bang, but with properties completely different from normal matter.
The Milky Way is trapped inside a spherical prison of dark matter that extends 3 times farther than the visible edge of our galaxy. This invisible halo contains 10 times more mass than all the stars, gas, and dust we can observe. Without this dark matter cage, our galaxy would have fallen apart billions of years ago. Dark energy is tearing the universe apart at an accelerating rate. This mysterious force makes up 68% of everything that exists, and yet we have no idea what it actually is. Dark energy behaves like anti-gravity, causing space itself to expand faster and faster. 5 billion years ago, dark energy overcame gravity and began accelerating the expansion of the universe. Now, dark energy dominates, and the rate of expansion increases every day. The universe will expand forever, becoming colder and emptier with each passing billion years. On small scales, dark energy has no effect at all, but on the largest scales, dark energy rules everything. In the distant future, dark energy will create a lonely universe. Every gravitationally bound group of galaxies will be isolated inside its own bubble of expanding space. Stars will fade, black holes will evaporate, and the universe will drift toward maximum entropy. A supermassive black hole called 3C273 shines with the light of 1,000 Milky Way galaxies. Smaller than our entire solar system, this monster sits at the heart of a distant galaxy, devouring stars and gas at such a furious rate that it outshines every object in its cosmic neighborhood. The energy it releases in 1 second equals what our sun produces in 10 million years. Quasars represent supermassive black holes in their most violent feeding stages. When galaxies collide or merge, huge amounts of gas are funneled into the central black hole. This material forms a superheated accretion disk that shines brighter than anything else in the universe. The brightest quasar we have discovered shines with the luminosity of 40 trillion suns. This single object, fed by a black hole 20 billion times the mass of our sun, releases more energy in 1 second than would be produced by merging 400 billion stars. It is so bright that we can see it from more than 12 billion light-years away. Quasars also launch material jets at 99.9% the speed of light. These jets extend millions of light-years beyond their host galaxies. The closest known quasar is 3.2 billion light-years away from Earth. Even at the speed of light, the journey would take 3.2 billion years. The farthest quasar, J0313-1806, existed when the universe was only 670 million years old. Its light has been traveling toward us for more than 13 billion years. Cosmic expansion has carried that quasar to a distance of more than 46 billion light-years from us today. At such vast distances, we are not only looking into space, we are looking into the distant past. When we study the farthest objects, astronomy becomes archaeology.
As quasar light travels across cosmic distances, it passes through gas and dust clouds that leave absorption fingerprints in its spectrum. These absorption lines map the distribution of matter across the universe like a cosmic barcode. The vacuum of space contains dark energy that outweighs every star, planet, gas cloud, and black hole in the observable universe by more than a factor of 2. This invisible energy fills every cubic centimeter of empty space. Dark energy makes up 68% of the universe's total mass energy content. Dark energy behaves like a cosmological constant, providing a repulsive force that opposes gravity on large scales. The acceleration caused by dark energy began to dominate cosmic evolution about 5 billion years ago. The local group of galaxies spans 10 million light-years and contains over 80 individual galaxies, yet it occupies less than 1% of the volume of a typical cosmic void. Cosmic voids represent the largest structures in the universe. The largest known void, the Boötes void, is 330 million light-years wide and contains almost no galaxies. The boundaries of voids are defined by galaxy sheets and filaments that form the cosmic web. These structures contain most of the ordinary matter in the universe, organized into networks spanning hundreds of millions of light-years. Galaxy clusters form where multiple filaments intersect. Cosmic filaments stretch for hundreds of millions of light-years, forming the largest structural elements in the universe. These dark matter and gas strands connect galaxy clusters like a vast three-dimensional web. The filament containing our local group extends for over 500 million light-years. Individual filaments can contain the mass equivalent of 10 trillion suns stretched along their length. Despite their enormous size, filaments are surprisingly thin, typically only a few million light-years wide. This creates structures with aspect ratios more extreme than a human hair compared to its length. The Hercules Corona Borealis Great Wall stretches 10 billion light-years across space, making it the largest structure known in the universe. This cosmic wall contains billions of galaxies, and light would take 10 billion years to cross from one end to the other. The Great Wall is so massive that it challenges our understanding of cosmic structure formation. Theoretical models predict that structures this large should not exist because gravity has not had enough time since the Big Bang to pull them together. If the universe is finite and curved back on itself, we may be observing the same cosmic objects multiple times without realizing it. Light from a single galaxy could travel around the curvature of the universe and reach us from different directions, creating duplicate images separated by billions of years. The cosmic microwave background represents the farthest edge of the observable universe. It is the glowing shell of ancient light, marking the moment when atoms first formed and the universe became transparent. This radiation has been traveling toward us for 13.8 billion years, carrying information from when the universe was only 380,000 years old. The tiny temperature variations in this radiation, only a few millionths of a degree, represent the seeds that would eventually grow into galaxies, stars, and planets. Every structure we see today began as microscopic fluctuations in this ancient light. This ancient radiation fills the entire universe uniformly. Every cubic centimeter of empty space contains about 400 cosmic microwave background photons left over from the Big Bang. These photons have been redshifted by cosmic expansion from visible light to microwave frequencies. The observable universe is only a small bubble inside a cosmos that potentially extends infinitely in all directions. We can only see light that has had time to reach us since the Big Bang, creating a spherical boundary 46 billion light-years away. Cosmic inflation theory suggests that the entire universe is far larger than the part we can observe. In a fraction of a second after the Big Bang, space expanded exponentially. Conservative estimates suggest the entire universe is at least 10 to the 23rd times larger than the observable portion. An infinite universe would contain infinite copies of everything, including you, Earth, and exact duplicates of our entire observable region. The laws of probability guarantee that every possible arrangement of matter will occur infinitely many times across infinite space. Cosmic inflation expanded a region smaller than a proton into something larger than a grapefruit just 10 to the negative 35 seconds after the Big Bang. This exponential expansion increased the size of the universe by at least a factor of 10 to the 26th, turning quantum-scale fluctuations into the seeds of galaxies. If inflation is correct, there is a striking answer to the question, how big is the universe? It is either impossibly larger than what we can observe, or literally infinite. The universe started smaller than the period at the end of this sentence, then grew to be far larger than anything you can imagine.
The words you are reading right now, this screen, this planet, were once a point so small it couldn't be seen. Then, in an instant explosion, space itself expanded and over billions of years evolved into the cosmic scenery we see today. Every atom in your body was forged in the heart of a star. The oxygen you breathe, the calcium in your bones, the iron in your blood were all created inside stars that died billions of years ago. You are literally stardust. And here is the most striking truth. Despite all this incredible scale, all these cosmic time frames, all these unimaginable distances, we are still here, now, living this moment. We exist as an island of consciousness in an ocean of infinity. Does your sense of scale mean something different now? We can discuss it in the comments. Good night.
Everything we know about the universe's beginning might be a beautiful lie. The James Webb Space Telescope was supposed to be our victory lap, confirming decades of carefully constructed theories about cosmic birth. Instead, it's showing us a universe that plays by completely different rules. What if I told you that the most expensive scientific instrument ever built accidentally proved our cosmic origin story wrong? Stay with me, because what we're about to explore will challenge everything you learned in school. Let's dive in. 30 years of planning, $10 billion, all of it invested in building the most sophisticated eye humanity has ever pointed at the stars. The James Webb Space Telescope wasn't designed to surprise anyone. Its mission was simple: look back through time and watch the universe's baby photos. Scientists thought they had it all figured out. They knew exactly what they would find in the cosmic nursery: tiny, clumsy galaxies taking their first wobbly steps, primitive collections of stars barely holding together, the cosmic equivalent of watching toddlers learn to walk. But what they actually found was something else entirely. Imagine expecting baby pictures and instead discovering portraits of Olympic athletes in their prime. That's the shock we're dealing with.
These weren't infant galaxies. They were massive, sophisticated systems burning with the brilliance of billions of stars. They were organized, mature, and completely structured. And they existed when the universe was supposedly still figuring out how to form its first stars. Here's where it gets wild. Let's say you plant a tree today. Standard biology tells you it'll take decades to reach full height. Now imagine returning next week and finding a giant sequoia standing there, fully mature. That's essentially what Webb showed us in space. Galaxies that our models say need billions of years to develop were already there, completely formed, just 600 million years after everything began. The numbers don't just contradict our theories, they demolish them. Webb's infrared vision can see through cosmic dust and darkness like nothing we've ever had before. Its mirror spans 21 feet across, catching light that's been traveling longer than any photon we've ever captured. This gives us a literal time machine, showing us the universe when it was barely 3% of its current age. We expected infancy, we got impossibility. Scientists are calling it the crisis in cosmology, though that's putting it mildly. Research teams worldwide are scrambling to explain observations that shouldn't exist according to our best physics. The foundation of our cosmic understanding is cracking. Every image Webb sends back forces us to face an uncomfortable reality. That beautiful story we've been telling about cosmic evolution, the one that won Nobel Prizes and filled every textbook, it might be fundamentally wrong from page one. Webb was built to be the ultimate validator. Instead, it became the ultimate challenger, revealing a universe that refuses to follow any rules we've established. And this is just scratching the surface of what it found.
Think about galaxy formation like constructing a house. First, you need a foundation, the invisible dark matter that provides structural support. Then you need gas that cools down enough to start forming stars. Finally, those stars need time to live, die, and spread the heavier elements that enable complex chemistry. This entire process should take billions of years. These 6 objects Webb found seem to skip most of these steps entirely. They appeared fully constructed when the universe should barely have cooled from its initial explosion. Someone hit fast forward on cosmic evolution, compressing billions of years into an eye blink. But wait until you see how massive these impossible galaxies really are. One of the galaxies Webb discovered weighs more than 100 billion suns. Our own Milky Way, which has had over 13 billion years to accumulate material, contains about 60 billion solar masses. These early universe monsters achieved even greater mass in a fraction of that time. The Milky Way is like an ancient oak that's grown slowly over centuries. These early galaxies are like finding fully grown redwoods in a garden that was planted yesterday. The comparison reveals just how impossible these observations are. Mike Boylan-Colchin from the University of Texas ran the calculations and reached a troubling conclusion. If these measurements are accurate, we're entering completely uncharted territory. These galaxies are so massive, they require either fundamental changes to our understanding of galaxy formation or fundamental changes to our understanding of the universe itself.
Consider the absurdity here. The most massive early galaxies contain more stellar material than galaxies that have had billions of additional years to grow. It's discovering that a toddler weighs more than an adult. The timeline doesn't work with any known process. These galaxies exist when the universe was only 3% of its current age. Imagine compressing your entire adult life into a single year and trying to accomplish everything you've learned and built in that impossibly short window. That's what these galaxies achieved on a cosmic scale. Current galaxy formation models predict you need at least 2 billion years under perfect conditions to build such massive systems. These galaxies did it in less than 700 million years, and they did it in the hostile chaos of the early universe. If galaxies could grow this massive this quickly, then our entire cosmic timeline needs to be thrown out and rebuilt from scratch. The mass problem gets even stranger when you examine how efficiently these early galaxies converted raw materials into stars. For these massive early galaxies to exist, they'd need to convert nearly 100% of their available gas into stars. That's the absolute theoretical maximum of physical possibility. It's demanding that a factory achieve perfect efficiency with zero waste, using every single atom to create its product.
In today's universe, galaxies typically convert only about 10% of their gas into stars. The other 90% gets blown away by stellar winds, supernova explosions, and various energetic processes. Think of trying to build a campfire in a hurricane. Most of your fuel scatters before it can ignite.
This 10% efficiency isn't a flaw. It's a fundamental consequence of the physics governing star formation. When massive stars die in supernova explosions, they blast energy and material into space, disrupting nearby gas clouds and preventing new star formation. This creates a natural speed limit on how efficiently galaxies can make stars. Early galaxies would need to overcome all these barriers. They'd need stellar winds that somehow don't scatter gas, supernovae that don't disrupt anything, a universe operating by completely different rules than what we see today. Achieving near-perfect efficiency sits right at the theoretical edge of what's possible. These early galaxies somehow found a way to violate one of the most fundamental limitations in cosmic engineering. Boylan-Kolchin describes this efficiency requirement as technically possible only if everything in the early universe worked very differently from our expectations. Every process that normally prevents star formation would need to be suppressed or eliminated entirely. Imagine filling a bucket while someone shoots holes in the bottom. Normal galaxies have those holes, losing most of their gas before it can form stars. These early galaxies would need buckets with no holes whatsoever. The efficiency problem reveals we're dealing with galaxies that operated under fundamentally different physical laws than anything we observe elsewhere in the universe. And the mystery deepens when we discover what lurks at their centers. Supermassive black holes weighing billions of suns sit at the heart of these impossible early galaxies. Webb detected these cosmic monsters actively feeding when the universe was less than 1 billion years old. According to our understanding, these objects represent an even greater impossibility than the galaxies themselves. Black holes grow by eating matter, but there's a fundamental speed limit called the Eddington limit. Imagine drinking from a fire hose. There's only so much you can swallow before the pressure pushes everything away. That's how black holes work. The radiation from their feeding eventually pushes away their food. Growing from stellar mass black holes, formed when massive stars collapse, to the billion solar mass monsters Webb discovered should take several billion years under ideal conditions. These black holes accomplished it in less than 1 billion years, in a universe far more hostile to rapid growth.
It's like finding a fully grown elephant where only mice should exist. The growth timeline simply doesn't match the available time. These supermassive black holes would need to feed continuously at maximum rate from the moment the first stars formed. No breaks, no starvation periods, no competition from other cosmic processes. Webb discovered one quasar containing a black hole that weighs 10 billion suns, making it the most massive black hole known in the early universe. This cosmic giant exists when the universe was still an infant. The black hole alone contains more mass than most entire galaxies from that era. The presence of these early supermassive black holes creates a chicken and egg problem. Did black holes form first and help create galaxies? Or did galaxies form first and create conditions for rapid black hole growth? Either scenario requires processes operating much faster than anything we observe now. These black holes aren't sitting quietly either. They're actively gorging on material, blazing as quasars, some of the brightest objects in the universe. Their feeding generates so much energy it should blow away the gas needed for continued star formation. Yet somehow, both processes continue simultaneously. The discovery suggests either our black hole formation models are fundamentally broken, or the early universe operated under very different conditions than we've assumed. But supermassive black holes are just the beginning. Even stranger objects lurk in the deepest reaches of space and time. In Webb's deepest images, astronomers discovered 9 sources of brilliant blue ultraviolet light blazing from an epoch when stars shouldn't exist yet. These mysterious objects shine from when the universe was only 100 million years old. At this cosmic moment, the universe should be dark and empty, still recovering from its violent birth. These light sources represent the deepest observations ever made, pushing back the boundaries of observable time by several factors beyond previous records. Picture seeing individual candle flames from miles away on the darkest night imaginable. That's what Webb achieved. 6 of these objects exist when the universe was 200 million years old. 3 others shine from even earlier, when the universe was 100 million years old, an era so early that conventional star formation shouldn't be possible. The universe was still too hot and chaotic for gas to cool and collapse into stellar nurseries.
Pablo Pérez González from the Centro de Astrobiología in Madrid led the team that discovered these impossible light sources. His research pushes cosmic observation to absolute limits, revealing a universe much more active in its earliest moments than any model predicted. The blue ultraviolet light these objects emit is exactly what astronomers expect from massive, hot, young stars. This creates a profound puzzle. How did these stars form so early when the physics should have prevented their existence? It's like discovering a bonfire in a room that's supposedly too wet and cold for any flame to ignite. Some of these light sources appear point-like, suggesting they might be something even more exotic. About 30% have characteristics consistent with primordial black holes, theoretical objects that could have formed in the universe's first moments rather than growing slowly from stellar collapse. If these are primordial black holes, they represent a completely different pathway for creating massive objects. Instead of waiting for stars to form, live, die, and collapse, these objects could have existed from nearly the beginning, providing ready-made seeds for rapid galaxy formation. Finding light from when the universe was less than 1% of its current age means we're seeing a cosmos when atoms had barely formed. The universe was still emerging from the opaque fog following the Big Bang. Finding organized light sources at this epoch is like discovering a symphony orchestra performing in what should be an empty hall. Current cosmology models predict forming massive galaxies requires at least 2 billion years under the most favorable conditions. Webb structures accomplished this in less than 700 million years during the most challenging period in cosmic history. It's like watching someone complete a marathon in sprinting time. The 2 billion year minimum comes from fundamental physics governing matter's behavior in the expanding universe. First, dark matter needs time to clump together, creating invisible scaffolding that guides normal matter. Then, gas must cool from scorching temperatures down to levels where it can form stars. Finally, those first stars need time to live, die, and enrich space with heavier elements necessary for complex chemistry. Each step has its own built-in timeline that can't be significantly accelerated without violating known physics. Dark matter clumping follows gravitational dynamics operating at predictable speeds. Gas cooling depends on thermodynamics and universal expansion. Stellar evolution proceeds according to nuclear fusion rates, among the most precisely understood processes in physics.
Think of galaxy formation like cooking a complex meal, requiring multiple sequential steps. You can't skip preparation. You can't rush cooking. You can't combine certain steps without ruining everything. The universe appears to have somehow prepared this cosmic feast in a fraction of the recipe's required time. The 700 million year window Webb's galaxies had becomes even more constraining considering the hostile early universe conditions. Gas temperatures were much hotter, making star formation harder. The universe was denser, creating more turbulent conditions. Heavy elements were virtually non-existent,
limiting the types of stars that could form. Under these challenging conditions, galaxy formation should have taken longer than the 2 billion year minimum, perhaps 3 or 4 billion years. Instead, Webb discovered fully formed massive galaxies that somehow overcame every obstacle. Cosmologist Catherine Hamans explained the fundamental problem. Our cosmological theory predicts galaxies of this mass should take much longer to assemble. The timeline mismatch isn't a small discrepancy explainable by measurement error. It represents a factor of 3 difference between prediction and observation. If the universe could form such massive structures so quickly in its early epochs, our entire understanding of cosmic evolution needs reconsideration. This temporal impossibility becomes even more puzzling when examining other measurements that refuse to align with our cosmic timeline. The universe is expanding, but astronomers can't agree on how fast. This disagreement, known as the Hubble tension, represents one of the most significant crises in modern cosmology. Different measurement methods yield expansion rates differing enough to suggest something fundamental is wrong with our understanding. When astronomers measure expansion using nearby supernovae and local cosmic objects, they get about 73 kilometers per second per megaparsec. When they calculate it using cosmic microwave background radiation from the early universe, they get about 67. This 6-unit difference might sound small, but it's far too large to be measurement error. Think of 2 rulers consistently giving different measurements for the same object. One shows 10 inches, the other shows 11. The difference is systematic and significant enough to suggest something is fundamentally wrong.
The Hubble tension has persisted for over a decade despite increasingly precise measurements from multiple independent teams. Webb's observations have now confirmed and reinforced the higher expansion rate, ruling out the possibility that previous measurements were biased by errors. Adam Rees, who won the Nobel Prize for discovering the universe's accelerating expansion, led the latest Webb study verifying the higher expansion rate. His team used the largest Webb data sample from the telescope's first 2 years to confirm the local universe really is expanding faster than early universe measurements predict. This expansion rate disagreement creates a temporal paradox, compounding the timeline problems Webb revealed. If the universe expanded faster in its early epoch than we thought, it would provide more time for structure formation. However, it would also require new physics to explain why the expansion rate differed then versus now. The Hubble tension might be resolved by introducing new components to the early universe, such as early dark energy that gave cosmic expansion an unexpected boost shortly after the Big Bang. Alternatively, it might require exotic particles, changing fundamental constants, or primordial magnetic fields operating differently in the cosmic past. Mark Kamiankowski from Johns Hopkins University suggests resolving the Hubble tension could reveal new insights into other discrepancies that have emerged in recent years. The expansion rate problem might connect to the massive early galaxies Webb discovered, both pointing toward missing physics in our models. The Hubble tension represents more than just measurement disagreement. It suggests our understanding of cosmic expansion, cosmic time, and cosmic evolution might be incomplete or incorrect. But the timeline problems run even deeper when examining the large-scale structure of early galaxies. The early universe should be chaotic and turbulent, with matter just beginning to clump under gravity's influence. Webb's observations reveal instead a surprisingly organized cosmos, with galaxies showing clear patterns suggesting cosmic sophistication that shouldn't exist yet. Many distant galaxies Webb discovered have flattened oval disk shapes and elongated tube-like structures rather than irregular chaotic blobs. It's like discovering a construction site has organized itself into neat rows of completed houses while nobody was watching.
These organized structures require time and stable conditions to develop. In today's universe, galaxies develop characteristic shapes through billions of years of gravitational interactions, mergers, and evolution. Early galaxies show these same sophisticated structures when the universe was barely old enough for first stars to form.
Think of galaxy formation like choreographing a complex dance. In the early universe, dancers should still be stumbling around, learning basic steps, occasionally bumping into each other. Instead, Webb discovered cosmic dancers performing intricate routines with precision, suggesting they've been practicing for eons. The structural organization Webb observes requires what cosmologists call dynamical relaxation, a process where gravitational interactions gradually organize matter into stable patterns. This operates slowly, requiring many orbital periods to create the smooth structures we observe in mature galaxies. Simon Lilly from ETH Zurich discovered early galaxies had already created vast bubbles of ionized gas extending 2 million light-years around themselves. These bubbles represent another form of large-scale organization requiring coordinated star formation across enormous cosmic distances. Creating these ionization bubbles requires not just individual galaxies forming stars, but entire regions of space working together in coordinated fashion. Young stars pumped out enormous ultraviolet radiation that cleared surrounding gas, creating transparent regions in what should be an opaque early universe. Coordinating this process across millions of light-years requires cosmic organization conflicting with our understanding of the early universe as chaotic and turbulent. It's like discovering a newborn baby has already learned to speak in complete sentences and solve complex mathematics. The smooth, organized structures suggest either the early universe was far more mature and stable than believed, or processes governing structure formation operate much faster than models predict. Both possibilities require fundamental revisions to our understanding. In the early universe, gas temperatures were scorching hot, creating conditions that should have prevented galaxy formation entirely. Cosmic gas that eventually becomes stars needs to cool significantly before gravity can overcome thermal pressure and collapse matter into stellar nurseries. Imagine building a snowman during a heat wave when temperatures exceed 100 degrees Fahrenheit. Snow melts faster than you can pack it. That's essentially what galaxy formation faces in the early universe, where gas temperatures were thousands of degrees hotter than today's cosmic background. Hot gas has high thermal pressure, resisting gravitational collapse. The faster gas molecules move due to heat, the more they resist compression into dense clouds necessary for star formation. This creates a fundamental barrier that should delay galaxy development by billions of years. Alison Kirkpatrick from the University of Kansas explains galaxies cannot form quickly because early universe gas is very hot, preventing it from collapsing into galaxies and stars. The thermal energy creates outward pressure, counteracting gravity's inward pull, creating a cosmic standoff preventing rapid structure formation. The cooling process required to bring gas temperatures down to star-forming levels operates slowly in the expanding universe. As space expands, it carries heat away, allowing temperatures to drop gradually over cosmic time. This cooling has its own built-in timeline that can't be significantly accelerated without changing fundamental universe properties. Webb's early galaxies would need cosmic gas to cool much faster than physics allows, or star formation processes operating at much higher temperatures than anything observed currently. Both scenarios require physics differing fundamentally from our understanding of thermodynamics and stellar formation. The temperature problem becomes more severe considering the early universe was also much denser.
Higher density means more frequent collisions between gas particles, generating additional heat and further resisting the cooling necessary for star formation. The early cosmos was essentially a pressure cooker that should have prevented rather than encouraged rapid galaxy development. Some theoretical models suggest dark matter structures could have grown first, creating deep gravitational wells, helping cool gas more efficiently. However, even this requires time for dark matter to clump together, adding additional timeline constraints. The combination of high temperatures, high pressures, and hostile conditions creates a perfect storm of obstacles. Webb's early galaxies appear to have formed before dark matter had time to create necessary infrastructure. Think of dark matter like a skyscraper's steel framework that must be erected before adding walls, floors, and windows. The framework provides essential structure determining where everything else can be built. Dark matter halos provide the gravitational foundation, determining where galaxies can form and how large they can grow. Dark matter particles interact only through gravity, meaning they clump together slowly compared to normal matter that can lose energy through radiation. This slow clumping follows predictable gravitational dynamics operating on cosmic timescales measured in billions of years, not the hundreds of millions available to Webb's early galaxies. Dark matter halo formation follows a hierarchical process where small structures merge to form larger ones over time. First, tiny clumps form through gravitational instabilities. These merge to form larger halos, eventually becoming massive enough to trap normal matter and begin forming stars. Webb's massive early galaxies would require dark matter halos containing trillions of solar masses. Creating halos this massive through standard hierarchical formation should take several billion years. Even under optimistic scenarios, the timeline simply doesn't provide enough history. Kirkpatrick explains that instead of galaxies forming quickly, dark matter structure should grow first, and immense gravity should then funnel gas to the center to grow the first stars. This process has built-in delays that can't be circumvented without fundamentally altering how dark matter behaves. The dark matter timeline problem suggests these massive early galaxies formed through a completely different process than observed locally, or dark matter itself behaves differently in the early cosmos. Both possibilities require major revisions to fundamental physics. Some proposals suggest primordial black holes could have provided ready-made gravitational seeds for galaxy formation, bypassing the slow dark matter halo development. However, these primordial black holes would themselves require exotic physics during the universe's first moments beyond standard cosmology. The dark matter scaffolding problem extends beyond individual galaxies to the large-scale cosmic structure. The cosmic web of dark matter filaments connecting galaxies across vast distances should also take billions of years to develop. Yet Webb observations suggest this organization existed much earlier than predicted. Webb has detected heavy elements like carbon, oxygen, and iron in galaxies that formed when the universe should contain only hydrogen and helium. These complex elements are forged in massive stars' nuclear furnaces and distributed through space when those stars explode as supernovae. Their presence creates a chemical timeline paradox.
The Big Bang produced only the three lightest elements: hydrogen, helium, and tiny traces of lithium. Everything heavier must be created inside stars through nuclear fusion, requiring millions of years to complete. It's like finding a gourmet meal in a kitchen just stocked with basic ingredients moments before. Creating heavy elements requires multiple stellar generations. First-generation stars, population 3 stars, formed from pristine hydrogen and helium. These massive stars lived fast and died young, exploding as supernovae and spreading the first heavy elements. Second-generation stars then formed from this enriched material, creating even more complex elements through their life cycles. This chemical enrichment should take billions of years to produce the heavy element levels Webb observed. Each stellar generation requires millions of years to evolve, and mixing supernova ejecta throughout galactic gas takes additional time. Early galaxies appear to have skipped several steps in this sequence. Iron's presence in early galaxies is particularly puzzling because iron forms only in the most massive stars during final moments before they collapse into black holes or neutron stars. These deaths occur only after millions of years of nuclear burning, and iron must then be distributed by supernovae and stellar winds. Webb's spectroscopic observations reveal not just heavy element presence, but abundances suggesting multiple stellar evolution generations have already occurred. Chemical signatures indicate mature stellar populations with complex nucleosynthesis histories that should require billions of years. Some early galaxies show evidence of dust formation, which requires heavy elements to condense into solid particles in cold regions between stars. Dust formation adds another complexity layer to the chemical evolution timeline, requiring not just heavy element creation, but specific conditions for these elements to form solid grains. The rapid chemical evolution suggests either first-generation stars were more massive and shorter-lived than thought, or nuclear processes creating heavy elements operated much faster in the early universe. Both scenarios require significant revisions to our understanding. The chemical timeline problem compounds all other impossibilities. These early galaxies needed time to form dark matter halos, cool their gas, form multiple stellar generations, synthesize heavy elements, and organize into complex structures. The universe simply didn't provide enough cosmic history for all these processes to occur.
Webb discovered early galaxies were powerful enough to clear vast space regions around themselves, ionizing gas across millions of light years and creating transparent bubbles in what should be an opaque early universe. This process, called cosmic reionization, should have taken hundreds of millions of years, yet Webb shows it happening much faster than predicted. After the Big Bang, the universe went through a period called the Dark Ages, when space filled with neutral hydrogen gas, blocking most light from traveling freely. Think of trying to see through thick fog, absorbing and scattering photons, making the cosmos opaque to electromagnetic radiation. For light to travel freely as it does today, this fog needed clearing through a process ionizing neutral hydrogen. The ionization requires enormous ultraviolet radiation to strip electrons from hydrogen atoms, converting neutral gas into transparent plasma. Early galaxies provided this radiation through intense light output from young, massive stars. However, energy requirements for clearing cosmic-scale regions should have demanded much more time and many more galaxies than Webb observes. Lily's team discovered relatively tiny early galaxies created ionization bubbles with 2 million light-year radii around themselves. To put this in perspective, imagine a single house producing enough light to illuminate an entire state. The energy output required for such massive bubbles should have needed much larger galaxies or many more sources working together. These transparent bubbles eventually merged to create the completely transparent universe we observe today. However, the merging should have taken hundreds of millions of years as more galaxies formed and contributed ionizing radiation. Webb's observations show this reionization process was nearly complete when the universe was only 1 billion years old, much earlier than models predicted. The timeline compression means early galaxies were either much more numerous, much more massive, or much more efficient at producing ionizing radiation than theories suggest. The reionization paradox creates another impossible efficiency requirement.
Galaxies needed to convert gas into stars fast enough to produce necessary ultraviolet radiation while simultaneously growing massive enough to power the ionization, all while organizing into complex structures. Each ionizing photon can only convert one hydrogen atom from neutral to ionized, meaning the total energy budget for cosmic reionization is enormous and precisely calculable. Early galaxies would need to produce far more ionizing photons per unit of stellar mass than local universe galaxies, requiring either different stellar populations or more efficient energy production.
The rapid reionization suggests the early universe was a much more active and energetic place than believed. The combination of massive early galaxies, rapid star formation, efficient energy production, and large-scale ionization creates a picture of cosmic evolution operating at speeds challenging fundamental physics. What if the massive black holes Webb discovered didn't grow from stellar collapse, but existed from the universe's first moments? Primordial black holes represent a radical alternative, potentially explaining how massive structures could form so quickly without violating physics. Unlike stellar black holes, forming when massive stars collapse at their lives' end, primordial black holes could have formed directly from extreme conditions during the universe's first fraction of a second. These ancient objects would exist as ready-made gravitational seeds, providing the foundation for rapid galaxy formation without requiring slow dark matter halo buildup. Think of stellar black holes like oak trees growing slowly from acorns over decades. Primordial black holes would be like discovering fully grown sequoias somehow planted as mature trees from the beginning. They bypassed the entire growth process by existing from cosmic dawn, ready to immediately begin accreting matter and building galaxies. Perez-Gonzalez's team found about 30% of mysterious early light sources have characteristics consistent with primordial black holes rather than early stars. These objects appear point-like rather than extended, suggesting they might be individual massive black holes rather than distributed stellar populations. If primordial black holes provided gravitational anchors for early galaxy formation, they could explain many of Webb's impossible discoveries. Massive early galaxies wouldn't need to wait billions of years for dark matter halos to form through slow hierarchical assembly. Instead, they could begin growing immediately around these pre-existing gravitational wells. Primordial black holes could also explain rapid chemical evolution. These ancient objects would immediately begin accreting surrounding gas, triggering intense star formation in their vicinity. Resulting stellar populations could live, die, and enrich surrounding gas with heavy elements much faster than conventional models predict. Accretion around primordial black holes generates enormous energy that could power the intense luminosity Webb observed in early cosmic sources. This energy output could also drive rapid ionization of surrounding gas, helping explain how early galaxies cleared such large regions. However, primordial black holes require very specific conditions during the universe's first moments to form. Density fluctuations in the early cosmos would need to be much larger than current models predict, requiring exotic physics during the inflationary period immediately after the Big Bang. The primordial black hole hypothesis also makes specific testable predictions. These objects should leave characteristic signatures in cosmic microwave background radiation and create distinctive patterns in large-scale structure differing from conventional dark matter-driven formation. While primordial black holes offer potential explanation for some JWST discoveries, they represent just one of several alternative theories attempting to resolve timeline paradoxes.
Other proposals challenge even more fundamental assumptions about cosmic evolution, including the very nature of cosmic redshift itself. What if distant galaxies aren't racing away through expanding space, but their light is simply losing energy during its journey across the cosmos? The tired light theory, first proposed by astronomer Fritz Zwicky in the 1920s, suggests cosmic redshift might not indicate universal expansion, but rather a fundamental property of light traveling through space over vast distances. In the tired light model, photons gradually lose energy as they traverse the universe, shifting toward longer, redder wavelengths without requiring space itself to expand. Think of it like a marathon runner starting at full speed but gradually slowing over 26 miles. Light begins its journey with high energy and short wavelengths, but arrives exhausted and redshifted. This energy loss could occur through interactions with virtual particles in the quantum vacuum, scattering off cosmic dust, or through other mechanisms operating over cosmic distances. Einstein himself suggested light might experience energy loss proportional to distance traveled, though he didn't specify the exact mechanism. Recent Webb observations have renewed interest in tired light theory because they seem to support some predictions while contradicting aspects of expanding universe models. Lior Shamir from Kansas State University analyzed redshift data from over 30,000 galaxies and found patterns aligning better with tired light than cosmic expansion. The tired light model eliminates many timeline problems Webb discovered because it doesn't require the universe to be only 13.8 billion years old. If cosmic redshift reflects energy loss rather than expansion, the universe could be much older or even eternal, providing unlimited time for massive galaxies and supermassive black holes to form through conventional processes.
Under tired light theory, massive early galaxies wouldn't represent impossible rapid formation in a young universe. Instead, they'd be mature objects in an ancient cosmos where distance, not time, creates observed redshift. The apparent youth would be an illusion created by misinterpreting redshift as expansion rather than energy loss. This alternative explanation also resolves the Hubble tension because there'd be no universal expansion to measure. Conflicting expansion rates that have puzzled cosmologists for decades disappear if redshift indicates tired light rather than recession velocity. Shamir's analysis found galaxies rotating in opposite directions relative to the Milky Way show different redshift patterns reflecting Earth's motion through space rather than universal expansion. This asymmetry supports tired light models while challenging the assumption that redshift indicates recession due to expanding space. However, tired light theory faces significant challenges from other astronomical observations. The cosmic microwave background radiation, light element abundance, and detailed large-scale structure patterns all seem to require the Big Bang model with cosmic expansion. Reconciling tired light with these observations requires additional theoretical modifications. The theory also struggles to explain time dilation observed in distant supernovae, where explosive events appear to unfold more slowly at higher redshifts. This time dilation effect provides strong evidence for cosmic expansion that tired light models have difficulty reproducing without additional assumptions. Despite these challenges, Webb's discoveries have forced cosmologists to reconsider fundamental assumptions about cosmic redshift and expansion. The massive early galaxies and impossible timelines revealed by the telescope suggest our interpretation of cosmic observations might need radical revision. Webb detected active star formation occurring when the universe was only 100 million years old, during an epoch when the cosmos should be too hot and chaotic for stellar nurseries to exist. The telescope revealed young, massive stars blazing with intense blue light from extremely early times, pushing the boundaries of when star formation could theoretically begin. At 100 million years after the Big Bang, the universe was still recovering from its violent birth. Gas temperatures remained scorching hot, matter was distributed much more uniformly than today, and heavy elements necessary for efficient star formation hadn't yet been created by previous stellar generations. These conditions should have prevented gas clouds from collapsing into dense cores needed for nuclear ignition.
Think of trying to build a campfire during a hurricane with wet wood and no kindling. Environmental conditions work against every step of the process, making ignition nearly impossible. Early universe star formation faced similar obstacles. Hot gas resisted gravitational collapse. Turbulent motions prevented stable cloud formation. The lack of heavy elements eliminated efficient cooling mechanisms. Normal star formation requires gas clouds to cool down and collapse under their own gravity until core temperatures reach 10 million degrees, hot enough to ignite nuclear fusion. In the early universe, background gas temperature was already so high that additional cooling became extremely difficult, creating a fundamental barrier to stellar birth. First-generation stars, population 3 objects, should have been significantly different from stars we observe today. These primordial giants would contain only hydrogen and helium, making them extremely massive and short-lived compared to metal-rich stars forming in the current universe. Their brief lifespans should create a natural delay in building up large stellar populations. Webb's observations suggest early star formation proceeded much more rapidly and efficiently than theoretical predictions. The blue ultraviolet light detected indicates the presence of massive hot young stars requiring rapid formation and high-efficiency conversion of gas into stellar material. Some research teams proposed early star formation operated through a bursty mode, where periods of intense stellar birth alternated with dormant phases. During these bursts, galaxies could form stars much faster than the steady, continuous process observed in local galaxies, temporarily overcoming hostile early universe conditions. Claude-André Faucher-Giguère from Northwestern University suggests early galaxies experienced rapid star formation bursts after millions of years of dormancy. These intense episodes could create the bright, massive stellar populations Webb observed without requiring sustained star formation over billions of years. The bursty formation model proposes stellar winds and supernova explosions would periodically clear gas from early galaxies, shutting down star formation temporarily. When gas eventually cooled and fell back, it would trigger another intense burst of stellar birth, creating a cosmic heartbeat of stellar formation. However, even the bursty formation model struggles to explain the sheer number and brightness of early stars Webb discovered. The energy output from these early stellar populations exceeds what even optimistic burst models predict, suggesting fundamental aspects of stellar physics might operate differently in the primordial universe.
Lambda cold dark matter cosmology, the theoretical framework guiding our understanding for decades, faces its greatest challenge from Webb's impossible discoveries. This standard model, built on dark energy, cold dark matter, and conventional physics, simply cannot accommodate the massive early galaxies and rapid evolution the telescope revealed. The Lambda CDM model makes specific quantitative predictions about how quickly structures can form in the early universe. These predictions arise from fundamental physics governing how dark matter clumps together, how gas cools and forms stars, and how galactic structures assemble over cosmic time. Webb's observations violate nearly every one of these carefully calculated predictions.
Think of the standard model like a detailed recipe specifying exactly how long each step should take to create the final cosmic dish. The recipe calls for billions of years of slow simmering to develop complex flavors and textures. Webb discovered the universe somehow produced a gourmet meal in minutes using only basic ingredients. Boylan-Kolchin warned that if Webb's mass measurements prove correct, fundamental changes to the reigning model would be required. The discoveries don't represent minor adjustments to existing theory, but wholesale revisions to our most basic assumptions about how the universe works. The standard model predicts only a small fraction of the universe's matter should be contained in massive galaxies during the first billion years. Webb discovered roughly twice as many massive early galaxies as the model allows, with some individual objects exceeding theoretical maximum mass for their epoch by factors of 10 or more. These violations extend beyond just galaxy masses to include formation timescales, chemical evolution rates, and structural organization that all conflict with lambda CDM predictions. It's not a single observation contradicting theory, but a systematic pattern of violations across multiple independent measurements. The crisis deepens because the standard model isn't just a loose collection of ideas, but a tightly integrated theoretical framework where each component depends on others. Changing one aspect to accommodate Webb's discoveries inevitably creates conflicts with other well-established observations. For example, modifying dark matter properties to allow faster structure formation might resolve the early galaxy problem, but would create new conflicts with observations of the cosmic microwave background, large-scale structure, or the abundance of light elements created during Big Bang nucleosynthesis.
Similarly, changing the expansion history to provide more time for early structure formation would affect the predicted age of oldest stars, timing of cosmic reionization, and the relationship between distance and redshift underlying much of observational cosmology. James Peebles, a Nobel laureate and modern cosmology pioneer, emphasizes that science thrives on doubt, and Webb's findings present an opportunity for progress rather than a crisis. However, the scope and scale of violations suggest any resolution will require fundamental rather than incremental changes to our cosmic worldview. Webb discovered distant galaxies appear larger in the sky than expanding universe models predict, creating a measurement crisis challenging one of the fundamental assumptions underlying Big Bang cosmology. The angular sizes of these faraway objects suggest space itself might not be expanding as we've assumed for nearly a century. When space expands, it creates a specific relationship between an object's distance, its actual size, and how large it appears in the sky. Think of watching a balloon inflate while a toy soldier sits on its surface. As the balloon grows, the toy soldier moves farther away and should also appear smaller due to increasing distance created by the expanding surface. In an expanding universe, distant galaxies should appear smaller than they would in a static cosmos, because expansion stretches the light path and affects the relationship between distance and angular size. This prediction is fundamental to Big Bang cosmology and has been used to interpret cosmic observations for decades. However, Webb's measurements of distant galaxy angular sizes don't match expanding space predictions. Galaxies appear roughly 10 times larger than Big Bang models predict they should at their observed redshifts. This discrepancy is systematic and consistent across multiple independent measurements, ruling out random errors. The angular size problem connects directly to the Doppler interpretation of cosmic redshift, supporting tired light theory.
If redshift indicates light energy loss rather than cosmic expansion, then the relationship between distance, redshift, and angular size would follow completely different mathematical rules, aligning much better with Webb's observations. Biblical cosmologist Danny Faulkner analyzed Webb's data and found galaxy angular sizes average about 0.2 arcseconds at high redshifts, exactly matching predictions from non-expanding Doppler models, while contradicting Big Bang expectations by factors of 10. This represents one of the most precise observational tests of cosmic expansion ever conducted.
Angular size measurements are particularly significant because they don't depend on complex assumptions about stellar populations, galaxy evolution, or dark matter physics. They represent direct geometric observations testing the fundamental assumption of expanding space through basic trigonometry and light travel. If space is not expanding, then cosmic redshift must be explained through alternative mechanisms like tired light, intrinsic redshift, or other physical processes not requiring the fabric of space itself to stretch over time. These alternatives would eliminate the need for dark energy, the mysterious force supposedly driving accelerated expansion. The angular size anomaly also affects brightness measurements, with distant galaxies appearing brighter than expanding universe models predict. The combination of larger angular sizes and higher brightness creates a consistent pattern supporting static universe interpretations while challenging expansion-based cosmology. According to Big Bang theory, the universe should have experienced a prolonged darkness lasting hundreds of millions of years when no stars existed and no light illuminated the cosmos. Webb's discoveries suggest these dark ages never happened, revealing instead a universe actively forming stars and galaxies much earlier than theory allows. The Dark Ages were supposed to begin about 400,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, should have made space transparent for the first time, but also eliminated free electrons needed for continued energy production through electromagnetic processes. Without energy sources to prevent gravitational collapse, the universe should have entered a dark period where only gravity operated to slowly pull matter together into first cosmic structures. This era should have lasted until first stars finally formed, hundreds of millions of years later, ending the darkness with cosmic dawn. Think of the Dark Ages like a power outage in a city that should last for hours while repair crews slowly restore electricity. The universe was supposed to go dark after recombination and remain dark until the first stellar power plants came online to illuminate space again. Webb discovered bright, organized light sources at extremely early times when the universe was only 100 million years old. This represents cosmic dawn arriving 3 to 4 times earlier than standard models predict, compressing the supposed Dark Ages into a much shorter period than theory allows. The discovery of active star formation at these early times suggests the universe never experienced the extended dormant period that Big Bang cosmology requires. Instead of dark ages lasting hundreds of millions of years, Webb reveals a cosmos that became active and luminous almost immediately after recombination.
Emmett Chapman from the University of Nottingham noted that discovering such massive galaxies so soon after the Big Bang suggests the Dark Ages may not have been so dark after all. The universe appears awash with star formation far earlier than thought, fundamentally altering our timeline of cosmic evolution. The absence of extended dark ages eliminates one of the key predictions of Big Bang cosmology and suggests the early universe operated according to very different physical principles than assumed. The rapid transition from recombination to active star formation requires processes bypassing the slow gravitational assembly predicted by standard models.
If the Dark Ages were much shorter or non-existent, then timeline problems Webb discovered with early galaxy formation become even more severe. The universe would have had even less time than previously calculated to assemble the massive organized structures observed. The missing Dark Ages also affect our understanding of cosmic reionization, the process that made the universe transparent to most wavelengths of light. If star formation began much earlier than expected, then reionization would also have started earlier, requiring a complete revision of the timeline governing cosmic transparency. To explain Webb's impossible discoveries, physicists are proposing exotic forces and particles that operated in the early universe but have since disappeared or become inactive. These theoretical additions to the Standard Model represent desperate attempts to preserve our cosmic timeline by introducing completely new physics. Boyle and Colchan suggested one of the most extreme possibilities for explaining rapid early galaxy formation is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles beyond everything we currently understand about fundamental reality. Think of the early universe like a construction site where workers had access to advanced tools and techniques no longer available today. These cosmic construction crews could build massive structures using methods that became obsolete once conditions changed, leaving behind achievements that seem impossible given current capabilities. Early dark energy represents one proposed new component that could have accelerated cosmic expansion during the first billion years, providing more time for structure formation by stretching the cosmic timeline. This mysterious energy field would need to operate very differently from the dark energy driving current cosmic acceleration.
Kamyankowski suggests exotic particles with properties unlike anything in the Standard Model might have dominated physics during the universe's infancy. These particles could have enhanced gravitational attraction, modified stellar formation processes, or provided alternative energy sources for cosmic structure development. Changing electron mass represents another exotic possibility, where fundamental particles had different properties in the early universe. If electrons were lighter or heavier in the past, it would affect atomic structure, chemical bonding, and stellar physics in ways that could accelerate galaxy formation and energy production. Primordial magnetic fields offer yet another avenue for new physics, suggesting the early universe contained much stronger magnetic fields than exist today. These fields could have guided matter assembly, enhanced star formation efficiency, and created organized structures through electromagnetic forces. The proposals for new physics aren't just minor additions to existing theory, but fundamental modifications to our understanding of how forces, particles, and fields operate. They suggest the universe once functioned according to a completely different set of physical laws that somehow transitioned to current physics. The universe demands a new origin story, one that can accommodate massive early galaxies, rapid cosmic evolution, and impossible timeline compressions, while explaining why these discoveries conflict so dramatically with our most fundamental theories. This new cosmic narrative will likely combine elements from multiple alternative theories while introducing physics we haven't yet discovered. The new model might begin not with a singular Big Bang, but with a pre-existing cosmic state that provided unlimited time for structure formation before transitioning to the expanding universe we observe today. Hybrid cosmologies combining steady-state creation with Big Bang evolution offer one path forward, suggesting the universe underwent different phases of evolution governed by different physical laws. The early phase could have operated under conditions allowing rapid structure formation before transitioning to standard physics. Multi-dimensional models propose early cosmic evolution occurred in higher dimensional spaces where different physics allowed impossible structure formation rates.
As the universe evolved, it transitioned to our current three-dimensional limitations, preserving early structures while preventing further impossible evolution. The new cosmic story might feature variable fundamental constants, with the strength of gravity, the speed of light, or particle masses changing over time in ways that created windows of opportunity for accelerated structure formation during specific cosmic epochs.
Quantum cosmology could provide the framework for pre-existing cosmic organization, suggesting the universe inherited structure from underlying quantum fields rather than building it up slowly through gravitational assembly. This quantum inheritance would explain rapid organization without violating physical laws. The role of consciousness and information in cosmic evolution represents another frontier that might need exploration. If the universe operates more like a computational system than a mechanical one, then cosmic evolution could follow algorithmic rules, permitting rapid structure formation under specific conditions. Whatever new model emerges will need to be more than just theoretically consistent. It must make specific, testable predictions that can be verified or falsified through future observations. The James Webb Space Telescope will continue collecting data that will either support or eliminate various proposals for new cosmic physics. The rewriting of our origin story represents more than academic exercise. It touches on fundamental questions about the nature of existence, the role of time in cosmic evolution, and humanity's place in a universe that might be far stranger and more wonderful than we ever imagined. We stand at a cosmic crossroads where the universe itself is forcing us to expand our understanding of reality. The impossible discoveries Webb has revealed suggest we're living in a cosmos that operates according to rules we haven't yet learned to recognize. The greatest adventure in human understanding is just beginning. To continue these adventures and discoveries together, don't forget to subscribe and like. Good night. Sweet dreams.
Beneath the ground you are standing on right now, at a depth of 60 million years, something is hidden that has the power to change all your beliefs about humanity being special. Scientists have discovered chemical traces in ancient sediment layers that are eerily familiar. These traces almost perfectly match the marks left today by our own industrial civilization. Are we really the first? Or could intelligent and willful beings have emerged before us, built cities, altered the climate, and then vanished without leaving a trace? Together, we will examine 26 pieces of evidence suggesting that Earth may have hosted other civilizations in its past. If I told you that your city would no longer exist in 3,000 years, would that sound absurd to you? Every skyscraper, every highway, every monument we believe to be permanent will eventually turn to dust, and Earth will not even notice. I don't want you to see this as a random guess. We will ground these claims in solid evidence. We know exactly how fast our civilization is disappearing because we can observe it in real time, and whether we want to or not, we are part of it as humanity. In the abandoned zones around Chernobyl, nature has already begun erasing just 30 years of human presence. Climbing plants have cracked concrete, trees have split foundations apart, metals have rusted into orange dust and washed away with the first rain. Think of concrete as a sandcastle. It stands firm the moment it is built, but time is like an endless tide. Freeze-thaw cycles act like millions of hammer blows each year. Chemical reactions turn steel into iron oxide. Even our most durable materials are subject to the same law that governs everything in nature. Order turns into chaos, structure turns into dust. And we are a fundamental part of that process. The only human artifacts likely to survive for more than 1 million years are the simplest ones: stone tools, fragments of pottery, and tiny pieces of plastic mixed into sediment layers.
Everything else that defines our technological civilization will completely disappear, leaving almost no evidence that we ever existed. But the question that truly fascinates scientists is this: if our advanced civilization can vanish so quickly, how could we ever detect the evidence of a civilization that may have existed in the distant past?
This leads us to an even stranger realization. Humanity occupies less than 0.01% of Earth's history. Let's imagine compressing Earth's 4.5 billion year story into a single day. Humans appear in the very last second before midnight. Our entire industrial age, from the steam engine to smartphones, unfolds in the final millisecond. Geologically speaking, we are such newcomers that our presence barely registers in the rock record. This creates what scientists call the detection problem. When you look at rock layers, every centimeter represents thousands or even millions of years of compressed time. A civilization that lasted 10,000 years would appear as a paper-thin line between massive layers of stone. Most sediment samples simply skip over such short intervals. Now consider this. If an industrial civilization had existed 60 million years ago and lasted twice as long as ours, finding any trace of it would require extraordinary luck. It would be like searching for a single page torn from a book and scattered across an entire continent. You might be looking in all the right places and still find nothing. And even if you did find something, you might not believe it was real.
But here is what completely changes the rules of the game. Industrial civilizations don't just build things that decay. They alter the planet's entire chemistry in ways that can last for millions of years. They leave signatures etched into the atomic structure of rocks. Every year, we produce 300 million tons of plastic. Most people assume plastic pollution will last forever, but they are wrong. On a geological timescale, plastic breaks down relatively quickly. Heat, sunlight, and chemical reactions break these long molecular chains apart within thousands of years, not millions. The plastic bottles polluting the oceans today will likely be gone long before the next ice age. Perhaps then someone else will be searching for evidence of us. However, plastic doesn't simply disappear, it transforms. As these molecular chains break apart, they release specific chemicals that become mixed into sediments. Scientists can detect these chemical markers even after the original plastic has completely vanished. It's like finding the ghost of a molecule, a chemical fingerprint proving that something artificial once existed there. Think of it like the scent of perfume left in a room. The person who wore it is gone, but you can still detect their presence through the molecules lingering in the air. Plastic leaves similar molecular traces in rock layers, creating what geologists call a synthetic signature.
The most persistent markers come from the additives mixed into plastics during manufacturing. Flame retardants, UV stabilizers, and plasticizers contain rare combinations of elements that would never occur naturally. When plastic debris settles on the ocean floor, these compounds become incorporated into marine sediments. But plastic is only one example of how industrial activity leaves chemical traces. Right now, we are creating dozens of other signatures that could persist for millions of years. And some of the most revealing signatures come from something we never intended to leave behind. Ancient rock layers contain carbon signatures we struggle to explain. Scientists who extract ice cores and sediment samples sometimes encounter layers where carbon chemistry shifts suddenly and unexpectedly. Isotope ratios change rapidly, indicating that enormous amounts of carbon were released into the atmosphere over very short geological timescales. Natural processes such as volcanic eruptions or wildfires can cause increases in carbon levels. But some of these ancient anomalies look different. They look industrial. When we burn fossil fuels, we release carbon with a specific isotopic signature. Coal, oil, and natural gas are made from ancient organic matter. As a result, they contain lighter carbon isotopes compared to the carbon found in living plants. This creates a measurable shift in atmospheric chemistry, recorded in tree rings, ice cores, and ocean sediments.
Think of carbon isotopes as fingerprints. Each source has its own unique pattern. Volcanic carbon has one signature. Carbon from wildfires has another. Industrial carbon from burning fossil fuels has a third, distinctly different pattern. When scientists find this industrial pattern in rock layers that are millions of years old, they conclude that something at that time was burning fossil fuels. The most astonishing examples come from deep ocean sediment cores. Some layers show rapid shifts in carbon chemistry that occurred over just a few thousand years. Geologically speaking, this is extremely fast, indicating sudden and massive carbon releases that disrupt natural cycles. These carbon spikes are often accompanied by other chemical changes that make them even more intriguing. As our oceans absorb carbon dioxide from fossil fuel combustion, they become more acidic. This process of ocean acidification is happening at a rate that deeply concerns marine biologists. The pH of seawater is measurably decreasing each year, dissolving coral reefs and disrupting the entire marine food chain. We can track this acidification in real time using instruments deployed across the world's oceans. But when scientists examine ancient sediment layers, they find evidence that the oceans rapidly acidified several times in Earth's deep past. The chemical signatures are clear. Calcium carbonate shells dissolve, marine ecosystems collapse, and the fossil record shows mass extinctions that align precisely with these acidification events.
Natural processes can acidify the oceans, but most of them occur very slowly over millions of years. Volcanic activity or asteroid impacts can cause faster changes, but they leave behind other distinctive markers. Some ancient acidification events have no clear natural explanation. Think of ocean chemistry as a massive buffering system. Overwhelming the ocean's natural ability to maintain its pH requires an enormous input of carbon dioxide. When you find rapid acidification in the geological record, it means something was pumping extraordinary amounts of carbon into the atmosphere in a very short period of time. The most mysterious acidification events are those that show multiple rapid pulses, as if someone were repeatedly turning a massive carbon source on and off. This pattern suggests control and regulation rather than a single natural catastrophe. These chemical signatures become even more intriguing when you examine what happened to specific elements during these ancient events.
Every industrial process alters the isotopic signatures of elements in predictable ways. When we smelt metals, refine oil, or manufacture chemicals, we are effectively sorting atoms by weight. Lighter isotopes behave slightly differently from heavier ones during chemical reactions. This creates distinctive isotopic patterns that persist long after the original industrial activity has ended. Lead isotopes provide the clearest example. When ancient civilizations smelted lead ores, they unknowingly produced specific lead isotope ratios that were entirely different from natural background levels. Scientists can detect these artificial lead signatures in ice cores and sediment layers, providing direct evidence of metal production thousands of years ago. The same principle applies to other elements. Copper, zinc, silver, and mercury all display isotopic fingerprints resulting from industrial processing. These signatures function like atomic serial numbers, identifying human activity even after all physical artifacts have disappeared.
Think of isotopes as identical twins with slightly different weights.
When you put them through industrial processes, the lighter twin moves a bit faster than the heavier one. This separation creates patterns that nature rarely produces on its own. What makes this evidence so compelling is its persistence. Isotopic signatures can survive for millions of years because they are literally built into the atomic structure of sediments. Unlike physical artifacts that rust and decay, these chemical fingerprints remain readable across geological time. Some of the most dramatic isotopic anomalies in Earth's history coincide with mysterious mass extinction events. 5 times in Earth's history, more than 75% of all species vanished suddenly. These mass extinctions have obvious natural causes. Asteroid impacts, massive volcanic eruptions, or dramatic climate shifts can explain most of the destruction. But when scientists examine the detailed progression of these extinctions, some patterns appear disturbingly artificial.
Some ancient mass extinctions display this selective signature alongside rapid environmental changes that look industrial rather than natural. The timing is also suspicious. These extinctions often occur far more quickly than natural climate change can explain. But the most compelling evidence comes from examining what disappeared during these ancient events. Every smartphone contains 17 different rare earth elements. Elements with names like neodymium, dysprosium, and terbium are essential to modern technology. They make magnets stronger, screens brighter, and batteries more efficient. Without rare earth elements, we could not build computers, electric motors, or renewable energy systems. Here's the problem: these elements are truly rare. Across the entire planet, there are only a few dozen economically viable deposits. Once these materials are extracted and used, they don't disappear, but they become dispersed and diluted beyond practical recovery. We are essentially consuming a finite resource that took billions of years to concentrate. What fascinates geologists is that some ancient sediment layers show unusual depletion patterns of rare earth elements. These layers contain concentrations far lower than what natural processes would predict. Something, millions of years ago, was extracting and redistributing these materials. Think of rare earth mining like harvesting honey from wild beehives. The first civilization to discover these deposits would have easy access to highly concentrated ores. But after intensive extraction, future civilizations would find only dispersed, low-grade deposits that are far more difficult to process. This creates what scientists call a resource bottleneck. If a technological civilization exhausts critical mineral resources, it becomes much harder for the next civilization to reach advanced industrial levels. They would need to develop far more complex extraction and recycling technologies just to obtain what their predecessors achieved relatively easily. Geological evidence suggests that this bottleneck may have operated before. It takes Earth about 100 million years to generate a new generation of fossil fuels. Coal, oil, and natural gas form through extraordinarily slow geological processes. Organic matter must be buried under specific conditions, heated to precise temperatures, and compressed for millions of years. The fossil fuels we burn today began forming when dinosaurs still dominated the planet. This creates a fascinating detection opportunity. If a previous industrial civilization had depleted Earth's fossil fuel reserves, there would be a gap in the geological record. Layers that should contain coal or oil deposits would instead appear mysteriously empty or exhausted. Several sedimentary basins around the world display exactly this pattern. They contain rock formations with all the right conditions for fossil fuel formation, yet they hold far less organic carbon than geologists would expect. These missing deposits may represent fossil fuels that were extracted and burned millions of years ago. Think of fossil fuel formation like wine aging in a cellar.
Each geological layer represents a different grape harvest, slowly maturing over millions of years. If you find empty spaces where certain vintages should be, you know someone has already collected them. The evidence becomes even more compelling when you consider what happened to the chemistry of these missing deposits. Burning large amounts of fossil fuels would leave specific chemical signatures throughout the environment. These signatures would persist far longer than the civilization that created them. Our most advanced technologies leave the smallest traces. Bronze axes can survive for 3,000 years in museum collections. Stone tools can last for millions of years, but silicon computer chips turn to dust within decades. Fiber optic cables degrade faster than wooden handles. The more complex our technology becomes, the less likely it is to survive as recognizable artifacts.
This creates a strange archaeological paradox. The most advanced civilizations leave the fewest traces. If we discovered the ruins of an ancient city today, we would find pottery, metal tools, and stone foundations. We would never find computer processors, plastic components, or electronic devices, even if those were the most important technologies that civilization used. Advanced materials such as carbon fiber composites, rare earth magnets, and synthetic polymers are designed to be lightweight and efficient, which makes them inherently fragile over geological timescales. They oxidize, break down, or dissolve far more quickly than raw materials like iron and stone. Think of technological preservation like construction materials in a house. Concrete blocks and steel beams will survive for millions of years longer than high-tech insulation or complex electronics. Future archaeologists would find evidence of our building methods, but they would miss most of our true technology. This means that if we want to detect evidence of previous technological civilizations, we cannot rely on finding their artifacts. We must look for the subtler signatures that advanced technology leaves in the environment. And some of those signatures are written into the deepest layers of the Earth. Ice cores extracted from Antarctica contain a record of Earth's atmosphere going back 800,000 years. Each year, snowfall accumulates on the polar ice sheets, compressing into layers of ice that trap tiny bubbles of ancient air. Scientists can extract these bubbles and measure the exact composition of the atmosphere from hundreds of thousands of years ago. It's like having a chemical diary of Earth's climate history.
The ice core record shows the natural cycles of carbon dioxide, methane, and other greenhouse gases. These cycles correspond to ice ages, volcanic eruptions, and other known climate events. But scattered throughout this record are brief spikes and anomalies that do not match any natural pattern. Some of these anomalies suspiciously resemble our current industrial emissions. Rapid increases in carbon dioxide and methane are followed by strange chemical signatures that suggest industrial activity. The timing and magnitude of these increases cannot be explained by volcanism, wildfires, or other natural processes. Think of ice cores like tree rings, but for the entire planet's atmosphere. Each layer contains chemical information that reveals what was happening in the environment when that ice formed. Unusual chemical combinations stand out like foreign words written in a familiar language. The most intriguing anomalies are those that show multiple industrial signatures occurring at the same time. Increases in carbon dioxide are accompanied by sulfur compounds, nitrogen oxides, and trace metals that suggest coordinated industrial activity rather than random natural events. However, ice cores only go back 800,000 years, which is considered recent in geological terms. A civilization lasting 10,000 years would occupy a sediment layer thinner than a sheet of paper. Ocean sediments accumulate incredibly slowly, often less than 1 centimeter per 1,000 years. This means that entire civilizations could be compressed into layers so thin that standard geological sampling techniques would completely miss them. Most sediment cores are taken at intervals of several centimeters, which can easily miss short industrial periods. Scientists face what they call a sampling resolution problem. Tools and methods designed to study geological processes over millions of years are not well suited to detecting events that last only thousands of years. It is like looking for a needle in a haystack, but the needle is smaller than the gaps between the hay. However, there are places where sediments accumulate much more rapidly. River deltas, coastal margins, and certain deep ocean basins can preserve records with much higher resolution. In these special locations, a civilization lasting 10,000 years could leave behind a measurable sediment layer containing detectable chemical signatures. Think of sediment layers as pages in a book about Earth's history. Most pages cover millions of years. Short-lived civilizations are like single sentences scattered across thousands of pages. You need to know exactly where to look, and you need sampling techniques specifically designed to capture these brief intervals. Recent advances in analytical chemistry now allow scientists to detect industrial signatures even in extremely thin sediment layers. They can identify synthetic compounds, isotopic anomalies, and chemical combinations that indicate technological activity. Some of the most promising evidence comes from sediments that should not contain certain elements at all. Nuclear technology leaves signatures that can persist for millions of years. When we split atoms in nuclear reactors or weapons tests, we create isotopes that do not occur naturally on Earth. These artificial isotopes possess distinctive decay signatures that remain detectable long after the original radioactive material has fallen to safe levels. They are atomic fingerprints, proving that nuclear technology was once active. The most persistent nuclear signatures come from plutonium production and uranium enrichment. These processes create specific ratios of uranium and plutonium isotopes that never form in nature. Even millions of years later, scientists can detect traces of these artificial isotopes within sediment layers. Nuclear accidents and weapons tests also leave characteristic patterns. The Chernobyl disaster created a global fallout signature that will remain detectable for thousands of years. Nuclear weapons tests conducted in the 1950s produced artificial isotopes that are now embedded worldwide in tree rings, ice cores, and sediment layers. Think of artificial isotopes as radioactive signatures written in atomic ink. As the isotopes decay, they slowly fade over time, but they follow predictable mathematical patterns that allow scientists to trace them back to their original sources and creation dates. What makes nuclear signatures especially valuable for detecting ancient civilizations is their uniqueness. There are no natural processes capable of producing these specific combinations of isotopes. Finding them in ancient sediment layers would be definitive proof of technological activity. Some deep ocean sediment cores contain unexplained isotopic anomalies that could represent ancient nuclear signatures. Approximately 2.5 billion years ago, cyanobacteria polluted Earth's atmosphere with a deadly toxin known as oxygen. This mass poisoning event, known as the Great Oxygenation Event, killed most life on Earth. Toxic oxygen gas reacted with everything it encountered, triggering what scientists describe as the first global pollution crisis. It took millions of years for new life forms capable of surviving in this poisonous atmosphere to evolve. From our perspective, oxygen appears natural and essential, but that is only because we evolved to breathe it. Earth's original atmosphere contained almost no oxygen, and many early life forms found it just as toxic as we would find hydrogen sulfide or chlorine gas today. This precedent shows that intelligence and technology are not required to cause global environmental catastrophes. Even simple organisms can completely transform a planet's chemistry through biological processes. If bacteria could poison an entire atmosphere, imagine what an industrial civilization could achieve. Think of the Great Oxygenation Event as a dress rehearsal for industrial pollution. It demonstrates how Earth's environment can be radically altered by the byproducts of biological activity. The same principles apply to technological activity, but on much faster timescales. What makes this precedent especially relevant is that it left permanent chemical signatures in rock layers worldwide. The oxygenation event created distinctive iron formations and sulfur isotope signatures that geologists can still identify billions of years later. If living organisms can leave such clear chemical fingerprints, technological civilizations should leave even more pronounced ones. On the ocean floor, within sediment layers around 50 million years old, lie mysterious regions where nothing lived. These ancient dead zones appear as dark bands in sediment cores, completely devoid of fossils, organic matter, or any signs of life. They represent periods when vast areas of the ocean became so toxic that no organisms could survive there. The chemistry of these layers points to extreme pollution overwhelming natural ocean systems. Most dead zones form when excessive nutrient loads trigger massive algal blooms that consume all available oxygen. When the algae die and decompose, they create anoxic conditions that kill everything else. This process can occur naturally in some environments, but the ancient dead zones are far more widespread and intense than what natural processes typically produce. One of the most surprising aspects of these ancient dead zones is their geographic distribution. They do not follow the patterns expected from natural causes, such as volcanic activity or climate change. Instead, they appear clustered around continental margins and major river systems, exactly where industrial pollution would be expected to be most concentrated. Think of these dead zones as crime scenes preserved in rock. The evidence shows that something killed marine life across vast areas of the ocean, but the usual suspects, natural disasters, do not match the patterns of destruction. Chemical analysis of these dead zone sediments reveals synthetic organic compounds and metal concentrations that are difficult to explain through natural processes. These signatures suggest industrial runoff and chemical pollution on a scale that would require complex manufacturing capabilities. But these oceanic dead zones are only one part of a much larger puzzle that becomes even more intriguing when you examine what was happening on land during the same periods. Copper should be randomly distributed throughout Earth's crust, but it isn't. When geologists map the locations of metal deposits worldwide, they expect to find patterns consistent with natural geological processes. Volcanic activity, hydrothermal vents, and sedimentary processes create predictable metal distributions based on chemistry and physics. Yet some elements display clustering patterns that do not align with these natural processes. The most obvious anomalies involve metals essential to technology. Deposits of copper, tin, and zinc often appear in combinations and concentrations that would be exceptionally useful for Bronze Age or industrial civilizations. It is as if someone had already identified and exploited the richest and most accessible ores, leaving behind depleted regions and scattered deposits. Archaeological evidence supports this interpretation for recent human activity. Ancient mining sites show clear signs of selective extraction. Miners targeted the highest grade ores and left behind lower quality material. This creates distinctive geochemical signatures that persist long after mining activity has ended. Think of metal distribution like harvesting fruit from an orchard. The first harvesters take the largest, ripest fruit from the most accessible trees. Later visitors find only smaller fruit in harder-to-reach locations.
The pattern of what remains tells a story about who was there before. What makes this evidence particularly compelling is that some ancient depleted regions are far older than human civilization. Geological surveys reveal mining-like patterns in rock formations dating back millions of years. These patterns suggest the systematic extraction of high-quality ores by unknown actors.
The depletion patterns become even more suspicious when you examine how precisely they match the requirements of advanced metallurgy. The Great Pyramid of Giza erodes by roughly 1 part in 1,000 every 1,000 years. Even the most durable human structures follow predictable decay curves. Stone monuments weather according to mathematical processes driven by rainfall, temperature cycles, and chemical erosion. Scientists can calculate with remarkable accuracy how long it takes for any structure to become unrecognizable. The results are sobering. Mount Rushmore will become unreadable in about 500,000 years. The Great Wall of China will be effectively invisible in roughly 2 million years. Even structures built from the most durable materials available to human engineering will be completely erased within 10 million years. This creates what archaeologists call the monument paradox. If previous civilizations built structures comparable to our greatest achievements, we should occasionally find traces of their foundations or remnants of their building materials. The absence of such evidence suggests either that previous civilizations never existed or that they built using materials and methods entirely different from our own. Think of monument decay like erosion carving canyons into solid rock. The process is slow but relentlessly certain. Every freeze-thaw cycle, every acid rainstorm, every seismic tremor contributes to the gradual dissolution of even the largest structures. However, there are environments where unusually durable materials could survive far longer. Certain crystalline formations, synthetic diamonds, or engineered ceramics could potentially last for hundreds of millions of years under the right conditions. Some geological formations display strange regularities that could represent heavily eroded remnants of artificial structures.
But the most intriguing evidence comes from materials that should not exist in nature at all. Ancient sediments contain molecules that could never form through natural processes. Every chemical compound follows specific rules governing how atoms can bond. Natural processes create predictable molecular patterns based on temperature, pressure, and available elements. Industrial chemistry, however, can force atoms into arrangements that would never arise without technological intervention. These synthetic molecules behave like chemical fossils, proving that artificial activity once occurred. Even after the original materials have decayed, their breakdown products retain distinctive molecular signatures. Using mass spectrometry and other advanced analytical techniques, scientists can identify these signatures and detect artificial compounds at concentrations as low as parts per trillion. The most persistent synthetic signatures come from polymer chemistry. When plastics, synthetic fibers, and industrial chemicals break down, they leave behind specific molecular fragments with no natural counterparts. These fragments can survive in sediment layers for millions of years, providing direct chemical evidence of technological activity. Think of synthetic molecules like artificial DNA. Each one carries information about the industrial processes that created it. Their molecular structures reveal details about temperatures, pressures, catalysts, and manufacturing methods that would be impossible to achieve without complex technology.
Recent advances in analytical chemistry have enabled scientists to detect these synthetic signatures in sediment cores dating back millions of years. Some ancient layers contain molecular patterns that closely resemble modern industrial byproducts, yet display subtle differences that suggest alternative production processes. When these chemical signatures appear alongside biological markers that should not exist naturally, the results become even more striking. DNA carries a record of every genetic modification that has occurred. Modern genetic engineering leaves distinctive traces in the genomes of modified organisms. Inserted genes, deleted sequences, and artificial regulatory elements create patterns that are clearly distinct from natural evolution. These biosignatures persist in the fossil record and can be detected even in ancient DNA samples. What astonishes paleogeneticists is that some ancient DNA samples contain sequences that appear suspiciously artificial. These sequences show evidence of precise editing, systematic modifications, and artificial genetic combinations that are statistically highly unlikely to arise through natural mutation and selection alone. The most intriguing examples come from extinct species that display signs of rapid, coordinated genetic changes. Rather than gradual evolutionary adaptation, these organisms appear to have undergone sudden improvements in multiple traits simultaneously. Such patterns are characteristic of deliberate genetic engineering rather than natural selection.
Think of genetic engineering like editing a book. Natural evolution usually makes random changes that are often harmful, like spelling mistakes that render sentences unreadable. Genetic engineering makes intentional changes that improve the text, like a skilled editor correcting grammar and adding a richer vocabulary. Some ancient species display genetic modifications that may have required a highly sophisticated understanding of molecular biology. Enhanced disease resistance, increased metabolic efficiency, and optimized reproductive systems that appear suddenly in the fossil record without clear evolutionary precursors. These biosignatures suggest that genetic engineering may have been applied millions of years before humans developed technology, raising profound questions about who performed this engineering and what happened to their civilizations. Geologists have identified 23 distinct geological epochs in Earth's history. Each geological epoch is defined by dramatic changes in rock layers, fossil assemblages, or chemical compositions that mark major transitions in Earth's development. Most of these transitions have clear natural causes, such as asteroid impacts, volcanic eruptions, or gradual climatic shifts.
However, some geological boundaries display features strikingly similar to our current Anthropocene epoch: rapid environmental changes, mass extinctions with selective patterns, and chemical signatures that suggest technological activity. These proto-Anthropocene periods appear to have occurred at regular intervals throughout Earth's history. The timing is particularly suspicious. These rapid transition periods seem to follow a rough cycle, occurring approximately every 50 to 100 million years. This suggests a repeating pattern rather than random natural events. Something appears to have periodically occurred that dramatically altered Earth's environment and biology. Think of Earth's geological history like a repeating musical composition. Most of the piece follows natural rhythms and patterns, but certain movements contain sudden crescendos and dramatic key changes that stand out from the background melody. The most detailed evidence comes from the Paleocene-Eocene thermal maximum, which occurred about 56 million years ago. This period shows rapid global warming, ocean acidification, and mass extinction patterns remarkably similar to modern human impacts, yet it took place long before any known intelligent species existed on Earth.
Chemical analysis of rocks from these periods reveals isotopic signatures, synthetic compounds, and metal distributions that are difficult to explain through natural processes alone. These recurring patterns suggest that the rise and fall of technological civilizations may be a regular feature of Earth's long-term evolution.
Silicon solar panels leave distinctive geological signatures that can persist for millions of years. When solar panels degrade, they do not simply disappear. High-purity silicon, rare earth elements, and synthetic materials break down into characteristic chemical patterns. These degradation products possess specific isotopic signatures and molecular structures that are entirely different from naturally occurring silicon compounds. The manufacturing process for solar cells also creates unique environmental signatures. Silicon purification requires enormous amounts of energy and produces distinctive chemical byproducts. These industrial processes leave traces in the atmosphere, groundwater, and surrounding sediments that can be detected long after the original manufacturing facilities have vanished.
Modern renewable energy infrastructure represents the massive global distribution of rare earth elements, synthetic materials, and precision manufacturing. If a previous civilization developed similar technologies, it would have left comparable chemical fingerprints throughout the environment. Think of solar panel manufacturing as a vast chemistry experiment conducted across the entire planet. Every factory, every installation, and every panel that degrades over time contributes chemical signatures that accumulate in the global environment. Some ancient sediment layers show unusual concentrations of ultra-pure silicon and rare earth elements in combinations that closely resemble the byproducts of solar technology. These layers also contain synthetic compounds consistent with large-scale renewable energy production. The geographic distribution of these chemical signatures suggests a coordinated global spread, similar to how our current renewable energy transition is creating worldwide chemical markers. But renewable energy is only one type of technology capable of leaving long-lasting environmental traces. Evolution may be running the same experiment over and over again. Intelligence appears to be an inevitable outcome of evolutionary processes. When nervous systems reach sufficient complexity, problem-solving abilities, tool use, and social cooperation reliably emerge across many different species. This suggests that technological civilizations can arise by following predictable developmental pathways whenever conditions allow.
The recycling theory suggests that Earth periodically produces intelligent species that develop technology, alter the environment, and then disappear due to resource depletion or environmental collapse. After each civilization collapses, Earth gradually recovers and restarts the evolutionary cycle with new species. This process may explain why geological evidence of previous civilizations is so thin and fragmented. Each civilization would exploit different resources, develop different technologies, and leave different types of environmental signatures. But all would follow similar patterns of rapid development, environmental impact, and eventual collapse. Think of civilization development like successive generations of gardeners working the same piece of land. Each gardener plants different crops, uses different tools, and makes different mistakes, but all follow similar patterns of soil manipulation, resource extraction, and environmental modification. The timescales involved make this recycling process almost invisible at the level of individual civilizations. 50 million years is enough time for most environmental damage to heal, new species to evolve, and fresh resource deposits to form. Each new civilization would inherit a planet that appears pristine and untouched.
Archaeological evidence supports this recycling model. The fossil record shows repeated episodes of rapid brain evolution across different lineages, suggesting that intelligence evolved independently multiple times, raising the question of what we might be able to detect from space. Everything we launch into space eventually falls back to Earth. Satellites, space stations, and other orbital debris follow predictable decay patterns driven by atmospheric drag, solar radiation, and gravitational perturbations. Most objects in low Earth orbit re-enter the atmosphere within decades or centuries, burn up, and contribute their materials to the planet's global atmospheric chemistry. This process creates a distinctive signature in atmospheric and sedimentary records. Space-grade materials such as titanium alloys, specialized ceramics, and rare earth magnets have isotopic compositions that differ from terrestrial sources. When these materials burn up during re-entry, they generate unique chemical signatures that become embedded in global environmental records. A technologically advanced civilization would almost certainly develop space technology and launch significant amounts of material into orbit. Even if that civilization collapsed, its orbital infrastructure would continue to fall back to Earth for thousands of years, creating a long-lasting artificial material signature in environmental records.
Human development follows exactly this pattern. Our ancestors developed language, which enabled complex cooperation, which enabled tool development, which enabled agriculture, which enabled civilization, which enabled science, which enabled technology that further increased our intelligence. Think of intelligence evolution like compound interest. Small improvements in cognitive ability produce larger improvements in technology, which create even greater improvements in cognitive development in a continuously accelerating spiral towards superhuman capabilities. Mathematical models suggest that once this spiral begins, it becomes nearly impossible to stop. Intelligence creates tools that make it more intelligent, which create better tools, which make it even more intelligent in an explosive feedback loop. If this process is universal, then every planet that develops life will eventually produce intelligence that follows this same accelerating pattern. The spiral would continue until intelligent species transcend planetary limitations or destroy themselves. Earth may have attempted this intelligent spiral more than once. Each attempt may have reached different levels before ending, which brings us to the most disturbing question.
We can only find the evidence we know how to look for. Our scientific instruments and analytical methods are designed to detect signatures and patterns we already understand. We search for chemical traces that resemble our own industrial processes. We look for artifacts that match our engineering approaches. We identify environmental damage that follows patterns similar to our current impacts. But a truly advanced civilization may have developed technologies completely different from ours. They may have used energy sources that leave no chemical signature. They may have built with materials that integrate seamlessly into natural systems. They may have solved the same problems we face using methods that are invisible to our detection techniques. This creates what philosophers call the detection bias problem. We search for civilizations that think and build like we do, while missing civilizations that think and build differently. Our search methods are like flashlights that illuminate only objects similar to those we already know. Think of our detection techniques like archaeologists using metal detectors to find ancient artifacts. They will locate every metal object in the ground, but completely miss wooden tools, textiles, and organic technologies that may have been far more important to the original civilization. Advanced civilizations may have deliberately minimized their environmental impact to avoid the resource depletion and pollution problems that destroyed their predecessors. They may have developed sustainable technologies that work with natural systems rather than against them.
Such civilizations may be all around us, having learned to live in harmony with planetary systems in ways that render them essentially invisible to our current detection methods. And this leads to the final and most important question. What traces of our civilization will remain 50 million years from now? Future geologists will find a thin layer of unusual chemistry in sediment cores dating to the early 21st century. They will detect plastic molecular fragments, artificial isotopes from nuclear tests, and carbon signatures from fossil fuel combustion.
They will uncover mass extinction patterns, the chemistry of ocean acidification, and metal distributions that clearly indicate technological activity. But will they understand who we really were? Will they recognize our art, our literature, our dreams, our struggle to balance technological power with wisdom? Or will they simply catalog our chemical signatures as those of another intelligence that briefly altered planetary chemistry before disappearing? The Silurian hypothesis forces us to confront our own impermanence. We are not the permanent masters of Earth. We are temporary custodians of a planet that has hosted intelligence before and will likely do so again. Our entire civilization is only a brief chapter in a much longer story.
Think of Earth as an ancient library where countless civilizations have written their stories. Most of these stories have faded into unreadable traces, detectable only through sophisticated analysis of chemical ink stains and patterns of paper decay. Right now, we are writing our own story in this cosmic library. The question is not whether our story will fade like the others. The question is what kind of message we want to leave for the civilizations that come after us. Will they find evidence of a species that learned to live sustainably with planetary systems? Or will they find a series of chemical signatures marking a brief technological brilliance followed by environmental collapse? The choice is still ours, but geological evidence suggests that we may not be the first civilization to face this choice, and we will likely not be the last. See you in our next video. Good night.
Do you think the observable universe shows us everything? We need to think about this a little more deeply. It's as if we're trapped inside a balloon with a diameter of 93 billion light-years. But compared to what lies beyond it, this balloon is only as small as a single dot. Out there are places where universes come into existence like foam. Every second, while cosmic strings split reality in two like invisible swords, white holes give birth to entire galaxies from pure energy. If you've subscribed to and liked what lies beyond the limits of human vision, the journey begins. The number that strains your brain is 93 billion. This is the width that scientists say stretches from one edge of our observable universe to the other. 93 billion light-years of stars, galaxies, and cosmic dust. You might think this represents everything that exists. You would be wrong. This is where things start to get strange. The universe began only 13.8 billion years ago during the Big Bang. Light travels at reality's ultimate speed limit, so how can we see objects that are 93 billion light-years away when the light coming from those objects has had only 13.8 billion years to reach us? It seems mathematically impossible. Yet the answer reveals the first clue about what lies beyond our vision. Space itself has been expanding throughout all this time. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move away from each other, even though they never actually move across the surface of the balloon. The universe works the same way. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us. But during the billions of years it took for that light to reach our telescopes, space expanded and carried that galaxy much farther away. Today, that same galaxy stands 93 billion light-years away from Earth, even though the light shows us how it looked when it was only a few billion light-years away. This expansion created our cosmic balloon. Inside this balloon, we can see roughly 2 trillion galaxies. Every star you observe in the night sky, every galaxy image from the Hubble telescope, every distant quasar and nebula represents objects inside our 93 billion light-year sphere. Scientists call this the observable universe because we can observe it. Everything else remains hidden behind an insurmountable barrier. The barrier is not made of matter or energy. It is made of time itself. Light coming from regions beyond 93 billion light-years has not yet had enough time to cross the expanding space and reach us. Some of this light is still traveling toward Earth right now, carrying images of galaxies we will see for the first time millions of years from now. Here is the mind-bending reality. Our 93 billion light-year balloon actually represents only a tiny fraction of what exists. The true universe stretches far beyond what we can see. Imagine standing on a beach and looking at the horizon. You might see 20 kilometers of ocean, but you know that beyond that horizon lie vast continents and islands. The same principle applies to cosmic space. Somewhere along our cosmic horizon, billions of galaxies continue their ancient dances around black holes. Stellar nurseries give birth to new stars. Planets orbit distant suns, and potentially entirely different regions of space follow completely different laws of physics. What makes this even more incredible is that space continues to expand. Every second, more distant regions move away from us faster than light can travel. We will never see them. They exist in a realm forever beyond our reach. The 93 billion light-year limit is not a wall. It is a window that shows us the nearest room in an infinite cosmic mansion. What blocks our view of the rest of that mansion will shock you even more. 380,000 years after the Big Bang, the universe was engulfed in flames. This was not an ordinary familiar fire. The entire cosmos glowed with such intense light that nothing could escape it. Every photon of light bounced endlessly between particles of matter, like ping-pong balls trapped inside an infinite machine. Space itself glowed with a white brilliance at temperatures exceeding 10,000 degrees. During this era, the universe was like the interior of a star. Free electrons flew around at incredible speeds, constantly colliding with photons and scattering them in random directions. Light could not travel more than a few meters without hitting something. If you could somehow survive inside this cosmic furnace, you would see nothing beyond your immediate surroundings. The universe was completely opaque. Then suddenly, everything changed. As space expanded and cooled, electrons finally slowed down enough to attach to atomic nuclei. For the first time in cosmic history, complete atoms were formed. With no free electrons left to scatter them, light was suddenly set free and began to flow through the universe in perfectly straight lines. This moment of cosmic liberation caused a brilliant burst of light simultaneously in every direction. Scientists call this the surface of last scattering. Every photon that escaped from this burst is still traveling through space today as the cosmic microwave background radiation. This ancient fire is why our observations face an insurmountable barrier. The cosmic microwave background represents the first light that could escape the early universe. We can detect this radiation coming from every direction in space. It surrounds us like a glowing shell shining 93 billion light-years away. This shell marks the absolute limit of what any telescope can ever see. Imagine trying to see through dense fog. The fog blocks the view of everything beyond it. The cosmic microwave background works in exactly the same way, only instead of water vapor, it is made of ancient light from the moment atoms first formed. Everything that happened during the first 380,000 years after the Big Bang remains forever hidden behind this wall of fire. We cannot see the early universe when it was completely opaque. We cannot observe the Big Bang itself. We cannot glimpse the cosmic events that shaped the first few 100,000 years of existence. But what scientists find truly mysterious about this ancient barrier is this. The cosmic microwave background appears almost perfectly uniform in every direction. the temperature varies across the entire sky by only tiny fractions of a degree. This uniformity seems impossible. Regions of space that were never close enough to exchange heat somehow ended up at exactly the same temperature. Imagine filling a bathtub from two faucets at opposite ends. The water from each faucet starts at different temperatures, yet somehow the entire bathtub ends up at exactly the same temperature from one end to the other. This is essentially what happened to the early universe. This uniformity proves that something extraordinary occurred before the wall of fire formed, and that something points directly to the infinite cosmos waiting beyond our reach. Count every star in the night sky, and you will reach roughly 9,000. Count every galaxy visible with the most powerful telescopes, and you reach 2 trillion. Each galaxy contains hundreds of billions of stars. The total number of stars in our observable universe reaches a figure so vast that counting them would take longer than the universe has existed. Yet this inconceivable collection of matter essentially represents nothing when compared to what lies beyond our vision. Think about this carefully. Our observable universe stretches 93 billion light-years in every direction. This creates a sphere of space that contains everything we are likely able to detect. Every telescope image you see, every distant quasar, every galaxy cluster comes from within this sphere. Basic geometry tells us something profound about what this means. If you travel 93 billion light-years from Earth in any direction, you reach the edge of our observable bubble. From that new position, you can observe a completely different sphere of space, also 93 billion light-years across. Some of the galaxies in your new observable universe would overlap with those visible from Earth, but vast regions would remain entirely unique. An alien astronomer sitting at the edge of our observable universe would see roughly 2 trillion galaxies that we can never see from Earth. Move another 93 billion light-years farther, and you would discover 2 trillion more different galaxies. Continue this process in any direction, and you would keep finding new collections of cosmic matter stretching endlessly into space.
Scientists studying the cosmic microwave background radiation have confirmed that space appears flat on the largest scales we can measure. A flat universe extending beyond our observable horizon carries a specific implication. It means that the total universe is either infinite in size or unimaginably larger than what we can see. If the universe is infinite, then there are infinite galaxies beyond our vision. This is not speculation or wishful thinking. The mathematics of cosmic expansion, combined with observations of space's flat geometry, make this conclusion nearly inevitable. Somewhere beyond our cosmic horizon, galaxies identical to the Milky Way orbit around supermassive black holes. Planets exactly like Earth orbit stars exactly like our Sun. The same physical processes that created our solar system have been repeated countless times in regions we will never be able to observe. The strangest part is this. Because space itself is expanding, the galaxies at the very edge of our observable universe are moving away from us at nearly the speed of light. Galaxies just beyond our cosmic horizon are receding faster than light can travel. This means that no matter how long we wait or how powerful our telescopes become, we will never be able to see them. Cosmic expansion behaves like a one-way mirror. We can detect light coming from distant galaxies, but we can never send a signal back to them. They exist in a realm that is causally disconnected from our region of space. Every second, thousands of galaxies drift forever beyond our cosmic horizon as space carries them past the point of no return. Yet, from beyond that horizon, something reaches back and pulls our galaxies toward the darkness. Galaxy clusters should not be moving in the same direction. According to everything we know about cosmic expansion, galaxy clusters should spread out evenly in all directions, like dots on an inflating balloon. Each cluster should move away from us at a speed determined only by its distance. The farther it is, the faster it recedes. When astronomers began measuring the motion of distant galaxy clusters in 2008, this is exactly what they expected to find. Instead, they discovered something that defies explanation. Hundreds of galaxy clusters are flowing toward the same region of the sky at speeds exceeding 3 million kilometers per hour. This massive migration stretches across billions of light years and shows no sign of slowing down. The clusters are moving independently of cosmic expansion, as if they are being pulled by an invisible string by something beyond our vision.
Alexander Kashlinsky and his team at NASA's Goddard Space Flight Center named this phenomenon dark flow. Like dark matter and dark energy, the flow remains completely mysterious. Unlike cosmic expansion, which separates objects evenly in all directions, dark flow drags matter toward a specific patch of sky between the constellations Centaurus and Vela. What makes dark flow truly disturbing is this. Researchers calculated how much gravitational pull would be required to draw galaxy clusters at such enormous speeds. Nothing in our observable universe possesses enough mass to produce this effect. All detectable galaxies, galaxy clusters, dark matter, and even supermassive black holes combined cannot generate the gravitational force required for dark flow. The source of this cosmic tug-of-war must lie beyond the edge of observable space.
Imagine watching leaves floating downstream in a river. You can see the leaves moving, but the waterfall creating the current remains hidden around a bend upstream. Dark flow shows us the cosmic equivalent of those drifting leaves. Galaxy clusters are moving in response to gravitational forces we cannot see. What could be massive enough to pull galaxy clusters across billions of light years? The leading theory involves structures formed during cosmic inflation, the period of rapid expansion immediately after the Big Bang. During inflation, regions of space expanded faster than light and pushed enormous concentrations of matter beyond our cosmic horizon. These structures would resemble nothing in our observable universe. They could contain the mass of millions of galaxy clusters compressed into regions larger than our entire visible cosmos. Or they could represent exotic forms of matter that follow entirely different laws of physics. Some scientists propose even stranger explanations. Dark flow could be caused by gravitational effects leaking in from parallel universes. Or it could be evidence of cosmic strings, one-dimensional defects in space-time stretching across the multiverse. Recent studies have questioned whether dark flow truly exists at all, suggesting the motion may be the result of measurement errors. However, other research teams continue to find evidence for the mysterious cosmic current. The debate continues, but one thing remains certain. If dark flow is real, something unimaginably massive is hidden beyond our vision, and that same cosmic realm may carry lasting scars from collisions with neighboring universes. Deep within the constellation Eridanus, there is a rot in space. This cosmic wound stretches across 1.8 billion light-years and appears as a cold spot in the cosmic microwave background radiation. The region contains about 100 times less matter than it should. It is as if something reached into reality and scooped out a large portion of the early universe. Scientists call this the CMB cold spot, and it should not exist. The cosmic microwave background represents the final glow of the Big Bang, the first light that escaped when the universe became transparent 380,000 years after its birth. This ancient light should show only small temperature variations across the sky. The cold spot violates this rule by displaying a temperature gap far too large to ever be explained by random chance. Imagine throwing a stone into a still pond. Ripples spread outward in perfect circles from the point of impact. Now imagine finding a pond where a section of water has mysteriously vanished, forming a dry patch surrounded by normal water. That dry patch represents how the cold spot appears in the cosmic microwave background data.
The most exotic explanation involves bubble universe collisions. According to the theory of eternal inflation, our universe formed as a bubble of space-time that stopped inflating while the surrounding multiverse continued to expand. Nearby, other bubbles formed, and sometimes, before their walls hardened into separate realities, two bubbles collided. A collision between our universe and a neighboring bubble would create a temperature anomaly, like the one we observe in the cosmic microwave background. The impact would compress matter in some regions while thinning it out in others, leaving permanent imprints visible in the ancient light. Computer simulations of bubble collisions predict that if our universe experienced such impacts, we should see circular patterns in the cosmic microwave background. Research teams analyzed the cosmic microwave background data in search of these telltale signatures. In 2010, scientists thought they had found 4 circular patterns matching the predicted collision signatures. However, statistical analysis suggested that these patterns could be the result of random chance. Much more detailed cosmic microwave background maps from the European Space Agency's Planck satellite showed that the apparent collision signatures were most likely statistical coincidences. Alternative explanations for the cold spot include cosmic voids, regions of space containing very few galaxies. These voids can create temperature drops in the cosmic microwave background through a process called the integrated Sachs-Wolf effect. As photons climb out of the gravitational wells created by matter concentrations, they lose energy. Some researchers suggest that the cold spot represents evidence of extra dimensions or violations of Einstein's general relativity on cosmic scales. Others propose that it may point to problems in our understanding of dark matter and dark energy. The cold spot remains one of the most astonishing features in cosmic microwave background maps. Whether it arises from bubble universe collisions, exotic physics, or unknown cosmic structures, its existence proves that our understanding of the early universe is still incomplete. The mystery deepens when you realize that space itself is moving faster than the ultimate speed limit of the universe. Nothing can travel faster than light except the fabric of reality itself. Einstein's special relativity sets an absolute speed limit for all matter and energy. Nothing with mass can reach the speed of light. Nothing without mass can exceed it. This cosmic speed limit governs every particle, every force, every wave in the universe. Space itself completely ignores this rule. During cosmic inflation, the period immediately after the Big Bang, space expanded exponentially. In less than a second, regions of the universe grew by factors of 10 to the 26th or more. This means a region smaller than a proton inflated to the size of a basketball or larger. This expansion occurred far faster than light could traverse the same distance. Imagine 2 ants standing on opposite sides of a deflated balloon. When you rapidly inflate the balloon, the ants move away from each other. Even though no ant walks across the surface, the expanding balloon separates them faster than they could ever run toward each other. Space expansion works in exactly the same way. Galaxies do not move through space faster than light. Instead, space itself stretches and carries the galaxies along with it. This distinction allows cosmic expansion to violate the light speed limit without breaking the laws of physics. The consequences are astonishing. During inflation, regions of space that were once close enough to exchange light and heat were suddenly separated by distances greater than light could ever cross. This explains why the cosmic microwave background appears so uniform. Before inflation, the entire observable universe was smaller than a grain of sand. Every part could affect every other part and reach the same temperature. After inflation, these regions became causally disconnected. They can no longer exchange information or influence one another because signals between them would have to travel faster than light. Today, cosmic expansion continues to accelerate because of dark energy. Beyond a certain distance, galaxy clusters are moving away from us faster than light can travel. We can still see some of these clusters because their light left them billions of years ago when they were much closer. But any light they emit today will never reach Earth. This creates a cosmic event horizon, similar to the boundary around a black hole. Information from beyond this horizon can never reach us, no matter how long we wait. The horizon currently stands about 16 billion light-years away, and it grows every second. Expansion doesn't only affect our ability to see distant objects, it fundamentally shapes the structure of reality by determining which regions of space can interact with each other and which remain isolated forever. The same expansion process that created our cosmic balloon continues to create new bubbles in the infinite multiverse. Inflation did not end everywhere at once. Imagine the early universe as a vast ocean of space, expanding exponentially in every direction. This cosmic ocean contained a special field called the inflaton, which drove the expansion by stretching space faster than light. For a short time, this field ruled all of reality. Then, in random patches scattered throughout this swelling ocean, the inflaton field began to decay. When the field decayed in our region of space, inflation stopped. The enormous energy that had been driving exponential expansion transformed into matter and radiation. This transformation created a hot, dense plasma that cooled into atoms, stars, galaxies, and everything we observe today. Our observable universe was born. But the inflaton field did not decay everywhere simultaneously. In most regions of the cosmic ocean, inflation continues even today. These regions keep expanding exponentially, stretching space and diluting matter until it becomes nearly empty. Within this eternally inflating background, new bubbles randomly stop inflating and convert their energy into matter. Think of water boiling in a pot. As pockets of steam separate from the surrounding water, bubbles form randomly throughout the liquid. Each bubble represents a separate region with properties different from the surrounding medium. Our universe is one of these bubbles floating in the eternally boiling cosmic pot. The mathematics of this process is striking. Quantum fluctuations in the inflaton field determine when and where bubbles form. These fluctuations are completely random, like radioactive decay. You can calculate the probability of bubble formation, but you cannot predict exactly when or where each bubble will appear.
Here is the crucial insight. Once inflation begins, it becomes eternal. The inflaton field creates new space faster than it can decay into matter. Even if countless bubbles form every second, they occupy only an infinitesimal fraction of the total volume. Most of space remains eternally inflating. This eternal inflation produces an infinite multiverse made of bubble universes. Each bubble forms with its own Big Bang, evolves its own galaxies and stars, and eventually dies when its energy runs out. Meanwhile, the background space continues forever creating new bubbles. Our bubble universe today spans roughly 93 billion light-years. Other bubbles could be smaller, larger, or exist in completely different dimensions. Some could contain more matter than ours. Others could remain almost empty. A few could develop completely different laws of physics during their formation. The space between bubble universes depends on the rate of inflation versus the rate of bubble nucleation. Most bubbles remain forever separated by regions of eternally inflating space. They can never communicate or influence each other across these expanding barriers. However, sometimes two bubbles form close enough that their walls touch before the space between them inflates too much. When this happens, the universes collide, producing rippling effects in both realities. Reality is being split billions of times per second at the smallest possible scale. Approach any seemingly empty patch of space and examine it at distances smaller than the Planck length, roughly 10 to the minus 35 meters. At this scale, the smooth fabric of space-time becomes a sea of quantum foam violently shaking. Virtual particles appear and annihilate each other in time intervals shorter than any clock could measure. This quantum foam does not affect only empty space. It sustains the creation of all universes. During the inflation era, immediately after the Big Bang, quantum fluctuations in the inflaton field determined when different regions would stop inflating and form bubble universes. These fluctuations are completely random and occur everywhere throughout the eternally expanding multiverse. Here is how the process works. The inflaton field has a certain energy value that drives exponential expansion. Quantum fluctuations sometimes push this field above or below its average value in small regions of space. When the field falls below a critical threshold, inflation stops in that region, and its inflation energy converts into ordinary matter and radiation. These quantum events occur randomly across space, according to the laws of probability. In any volume of inflating space, within any short time interval, there is a calculable chance that a fluctuation will trigger bubble formation. Multiply this probability by the infinite volume of eternally inflating space, and you get infinite bubble creation.
Mathematics is astonishing. Every second, countless quantum fluctuations give birth to new bubble universes throughout the infinite multiverse. Each bubble undergoes its own Big Bang, develops its own laws of physics, and evolves its own cosmic structures. Most bubbles remain forever separated by regions of ongoing inflation. Think of quantum foam as cosmic seeds scattered by the wind. Most seeds fall on barren soil and never grow, but occasionally a seed falls on fertile ground and becomes a full ecosystem. Bubble universes are cosmic ecosystems grown from quantum seeds in the inflating multiverse. The consequences extend far beyond simply creating universes. If quantum fluctuations produce infinite bubble universes, then every possible set of physical laws must exist somewhere in the multiverse.
Bubbles where gravity pushes instead of pulls. Universes where electromagnetism works in reverse. Realities where time flows backward or simultaneously in multiple directions. Some bubbles develop physical constants perfectly tuned for life. Others become sterile wastelands where stars never form or matter never clumps together. A few may evolve exotic physics beyond anything we can imagine. The anthropic principle suggests that we observe only a life-permitting universe because we cannot exist in sterile alternatives. Among infinite possibilities, conscious observers like humans can only emerge in rare bubbles where conditions allow complexity to develop. This means that near-identical copies of you exist in bubble universes with almost identical histories. There are variations where you made different choices or history developed differently. From time to time, neighboring bubbles in this infinite multiverse collide with cosmic consequences. Here is the equation that proves the existence of the infinite universe. P equals 1 minus e to the negative t. This simple mathematical formula defines the probability that a bubble universe will form in any region of inflating space during a given time interval. As time approaches infinity, the probability approaches 100%. Given infinite time and infinite space, bubble formation becomes absolutely certain. The mathematics of eternal inflation works like a cosmic gamble where the house always wins. Imagine flipping a coin forever. Each flip has a 50% chance of landing tails. After enough flips, seeing tails at least once is guaranteed. Now imagine flipping the coin infinitely for infinite time.
Although each flip remains unpredictable, you will see tails infinitely many times. Bubble universe creation follows the same principle. Quantum fluctuations constantly flip coins throughout the inflating multiverse. Each fluctuation has a tiny probability of triggering bubble formation. Given infinite space and infinite time, bubble creation becomes inevitable and infinite. The key insight comes from understanding exponential growth. During inflation, the volume of space doubles repeatedly in fractions of a second. This doubling continues forever in regions where inflation never ends. Even if bubble formation has a very low probability, the exponentially growing volume of inflating space allows bubbles to continue forming at an accelerating rate. Think of bacteria multiplying in a petri dish. Each bacterium has a small chance of dividing in any time interval. At first, division happens slowly because there are few bacteria. As the population grows, more bacteria means more chances to divide. Eventually, the population explodes exponentially. Eternal inflation works similarly. Every region of inflating space has a small chance to produce a bubble universe. As inflation creates more space, there are more regions where bubble formation can occur. Even though the per-region probability stays constant, the bubble creation rate accelerates exponentially.
Here is where the math gets mind-bending. Andre Linde's chaotic inflation model shows that bubble universes form with random physical properties. The values of fundamental constants, like the strength of gravity, the mass of the electron, and the speed of light, are determined randomly during the formation of each bubble. This randomness allows an infinite variety of physics to exist across the multiverse. Some bubbles form with such weak gravity that matter never clumps into galaxies. Others develop with such strong electromagnetic forces that atoms cannot form. A tiny fraction evolves with perfectly balanced constants for complexity, life, and consciousness. The anthropic principle explains why we observe apparently fine-tuned physics. Among infinite random possibilities, conscious observers can only arise in the rare bubbles where conditions allow their existence. We observe a life-friendly universe because in the alternatives, we could not exist. Mathematical models also predict the frequency of bubble collisions. When two bubbles form close enough, their expanding walls eventually touch and interact. These collisions leave lasting imprints in our cosmic background radiation that we could detect. When universes collide, both realities remember it. Imagine two soap bubbles floating in the air, each containing its own miniature ecosystem. When the bubbles touch, their surfaces merge and create a permanent connection. The collision sends ripples across both bubble walls, forever preserving evidence of the impact. Universe collisions work similarly, except the stakes include all of reality. During eternal inflation, bubble universes form randomly throughout the expanding multiverse. Most bubbles remain forever separated by inflating regions of space, far beyond any chance of contact. But when two bubbles nucleate close enough in space and time, their expanding walls eventually meet. The collision produces gravitational waves that propagate across both bubble universes. These waves carry specific signatures depending on the collision angle, the relative speeds of the bubbles, and differences in their physical properties. Most importantly, the waves leave permanent imprints in each universe's cosmic microwave background radiation. Here is how scientists could detect evidence of a bubble collision in our own universe. When our bubble universe collided with a neighbor, the gravitational waves from that impact would have traveled at the speed of light through our space. Those waves would have reached the surface of last scattering, the moment when our universe became transparent and released the cosmic microwave background. Collision waves would have produced temperature fluctuations in the cosmic microwave background in a very specific pattern. Unlike random fluctuations, collision signatures appear as concentric rings centered on the direction of impact. The size and intensity of these rings depend on the collision parameters. Matthew Johnson and his team from the Perimeter Institute developed computer simulations to predict exactly how collision signatures should appear. They created detailed templates showing how different types of collisions would look on cosmic microwave background maps. In 2010, researchers announced that they had found 4 potential collision signatures in NASA's Wilkinson Microwave Anisotropy Probe data. Each signature appeared as a series of concentric rings with temperature variations matching theoretical predictions. The discovery suggested that our universe had collided with 4 different neighboring bubbles. However, follow-up analyses revealed problems with this interpretation. The European Space Agency's Planck satellite, which provided much more detailed cosmic microwave background maps, showed that the apparent collision signatures were most likely statistical coincidences. Random temperature fluctuations can sometimes, completely by chance, create ring-like patterns. The search for collision signatures continues with increasingly advanced methods. New analysis techniques can examine multiple statistical features simultaneously to distinguish real collision traces from random patterns. Finding definitive evidence of bubble collisions would revolutionize our understanding of cosmic reality. Such a discovery would prove that our universe is part of a vast multiverse and that other realities exist beyond our cosmic horizon. Evidence of collisions would also reveal how bubble universes form and interact, providing our first observational window into the physics of the multiverse. Meanwhile, the collision research revealed something even stranger: bubble universes where the fundamental laws of nature work completely differently. Alternatively, imagine a bubble where gravity is 10,000 times weaker. Matter would never clump together enough to form stars. Hydrogen and helium would drift through space forever as thin, cold gas. No nuclear fusion, no heavy elements, no planets, no chance of life. Electromagnetism offers equally dramatic variations. Make electromagnetism slightly stronger and atomic nuclei would fly apart because positive charges could not hold together. Make it weaker and electrons would spiral into atomic nuclei, erasing chemistry entirely. Some bubble universes develop with completely different particle physics. In these realities, the fundamental building blocks of matter follow alien rules. Particles that attract in our universe repel in theirs. Forces that weaken with distance here may strengthen with separation there. The most exotic possibilities include universes with different numbers of spatial dimensions. We live in a reality with 3 spatial dimensions plus 1 time dimension. Other bubbles could evolve with 4, 5, 10, or even hundreds of spatial dimensions. Movement in higher dimensional space would be completely alien to us. Objects could approach from directions that do not exist in our 3-dimensional reality. A sphere in 4-dimensional space would mysteriously appear and disappear as it passes through our 3-dimensional slice. String theory suggests that bubble universes with different numbers of compact dimensions could be common. These extra dimensions are curled up so tightly that we cannot detect them, but they influence the properties of fundamental forces and particles.
Some theoretical physicists suggest that advanced civilizations in other bubble universes could manipulate their local physics. By understanding the relationship between space-time geometry and the laws of physics, these beings could potentially alter fundamental constants in limited regions. Such physics manipulation would enable technologies that appear magical from our perspective. Civilizations could create regions where gravity runs backward, time flows at different rates, or matter transforms according to different rules. The anthropic principle suggests that while most bubble universes remain sterile, only a tiny fraction develop conditions suitable for complexity and consciousness.
This means that intelligent life represents an incredibly rare and valuable phenomenon across the infinite multiverse. But our bubble universe may not be the only place where exotic physics exists beyond our horizon. Some theories predict that reality-bending objects could exist here in our observable cosmos. Somewhere in the universe, there are evil twins of black holes that create instead of destroy. While black holes swallow everything that comes too close, white holes represent the opposite phenomenon. These theoretical objects expel matter and energy so violently that nothing can approach their surfaces. Like cosmic geysers, they spew material into space on the scale of entire galaxies. The same mathematics that predicts black holes also predicts white holes. Einstein's general relativity equations describe how massive objects curve spacetime. When you solve these equations for a black hole, you get two solutions. The first describes matter falling inward through an event horizon toward a central singularity. The second describes matter exploding outward from a central point that nothing can reach. Black holes represent the inward solution. White holes represent the outward solution. Imagine watching a film of matter falling into a black hole and then playing that film backward. The reversed film would show material launching outward from a central point and accelerating away at increasing speeds. That is essentially what a white hole would look like. White holes could explain some of the most energetic phenomena in the observable universe. Gamma-ray bursts release more energy in seconds than our Sun produces over its 10 billion-year lifetime. Quasars shine with the brightness of 1 trillion stars from regions smaller than our solar system. Active galactic nuclei accelerate particles to nearly the speed of light and launch them for millions of light-years. Current theories explain these extreme objects through matter falling into supermassive black holes. The infalling material heats up before crossing the event horizon and emits enormous amounts of energy. But some scientists wonder whether white holes could provide an alternative explanation for cosmic intensity. A white hole would be fundamentally unstable in our universe. Any material approaching the object would prevent matter from being ejected. The white hole would immediately collapse and turn into a black hole. This instability could explain why astronomers have never observed a definite white hole signature. However, white holes could exist in other bubble universes with different physics. In realities where certain symmetries work differently, white holes could be stable and common. These objects could serve as cosmic factories, continuously producing the matter and energy that build galaxies. Some cosmologists suggest that the Big Bang itself was a white hole event. Our entire observable universe may have burst out of a single point in a higher dimensional space and created all the matter and energy we observe today. This white hole Big Bang model offers an alternative to standard inflation theory. The most speculative theories propose that black holes in our universe could connect to white holes in other realities. Material passing through a black hole's event horizon could emerge from a white hole in a parallel bubble universe. This would create cosmic tunnels connecting separate regions of the multiverse. While white holes remain theoretical, other exotic structures definitely existed in the early universe and could cross through space today. Imagine a crack in reality, so thin you could never see it, yet so massive that 2.5 centimeters of it would weigh more than Mount Everest. These cosmic strings could stretch across the entire observable universe as one-dimensional defects in space-time formed during the first fractions of a second after the Big Bang, when the universe underwent rapid phase transitions that broke fundamental symmetries. Think of water freezing into ice. As liquid water cools and crystallizes, cracks sometimes form between different crystal regions. These cracks represent defects where the crystal structure is not perfectly aligned. The early universe underwent similar phase transitions as various forces separated from a unified field.
Cosmic strings formed along the boundaries where different regions of space developed different properties during these transitions. The physics of cosmic strings defies everyday experience. Each string would be no wider than a proton, yet contain incredible density. A single kilometer of cosmic string would weigh more than Earth. The gravitational field around such an object would be dense enough to bend light and distort time. If cosmic strings exist, they would be nearly indestructible. Unlike ordinary matter, which can be broken with enough force, cosmic strings are topological defects. You cannot destroy them without fundamentally altering the structure of space-time. They persist as lasting traces, marking the violent birth of our universe. Cosmic strings would also be incredibly long. The shortest string would stretch from one edge of the observable universe to the other. Most strings would extend into regions far beyond our cosmic horizon that we could never see. Some could form closed loops smaller than galaxies, while others could connect our bubble universe to neighboring realities. The motion of cosmic strings produces gravitational waves. As strings vibrate, oscillate, and occasionally intersect, they generate ripples in space-time that could be detected by instruments like LIGO. These gravitational wave signatures would differ from those of black hole or neutron star collisions. Some scientists already think they may have detected cosmic string signatures. The nanograv collaboration measures tiny timing variations in pulsars, ultra-precise cosmic clocks that emit radio pulses like lighthouse beams. The latest data show patterns that could be caused by gravitational waves produced by cosmic string networks. Cosmic strings could also influence the formation of galaxies and large-scale cosmic structure. Their immense gravitational fields would pull ordinary matter and dark matter, creating linear overdensities along string paths that seed galaxy formation. If cosmic strings connect our bubble universe to other realities, they could allow limited information transfer between them. Electromagnetic signals could potentially travel along string networks and carry messages between bubble universes that would otherwise be causally disconnected. The search for cosmic strings continues using multiple observational methods. Gravitational wave detectors, cosmic microwave background analyses, and large-scale structure surveys all provide different ways to hunt for string signatures. Finding cosmic strings would prove that reality contains structures beyond our imagination, extending into dimensions we are only beginning to understand. Two black holes rotating in perfect synchronization could tear a tunnel in the fabric of reality. This is not science fiction. Mathematical solutions to Einstein's equations predict that under very special conditions, the extreme curvature of space-time around massive objects could create shortcuts between distant regions of the universe. Scientists call these cosmic tunnels wormholes. The engineering requirements are astonishing. You would need two electrically charged black holes positioned at exactly the right distance. The electric charges would have to be perfectly balanced to prevent the black holes from pulling together or repelling and flying apart. Then you would need cosmic strings. These one-dimensional defects in space-time serve as cosmic scaffolding to keep the wormhole tunnel open. Remember, cosmic strings are thinner than protons, but denser than neutron stars. The incredible tension could theoretically prevent the wormhole from collapsing under its own gravitational stress. The resulting structure would create a stable tunnel connecting 2 points in space-time. You could enter one mouth of the wormhole and emerge instantly from the other mouth. No matter how far apart they are, the travel time through the tunnel would be essentially zero. This is where bubble universes come into the picture. If cosmic strings formed during the inflationary era, they could stretch across the ever-expanding regions of space from one bubble universe to another. A wormhole using these inter-bubble strings would create a direct connection between separate realities.
Imagine passing through such a tunnel and emerging in a universe with completely different physics. Gravity could run backward, electromagnetic forces could operate in reverse, or time itself could flow at a different rate. The experience would be like walking through a door from one dream into another. Unfortunately, even theoretical wormholes face serious stability problems. The cosmic strings that keep them open would gradually lose energy through gravitational wave radiation. As the strings shrink, the wormhole tunnel would collapse. Most models predict a full collapse within microseconds. However, some theoretical frameworks suggest that quantum effects or exotic matter with negative energy could stabilize wormholes for longer periods. These stabilized tunnels could naturally exist in regions of space where cosmic inflation created the right conditions. Advanced civilizations in other bubble universes might have developed technology to create and maintain artificial wormholes. Such technology would allow them to explore distant regions of their own universe or even visit neighboring bubble realities. If stable wormholes exist, they solve the cosmic isolation problem created by faster-than-light expansion. Bubble universes that would normally remain forever separated could maintain communication and travel connections through networks of wormholes. The implications are profound. A cosmic internet connecting multiple realities could allow the exchange of information, matter, and energy between bubble universes with vastly different properties. Scientists continue to search for wormhole signatures in gravitational wave data and cosmic microwave background observations. Finding evidence of these cosmic tunnels would prove that the barriers between realities are not absolute. However, some theoretical physicists suggest that parallel realities may be much closer than we imagine, with time itself running backward. Our mirror twin runs backward in time for every second that flows forward in our universe. This mirror reality was created at exactly the same moment as our universe during the Big Bang. Both realities share the same starting point but evolve in opposite temporal directions. While we experience time flowing from the past to the future, our mirror universe experiences time flowing from the future to the past. The concept arises from fundamental symmetries in physics. Most physical laws work equally well whether time moves forward or backward. Drop a ball and it falls. Reverse the process and the ball bounces up from the ground. Both directions obey the laws of gravity and motion. The mathematical equations do not prefer one temporal direction over the other. However, the second law of thermodynamics breaks this symmetry. Entropy, or disorder, always increases over time in our universe. Hot coffee cools down, never the opposite. Broken glass never spontaneously reassembles. Dead organisms do not return to life. Sean Carroll and other cosmologists proposed that the Big Bang created two universes with opposite arrows of entropy. In our universe, entropy increases as time moves forward. In the mirror universe, entropy increases as time moves backward relative to our frame of reference. Imagine watching a film of someone's life played in reverse. You see them getting younger, forgetting information, and eventually becoming a baby. From our perspective, the mirror universe appears to run backward, but conscious beings in that reality would experience time normally. They would see their universe evolving forward, while our universe appears to run in reverse. This creates a profound symmetry in cosmic evolution. Both universes begin at the moment of the Big Bang with low entropy and evolve toward higher entropy states. The total entropy of the combined two realities remains balanced throughout cosmic history. The mirror universe contains antimatter instead of ordinary matter. Antiparticles have opposite electric charges and magnetic properties compared to normal particles. When matter and antimatter meet, they annihilate each other and release pure energy. The stars in the mirror universe would be made of antihydrogen, anti-helium, and other antimatter elements. These anti-stars would shine as brightly as normal stars and follow the same nuclear fusion processes. Anti-planets would orbit anti-stars in solar systems that, from a distance, look identical to ours. If intelligent life evolved in the mirror universe, those beings would be made of antimatter. While experiencing their reality as completely normal, they would perceive our matter-based universe as exotic and alien. The mirror universe theory explains several cosmic mysteries. It accounts for the apparent absence of antimatter in our observable universe. It provides a natural explanation for the arrow of time without requiring special initial conditions. Some scientists speculate that dark matter in our universe could actually be ordinary matter from the mirror universe. Gravity could connect the two realities while electromagnetic interactions remain separate. The mirror universe represents just one example of parallel realities that could exist in higher dimensional spaces beyond our three-dimensional perception of curved space, like a saddle surface extending into infinity.
Space curves inward like a saddle surface extending into infinity. Most people imagine space as a flat sheet stretching in all directions with straight lines. Einstein's general relativity reveals that massive objects curve space, creating the phenomenon we experience as gravity. But the overall shape of space itself depends on the total amount of matter and energy it contains. Our universe appears to have flat geometry on the largest scales. Parallel lines remain parallel across cosmic distances. The angles of triangles add up to exactly 180 degrees. This flat space extends throughout our observable universe and likely continues beyond our cosmic horizon. However, other bubble universes could evolve with completely different spatial geometries. Imagine a universe with negative curvature, where space curves outward like a hyperbolic saddle. In this reality, parallel lines would gradually diverge as they extend into distance. The angles of triangles would add up to less than 180 degrees. The shortest distance between 2 points would follow a curved path instead of a straight line. Navigation in negatively curved space would be deeply disorienting. Objects that appear to move in straight lines would actually follow curved trajectories. Light rays would bend away from each other instead of traveling in parallel bundles. The familiar geometry of three-dimensional space would be replaced by strange mathematical relationships.
The implications for cosmic structure would be dramatic.
In flat space, matter clumps together under gravitational attraction to form stars, galaxies, and clusters. Negative curvature would continuously stretch distances between objects, working against this gravitational clustering. It would be difficult for galaxies in a negatively curved universe to form and maintain their spiral structures. Star systems would be less stable because orbital mechanics would follow hyperbolic paths instead of elliptical ones. The cosmic web of dark matter that connects galaxy clusters in our universe might never develop. Advanced civilizations in negatively curved bubble universes would need to develop completely different technologies. Their mathematics would be based on hyperbolic geometry rather than Euclidean principles. Their understanding of physics would include curved space effects in every calculation. Some theoretical models suggest that regions of negative curvature could exist within our own universe at scales smaller than we can currently detect. These hyperbolic regions could be created by exotic matter with unusual gravitational properties or remnants of cosmic inflation. Negative curvature could also exist in extraspatial dimensions that we cannot directly perceive. String theory predicts that reality may contain 6 additional spatial dimensions so tightly curled up that they appear as points from our three-dimensional perspective. If some of these extra dimensions have negative curvature, they could affect the behavior of fundamental forces and particles in ways that seem mysterious from our limited dimensional viewpoint. The geometry of space is just one of many variables that could differ significantly in the infinite inflation machine that produces infinite realities.
As you read this sentence, trillions of new universes have begun to exist. The cosmic inflation that created our bubble universe never actually ended. It continues across the infinite multiverse, constantly stretching space and giving birth to new realities at an accelerating pace. This infinite inflation machine operates on simple rules that produce unlimited complexity. Here's how the machine works. The inflaton field exists everywhere throughout the multiverse, stretching space faster than the speed of light and continuing to expand exponentially. Quantum fluctuations randomly push this field above and below its average value in small regions scattered throughout the expanding volume. When quantum fluctuations push the inflaton field below a critical threshold, inflation stops in that region. The field's energy converts into matter and radiation, creating a hot Big Bang that cools over time, eventually forming stars, galaxies, and potentially life. Meanwhile, inflation continues in the surrounding regions. The volume of inflating space grows exponentially, creating more locations where quantum fluctuations can trigger new bubble formation. This process feeds itself in an endless cosmic reproduction cycle.
Numbers are incomprehensible. Every second, the total volume of inflating space is multiplied by powers of 10 raised to unimaginable forces. Within this explosively growing volume, quantum fluctuations create new bubble universes at rates that dwarf human imagination. Imagine bacteria multiplying in an infinite petri dish that doubles in size every second, no matter how fast the bacteria reproduce. The space available grows even faster. The inflation machine works similarly, creating a continuous stream of new cosmic real estate where bubble universes can form. Each bubble universe lives and dies in cosmic isolation. When a bubble forms, the surrounding space inflates away from it faster than light. The bubble cannot send signals to other bubbles, nor can it receive information from the wider multiverse. Each reality evolves independently according to its own randomly assigned physical laws. But the infinite inflation machine ensures that every possible combination of physics eventually occurs somewhere in the infinite multiverse. Universes with 10 spatial dimensions, realities where time branches in multiple directions, bubble cosmoses where consciousness creates matter through observation. The machine also produces exact copies of our universe with identical histories. Quantum mechanics limits the number of possible arrangements of matter in any finite volume. With infinite bubble universes, identical copies become mathematically inevitable. Somewhere beyond our cosmic horizon, another Earth exists, orbiting another sun in another galaxy in another bubble universe. A copy exists with identical continents, identical life forms, and identical people living identical lives. The infinite inflation machine guarantees that this cosmic multiplication happens not just once, but infinitely many times. Every possible variation of history, every alternative choice, every different outcome occurs in the sea of infinite bubble realities. Andrea Linde, one of the founders of inflation theory, calls this the ultimate Copernican revolution. We are not the center of the universe, and our entire universe is not the center of existence. The machine creates realities so exotic that instead of our familiar 3, they exist with 10 spatial dimensions. So bizarre that moving through 10-dimensional space could drive you insane in seconds. We are trapped in 3 spatial dimensions: length, width, and height. Every object you see, every direction you can point, every path you can walk exists within this 3-dimensional prison. Your brain evolved to navigate only 3 spatial dimensions plus 1 time dimension. String theory demands that reality contains at least 10 dimensions in total. There are 6 extra spatial dimensions tightly curled up at every point in space, so small that we cannot detect them directly. Imagine looking at a garden hose from afar. The hose appears as a one-dimensional line. Approach it and discover that the line actually has width and circumference. These are hidden dimensions that only become noticeable at smaller scales. The extra dimensions in string theory work similarly. At every point in our three-dimensional space, there are 6 additional directions perpendicular to length, width, and height. These directions point in ways your mind cannot visualize because human brains lack the neural architecture to think in higher dimensions. Other bubble universes could have developed with these extra dimensions unfurled at microscopic scales. Imagine a reality where objects can move in not 3, but 10 full spatial dimensions. A sphere in 10-dimensional space would appear in our universe as a mysterious series of 3-dimensional slices changing over time. The full object would remain invisible because most of its volume extends into dimensions we cannot perceive.
10-dimensional space-specific beings would have sensory organs that detect light, sound, and matter from directions that do not exist in our reality. They could approach you from dimensional angles that would make them appear to materialize out of nowhere and vanish into nothingness. The physics of 10-dimensional space would be correspondingly alien. It would spread the influence of gravity across 10 dimensions instead of 3, making it much weaker over any distance. Stars might not form because gravity could not overcome thermal pressure. Galaxies would be impossible because gravitational attraction would be too diffuse. However, other forces could dominate in higher dimensions. Electromagnetic interactions or exotic forces predicted by string theory could shape matter into structures beyond our imagination. These structures could follow geometric patterns based on 10-dimensional symmetries. The mathematics of higher dimensional geometry produces shapes with properties that seem impossible from our 3-dimensional perspective. Inside-out turning hyperspheres, Klein bottles with no inside or outside surface, and mathematical objects that exist in multiple locations simultaneously. Advanced civilizations in 10-dimensional bubble universes would manipulate matter using principles beyond our comprehension. By using extra dimensions as data storage space, they could store infinite information in finite volumes. They could travel instantly between distant locations by taking shortcuts through higher dimensional space. Some string theorists propose that our 3-dimensional universe exists as a membrane floating in higher dimensional space. Other membranes could exist parallel to ours, separated from us by tiny distances through extra dimensions, while still being billions of light-years away in our familiar 3-dimensional space.
Gravity can spread through all dimensions, meaning massive objects in parallel universes could affect matter in our reality. This could explain part of the missing mass astronomers attribute to dark matter. The geometry of space represents only one aspect of how bubble universes could differ from our reality in ways that would challenge the foundations of existence. Empty space weighs more than all the matter in the observable universe. This statement seems impossible, but quantum mechanics proves it to be true. What we call the vacuum is actually boiling with virtual particles that appear and disappear in time intervals shorter than any measurement can detect. These quantum fluctuations create a background energy that fills every cubic centimeter of space. Quantum vacuum fluctuations must have an enormous energy density. According to theoretical calculations, if you sum up all the energy of virtual particles in a volume the size of a coffee cup, the total would exceed the combined mass energy of all visible stars and galaxies. Here is the cosmic mystery. This quantum vacuum energy should create a gravitational field strong enough to bend space-time into a tiny ball. Our universe should have collapsed before the first atoms formed. Instead, we observe an almost flat universe expanding for nearly 14 billion years. something must be canceling the vacuum energy to prevent cosmic collapse. Scientists call this the cosmological constant problem, and no one knows the solution. Different bubble universes may have different relationships between quantum vacuum energy and space-time curvature. In some realities, vacuum energy may remain uncancelled and create universes that collapse instantly into infinitely dense points. Other bubbles may evolve with negative vacuum energy, causing space to expand even faster than our cosmic inflation. The most interesting possibility includes bubble universes where quantum vacuum energy fluctuates randomly across space and time. Imagine a reality where empty space sometimes weighs more than matter and sometimes less. Regions with positive vacuum energy would curve space inward like invisible black holes. Regions with negative vacuum energy would curve space outward like cosmic anti-gravity wells. In such a universe, matter and energy would travel through space-time regions with constantly changing gravitational properties, following strange trajectories. Stars could spontaneously speed up or slow down as they encounter vacuum energy fluctuations. Planets might suddenly find their orbits reversed or bent into impossible configurations. Advanced civilizations in variable vacuum energy universes would need technologies that adapt to constantly changing physical laws. Spaceships would require navigation systems that account for random gravitational anomalies. Cities would need structures that remain stable despite the fluctuating curvature of space-time.
Some theoretical physicists propose that consciousness could influence quantum vacuum fluctuations through the observer effect. In bubble universes where this effect is stronger, intelligent beings could potentially manipulate local spacetime by focusing their awareness on specific regions. This idea creates realities where physics directly responds to observation, meditation can change gravity, and collective consciousness can reshape the fundamental properties of space. Such observer-dependent physics may exist in bubble universes formed inside the event horizons of black holes in other realities. Every black hole in our universe could be pregnant with an entire cosmos. When a massive star collapses, it creates a region of space-time so warped that not even light can escape. We see this as a black hole, a cosmic vacuum cleaner that devours everything around it. However, mathematical analysis of what lies inside the event horizon suggests something extraordinary. The collapsing matter does not simply crush into an infinitely dense point. Instead, it could trigger a new Big Bang that creates an expanding universe inside the black hole. This inner universe would be completely disconnected from our reality. No information can travel outward from the event horizon of a black hole. From our perspective, the black hole appears to freeze time at the moment of collapse. We cannot observe what is happening inside. However, from the perspective of the matter falling into the black hole, time continues normally. The collapsing material experiences extreme tidal forces that stretch and compress space into exotic forms. Under these conditions, the fabric of space-time itself could undergo phase transitions that trigger inflation. Think of a seed sprouting inside a protective shell. Outside the shell, everything appears unchanged. Inside, a complex organism grows and develops into full maturity. Black hole universes work similarly, with entire realities evolving inside event horizons that appear motionless to outside observers. The mathematics of this process suggests that black hole universes could become much larger than the black holes that contain them. It seems impossible until you remember that space-time itself is curved. The interior of a black hole represents a topologically disconnected region of space-time separate from our universe. Lee Smolin proposed that black hole universes could explain the apparent fine-tuning of physical constants in our reality. If universes that produce more black holes also generate more offspring universes, then natural selection would favor physics that creates stars massive enough to collapse.
Our universe produces billions of black holes through stellar evolution. Each black hole could give birth to a pocket universe with slightly different physical laws. Over cosmic time, this reproductive process could fill the multiverse with realities optimized for black hole formation. Generational universes may have stronger gravity, making massive stars more common. Or they may have different nuclear physics that allow stars to grow larger before collapsing. Each generation becomes better adapted to creating black holes. This evolutionary cosmology suggests that we live in a universe descended from countless generations of black hole ancestors. Our physical laws exist because they were successful at creating black holes in previous cosmic generations. Some bubble universes may have developed physics so efficient at producing black holes that they resemble vast stellar nurseries. These realities could contain billions of times more black holes than our universe. Each one potentially births new pocket cosmoses. While black holes create pocket universes through gravitational collapse, massive structures beyond our cosmic horizon could be pulling matter through entirely different mechanisms. Something with the mass of 10,000 Milky Way galaxies is pulling our entire region of space toward the Hydra constellation. The Milky Way is moving at over 1 million kilometers per hour in space in a direction that cannot be explained by cosmic expansion alone. Our galaxy, along with thousands of neighboring galaxies in the Local Group and the Virgo cluster, is flowing toward an invisible gravitational anchor about 250 million light-years away. Astronomers call this cosmic magnet the Great Attractor. Here is what makes the Great Attractor truly mysterious. When scientists point their telescopes toward the Hydra constellation, where this massive object should be located, they find a region of space that looks relatively normal. Galaxy clusters are there, but nothing is massive enough to gravitationally dominate our local region of the universe. The object is partially hidden behind the zone of avoidance, a band in the sky where dust from our own galaxy blocks our view of distant objects. But even accounting for this cosmic dust curtain, observations still fail to reveal enough matter to explain the gravitational effects of the Great Attractor. Scientists discovered that the Great Attractor itself is being pulled toward an even larger structure called the Shapley Supercluster. This collection of massive galaxy clusters contains the gravitational equivalent of 1 quadrillion suns concentrated in a region spanning hundreds of millions of light-years. But the cosmic hierarchy does not end there. The latest mapping of galaxy motions reveals that most of our local region is participating in an even larger flow toward an immense structure lying beyond our cosmic horizon. Scientists call this dark flow, and they suggest that the Great Attractor is only a small component of a cosmic architecture far beyond what we can see. It is like swimming downstream toward the edge of a waterfall. You can feel the current pulling you forward, but you cannot see the waterfall itself because it lies around a bend farther down the river. The Great Attractor and dark flow operate similarly. We can measure the gravitational effects on local galaxies, but the source of this pull may extend into regions of space that lie forever beyond our observation. Some cosmologists suggest that the Great Attractor could be a massive concentration of dark matter left over from cosmic inflation. During the inflationary era, quantum fluctuations may have created density variations on scales far larger than our observable universe. We observe only a small portion of these cosmic megastructures. Alternative theories propose that the Great Attractor could be evidence of extra-dimensional physics. Massive objects existing in higher dimensions could remain invisible to our telescopes while exerting gravitational influence on our three-dimensional space. The possibility of invisible extra-dimensional objects points to bubble universes, where the foundations of quantum reality operate according to entirely different rules.
In some bubble universes, opposite charges attract while like charges repel. Wait, that is exactly how electromagnetism works in our universe. Let me correct the fundamental misunderstanding in your perception of reality. In some bubble universes, like charges attract while opposite charges repel. This reversal would make the formation of atoms impossible. Positively charged protons in atomic nuclei would repel each other with incredible force. No force would be able to hold them together long enough for electrons to orbit around them. Chemistry would be impossible. Molecules would never form. Life as we know it could not exist. However, reversed electromagnetism could allow the development of entirely different types of matter. Imagine particles with the same electric charge coming together in stable configurations. These same charge assemblies could form crystalline structures held together by gravitational attraction, while electromagnetic repulsion prevents them from collapsing completely. The balance between gravitational attraction and electromagnetic repulsion could create exotic matter with properties unlike anything in our universe. These structures could be hollow with complex internal geometries shaped by competing forces. Large-scale cosmic structures in reversed electromagnetism universes would develop differently than those in our reality. Cosmic plasma would behave oppositely, potentially creating galactic magnetic fields that focus matter instead of dispersing it. Stars could form through electromagnetic attraction instead of gravitational collapse. Other bubble universes could develop with electromagnetic forces millions of times stronger or weaker than ours. Stronger electromagnetism would make atoms larger and chemical bonds more energetic. Molecular structures could become incredibly complex, potentially allowing exotic forms of chemistry and biology. Weaker electromagnetism would create atoms so small that quantum effects would dominate all chemical interactions. Matter would behave more like a quantum fluid than a collection of discrete particles. Such universes could support forms of intelligence based on quantum coherence rather than classical computation. The strangest possibility includes bubble universes where electromagnetism splits into multiple different forces. Instead of a single electromagnetic field, these realities could contain separate electric and magnetic forces that operate independently. Civilizations in such universes would develop technologies based on manipulating electric and magnetic fields separately. They could create materials that respond to electricity but ignore magnetism, or vice versa. Their electronics would follow engineering principles completely alien to our understanding. Some bubble universes could contain entirely new fundamental forces that do not exist in our reality. These exotic forces could bind matter into stable structures that would be impossible under our physics. Advanced beings in these universes could harness forces beyond our imagination to manipulate matter at will, travel instantaneously across cosmic distances, or convert energy into complex patterns of information. The diversity of possible electromagnetic behaviors represents only one aspect of the infinite variety expected across the multiverse. This electromagnetic diversity could be connected through networks of dark matter that span multiple bubble realities at once. Dark matter could be a cosmic internet linking infinite realities together. Across our observable universe, galaxies cluster along vast networks of invisible matter filaments that stretch for billions of light years. These dark matter structures form a cosmic web that connects galaxy clusters and guides the flow of ordinary matter through space. We can map this web by observing how it bends the light coming from distant galaxies. Dark matter filaments appear as massive highways that channel matter and energy across cosmic distances. Without this skeleton, galaxies would drift randomly through space instead of organizing into beautiful, large-scale structures. But here is the revolutionary possibility.
the cosmic web could extend beyond our observable universe into other bubble realities. If dark matter formed during cosmic inflation before the bubble universe is separated, then the same network of dark matter filaments could spread across multiple realities at once. This would create physical connections between bubble universes that would otherwise be causally isolated. Think of underground fungal networks that connect trees in a forest. Individual trees appear separate above ground, but they are actually connected through invisible root systems that allow them to share nutrients and information. Bubble universes could be linked through similar dark matter networks. Gravitational effects could propagate along these dark matter filaments from one bubble universe to another. This could explain mysterious phenomena like the dark flow, where galaxy clusters in our universe appear to be pulled toward massive structures beyond our cosmic horizon. The dark matter web could also provide a mechanism for information transfer between realities. Gravitational waves traveling along dark matter filaments could carry encoded messages between advanced civilizations in different bubble universes. Some theoretical models suggest that dark matter exists in extraspatial dimensions that we cannot directly perceive. These higher dimensional dark matter structures could intersect multiple three-dimensional bubble universes at once, creating gravitational connections between separate realities. Advanced civilizations could learn to manipulate dark matter filaments as a form of cosmic engineering. By concentrating or dispersing dark matter in specific patterns, they could alter the gravitational environment around solar systems or even create artificial connections to neighboring bubble universes. The cosmic web could also serve as a transportation network for travel between bubble realities. If dark matter filaments can maintain stable wormhole-like connections throughout the inflating multiverse, these structures could provide highways for inter-universal exploration. Mapping the full extent of the cosmic web would reveal which bubble universes remain connected to our reality and which have become completely isolated. This information would help scientists understand the topology of the multiverse and predict how bubble universes evolve over cosmic time. The dark matter web represents our most promising hope for detecting other realities in the infinite multiverse and potentially communicating with them. However, some bubble universes may contain intelligence so advanced that it creates new realities through the power of conscious observation. Consciousness could be the most powerful force in the multiverse. Quantum mechanics reveals that the act of observation fundamentally changes reality. Before measurement, particles exist in multiple states at once. The famous double-slit experiment shows that electrons can travel through two different paths simultaneously until someone observes which path they take. This observer effect suggests that consciousness plays a direct role in determining physical reality. In our universe, conscious observation appears to have minimal impact on large-scale phenomena. You cannot move mountains by thinking or change the orbits of planets through meditation. Quantum effects become negligible when applied to massive objects in hot environments. However, other bubble universes could develop where quantum effects remain strong at all scales. Imagine a reality where the boundary between quantum and classical physics never forms. In such a universe, conscious observation could directly influence the behavior of stars, galaxies, and even space-time itself. Intelligent beings could literally bring new matter into existence through thought, or reshape cosmic structures through focused attention. The mathematics of quantum mechanics allows for this possibility. If environmental decoherence never eliminates quantum superposition states, then objects of any size could exist in multiple configurations simultaneously until consciousness collapses them into specific realities. Civilizations in observer-dependent universes would evolve along paths completely different from life in our reality. Instead of building tools to manipulate matter, they would train their minds to manipulate reality directly.
Their technology would be based on consciousness rather than engineering. These beings could create matter by imagining it, travel instantly by observing themselves in distant locations, or even alter the fundamental laws of physics through collective consciousness. Their societies would be shaped by the understanding that reality responds to awareness. Some cosmologists suggest that consciousness may be necessary for any universe to exist. This participatory universe hypothesis proposes that realities without observers remain trapped in quantum superposition states and never develop classical properties. If this theory is correct, then observerless bubble universes would exist as ghostly quantum possibilities rather than concrete realities. Only bubbles that evolve intelligent life would collapse into definite physical states. This creates a selection effect where conscious observation becomes the factor determining which possible universes actually exist. The multiverse would primarily be filled with realities containing awareness. Advanced forms of consciousness could learn to observe other bubble universes and thereby bring them into existence. By focusing their awareness on specific quantum possibilities, these cosmic observers could literally create new realities through the power of attention. The observer effect could also explain why our universe appears finely tuned for life. If consciousness is required for reality to exist, then all observable universes must contain the conditions necessary for awareness to develop. This relationship between consciousness and reality becomes even deeper when you consider the possibility that our entire universe is a simulation running on another reality's computer. All of your existence could be code running inside a computer built by beings in a higher-level reality. The simulation hypothesis suggests that what we experience as physical reality is actually a detailed digital simulation created by an advanced civilization. Every atom in your body, every star, every thought could be computational processes running on a vast cosmic computer. This is not just science fiction speculation. The mathematics is compelling. Any civilization that develops sufficient computing power could simulate entire universes in full detail. If such simulations are possible, there would likely be far more simulated realities than natural ones. By pure probability, it would be more likely that we are living in a simulation than in base-level reality. Here's where the concept becomes truly mind-bending when applied to the multiverse. If our universe is a simulation, then the computer running our reality exists in another universe. That universe could also be a simulation running on another computer. This creates a hierarchy of stacked realities, like Russian dolls, where each level simulates the one below it. The beings running our simulation could themselves be simulations in a higher-level reality. Those higher-level beings could be simulations in an even more fundamental universe. The chain could extend through countless layers of computational realities. Each level in this hierarchy would have different computational limits. Base-level reality would have full access to the computing resources of physical matter. Every simulated level would have fewer resources because some processing power must be reserved to run the simulation itself. This creates a natural limit on how many layers of simulations can exist. Eventually, computational requirements exceed available resources and deeper levels can no longer be supported. However, civilizations could overcome these limits by developing more efficient simulation algorithms or building larger computers. Advanced beings could even learn to harness physical processes in their reality that provide effectively unlimited computing power. Quantum computers could potentially run infinite simulations by tapping into computational resources from parallel universes through quantum superposition. A civilization with quantum computers spanning across all realities could simulate countless sub-level universes simultaneously. The simulation hypothesis also explains why our universe appears to have fundamental limits like the speed of light and quantized energy levels. These could be computational shortcuts built into the simulation to reduce processing requirements.
Physical constants may represent the resolution limits of our cosmic computer using approximations to fundamental laws that would be too computationally expensive to simulate exactly. Just like video games use simplified physics to save computing resources, our universe may also use approximations because simulating the true fundamental laws is too costly. Absolutely. If we live in a simulation, we could detect glitches or structures that reveal the computational nature of our reality.
Scientists search for evidence, such as pixelation of spacetime at the smallest scales or computational limits in the complexity of quantum systems. The simulation hypothesis represents a possible explanation for our existence. But the ultimate answer may involve cycles that create and destroy infinite realities across eternity. Our universe must die so that infinite others can be born. Every bubble universe follows the same cosmic life cycle: birth through inflation, evolution through expansion and cooling, and death through heat death or collapse. But that death feeds the birth of infinite new realities. Here's how our bubble universe will end. Dark energy continues to accelerate cosmic expansion, pushing galaxies farther apart at an increasing rate. Eventually, expansion will carry every galaxy beyond the cosmic horizon of every other galaxy. Each galaxy will become isolated in its own pocket of space, unable to see or affect any other cosmic structure.
Stars will burn through their nuclear fuel and die. White dwarfs will cool into cold black dwarfs. Neutron stars will decay via proton decay, if theoretical predictions turn out to be correct. Black holes will evaporate through Hawking radiation over timescales shorter than a blink of the current age of the universe. The final state will be cold, empty space, containing only fundamental particles separated by distances larger than our present observable universe. This heat death scenario represents maximum entropy, the point at which no more usable energy can be extracted from any physical process. But the story does not end with cosmic death. Quantum fluctuations in the vacuum continue to occur throughout this decay and cooling process. These fluctuations occasionally create regions of false vacuum that can trigger new pockets of inflation. The death of our universe provides the quiet, low-energy environment where new cosmic seeds can sprout. Imagine a forest fire that clears old growth and creates conditions for new trees to sprout and grow. The heat death of our universe plays a similar role and prepares space for the next generation of cosmic evolution. Roger Penrose proposed an even more dramatic cycle called conformal cyclic cosmology. In this model, the heat death of our universe becomes the Big Bang of the next cosmic era. The geometry of space-time allows the infinite future of a dying universe to connect smoothly to the birth moment of a new cosmos. Each cosmic cycle preserves certain information from the previous universe while resetting the clock of time. Patterns in the cosmic microwave background could carry messages forward from universes that existed before our Big Bang. The endless cycle ensures that cosmic evolution never truly ends. Death and birth alternate forever, with the death of each universe giving rise to countless new realities.
Some of these new universes develop physics identical to ours. Others explore completely different possibilities. This cosmic reproduction could be guided by consciousness itself. If awareness affects quantum processes, then the evolution of intelligence in dying universes could determine the properties of successor realities. Advanced civilizations facing cosmic death could learn to encode their knowledge and culture into quantum fluctuations that shape the formation of new universes. In this way, consciousness could achieve a kind of immortality by shaping the birth of infinite future realities. The endless cycle turns cosmic death from an end into a beginning. The inevitable death of our universe becomes the fertilizer for limitless cosmic creativity.
Beyond our cosmic horizon, this cycle repeats forever, creating infinite realities where every possibility becomes real and every dream is turned into truth. The other side of the universe may contain not just more space, but also infinite versions of existence. See you in other videos. Good night.